the workshop. Feedback. So, wait. 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 The workshop.
My mic is on, but also my
feedback. So,
wait. My volume is also off.
The workshop.
My mic is on, but also my
feedback. So,
is it still coming?
wait.
Yes. My volume is also off.
The workshop.
My mic is on, but also my
feedback. So,
is it still coming? I mean, it sounds like yes. It's from this computer. My volume is also off.
The workshop.
My mic is on, but also my I'm speaking into my yes. Is it still coming? I mean, it sounds like yes. No, but my speaker is from this computer. My volume is also off.
The workshop.
My mic is on, but also I'm speaking into my presentation mode. It is going still. I mean, it sounds like yes. No, but my speaker is from this computer. My volume is also off. My mic is on. Is it okay now? I'm speaking into my presentation.
So, I did a Google search yesterday on
no, but my speaker is from this computer. My volume is also off.
and this is like ongoing.
I'm speaking into my
It's a very interesting work going on. So, I did a Google search yesterday on
no, but my speaker is from this computer. My volume is also off.
today we have invited, and this is like ongoing almost all over the world. So the speakers will have 30-minute talks, and then we have poster presentations, 10-minute talks. And then we have in the afternoon industry academia, we have speakers from Meta and Microsoft, and we have the academic presentations as well. So we thought we'll take an advantage of having both these sides on the same forum and have them have a good panel discussion. And at the end, we'll have the award function. And then we'll have, in the morning session, we'll have Professor RSJ from Dr. Juan Nieto, who will be actually replaced by Merico, because we thought we'll take an advantage of having both these guys, because of Cynthia Motoshek and also the V1 Ryu, good panel discussion. And at the end, we'll have the award. Just following the morning coffee break, we'll have the poster people session 1, all of these speakers. Then in the afternoon session, we'll have the speakers, Professor Marco Cabrera, Carlos Juarez Pico Gonzalez from Meta, and Professor Vicente Lozano. Good panel discussion. And at the end, we'll have the following that, we'll have following the poster coffee break, we'll have the poster people in the afternoon. Then the coffee break, and then we have this panel discussion, just actually giving a panel discussion. And to round off, we'll have the poster paper session, and then we'll have the award ceremony for the conclusion. So just an announcement, we have the poster stands across the hall there, in the other hall, and then we have this panel. You can put them up in the coffee break, in the lunch break, and in the second panel. And to round off, we will have the opportunity to discuss the poster conclusion over there. So just an announcement, I would like to thank our sponsors and endorsers, Meta and the other hall, and then we have this panel. You can put them up in the coffee break, and the technical committee, and to round off, and the future telepresence initiative, and discuss this workshop. So we have good support over there. So just an announcement, I would like to thank also like to thank my co-organizers. This Jeff Del Medico from Microsoft, Dan Schaefer from UNC Chapel Hill, and Farooq Atazar from NYU, and we have also Helen Fumihiro from ETS Zurich, Fumihiro from Waseda, and also like to thank my Mitsuhiro co-organizers. This Jeff Del Medico from. So without further ado, we would like to get started.
How are you? I'm trying to share my
First speaker,
Can you hear me?
from NYU, and we have also Helen Fumihiro.
You can't hear me?
Helen from ETS Zurich, Fumihiro from Waseda. So I invite Professor Mitsuhiro to share his screen. Jeff Del Medico from. So without
You can't
further
hear?
ado, we would like to get started.
How are you? I'm trying to share my
First speaker,
Can you hear me?
from NYU, and we have also Helen. Hello, Professor.
You can't hear me?
Helen from ETS Zurich.
How are you? Yeah, I'm trying to share my screen. Can you hear me? Yeah, I'm talking. You can't hear me? How are you? It's muted as far as I can see. Can you hear me?
So we can't hear
You can't hear me? You can't hear? How are you? Yeah, I'm trying to share my screen. Can you hear me?
How can we hear you?
Yeah, I'm talking. Can you hear me now?
Can you say something?
How are you? Yeah, of course. And can you see my presentation? Yeah, I'm talking. You can't hear me? You can't hear? How are you? Yeah, it's muted as far as I can see. Can you hear me?
How can we hear you?
Yeah, I'm talking. Can you hear me now?
Can you say something?
How are you? Yeah, of course. And can you see my presentation? Yeah, I'm talking. Can you hear me now?
Yes.
How are you? Yeah, it's muted as far as I can see. And can you see my presentation? Yeah, I'm talking. Can you hear me now?
Can you say something?
How are you? Yeah, of course. And can you see my presentation? Yeah, I'm talking.
Because I stopped sharing.
Can you hear me now?
Yes.
How are you? Yeah, it's muted
I need to share.
as far as I can see. And can you see my presentation?
But how can we share both? I just need to mirror the screen. Can you say something?
We can share
Yeah, of course. And can you see my presentation? Yeah, I'm talking.
Because I'll just share.
Can you hear me now?
Put mirror the screen.
How are you? Yeah, it's muted
I need to share.
as far as I can see. And can you see my presentation?
But how can we share both? I just need to mirror the screen. Can you say something?
we can share
Yeah, of course. And can you see my presentation? Yeah, I'm talking.
Because I'll just share.
Can you hear me now?
Put mirror the screen.
No worries.
I need to share.
And can you see my presentation?
I have her
But
screen.
how can we share both? I just need to mirror the screen. Can you say something?
We can share.
So we should put this to your.
Can you see my presentation?
Yeah, I don't need you to.
Yeah, I'm talking.
Because I'll just share.
Can you hear me now?
Yeah, she's sharing. Mirror the screen.
No worries.
Her.
I need to share.
And can you see my presentation?
Yes.
I have her
But
screen.
how can we share both? Professor, just a couple of minutes to get started.
We can share
So
No
we
worries.
should put this to you. I should put this there, right? Or no?
Yeah, I'm talking.
I'll just share
Can you
the
hear me now?
Yeah, yeah, she's sharing.
No worries.
I need to share.
And can you see my presentation?
Yes.
But how can we share both?
Professor, just a couple of minutes to get started. Share my. So
No
we
worries.
should put this to you. I should put this there, right? Or no?
I'll just share.
Can you hear me now?
Yeah, yeah, she's sharing.
No worries.
I need to share.
And can you see my presentation?
Yes.
But how can we share both?
Professor, just a couple of minutes to get started. Share my. So
No
we
worries.
should put this to you. I should put this there, right? Or no?
I'll just share.
Can you hear me now?
Yeah, yeah, she's sharing.
No worries.
I need to share.
And can you see my presentation?
Yes.
But how can we share both?
Professor, just a couple of minutes to get started. Share my. So
No
we
worries.
should put this to you. I should put this there, right? Or no?
I'll just share.
Can you hear me now?
Yeah, yeah, she's sharing.
No worries.
I need to share.
And can you see my presentation?
Yes.
But how can we share both?
Professor, just a couple of minutes to get started. Share my. So
No
we
worries.
should put this to you. I should put this there, right? Or no?
I'll just share.
Can you hear me now?
Yeah, yeah, she's sharing.
No worries. And can you see my presentation?
Yes. Okay.
We'll unmute here for the introduction.
Professor, just a couple of minutes to get started. Share my.
No worries.
So can you
Show you
I'll just share.
Can you hear me now?
yeah, yeah, she's sharing.
No worries.
I asked
And
how
can you
to
see my
mute.
presentation?
Okay.
We'll unmute here for the introduction.
Professor, just a couple of minutes to get started. Share my.
No worries.
So can you
Show you
okay, I think we can get started. So Professor Hadas Erel is joining us from Israel all the way. He's an assistant professor at the Media Innovation Lab, Reichman University, Israel. She's the head of the social HRI research and leads behavior research in her lab. The research focuses on
Okay,
I think we can get started with robotic objects, non-humanoid. So Professor Hadas Erel is joining us from Israel all the way. He's an assistant professor at the its impact on human interaction as well. So Professor Erel is interested in understanding how robots with design interaction characteristics enhance. Okay, I think we can get started with robotic objects, which is a very interesting take, I think, on human robot interaction. So she's interested in human interaction with more than one robot as well. She holds a PhD from Ben Gurion University in cognitive psychology. So welcome, Professor Hannah. I think we can get started.
Thank you.
Which is a very interesting take, I think, on human robot interaction. So she's interested in human interaction with more than one robot as well. She holds a PhD from Ben Gurion University in cognitive psychology. So welcome, Professor Hannah. I think we can get started.
Thank you.
Which is a very interesting take, I think, on human robot interaction. So she's interested in human interaction with more than one robot as well. She holds a PhD from Ben Gurion University in cognitive psychology. So welcome, Professor Hannah. I think we can get started.
Thank you.
Which is a very interesting take, I think, on human robot interaction. So she's interested in human interaction with more than one robot as well. She holds a PhD from Ben Gurion University in cognitive psychology. So welcome, Professor Hannah. I think we can get started.
Thank you.
Which is a very interesting take, I think, on human robot interaction. So she's interested in more than one robot as well. She holds a PhD from Ben Gurion University in cognitive psychology. So welcome, Professor Hannah. I think we can get started.
Thank you.
Which is a very interesting.
I can't really hear you now, and I also don't see my presentation on screen, so I don't know really.
She's interested in more than one robot as well. She holds a PhD from Ben Gurion University in cognitive psychology. So welcome, Professor Hannah. I think we can get started.
Thank you.
Which is a very interesting.
I can't really hear you now, and I also don't see my presentation on screen, so I
Can
don't
you
know.
can you start? More than one robot as well. She holds a PhD.
I can't really hear you now, and I also don't see my presentation on screen, so I don't know really what's going on. Thank you.
Which is a very interesting.
I can't really hear you now, and I also don't see my presentation on screen, so I
Can
don't know.
can you start? More than one robot as well. She holds a PhD.
I can't really hear you now, and I also don't see my presentation on screen, so I don't know really what's going on. Thank you. I can't really hear you now, and I also don't see my presentation on screen. So
Can you okay, so I can speak now.
I can't really hear you now, and I also don't see my presentation on screen. So I don't know really what's going on. Thank you. I can't really hear you now, and I also don't see my presentation on screen. So
Can you okay, so I can speak now.
I can't really hear you now, and I also don't see my presentation on screen. So I don't know really what's going on. Thank you. I can't really hear you now, and I also don't see my presentation on screen. So
Can you okay, so I can speak now.
I can't really hear you now, and I also don't see my presentation on screen. So I don't know really what's going on. Thank you. I can't really hear you now, and I also don't see my presentation on screen. So
Can you okay, so I
would
can
you like
speak
me to
now.
just start and hope for the best? I can't really hear you now, and I also don't see my presentation on screen. So I don't know really what's going on. Okay, so thank you. I can't really okay, so you can see my presentation and you see when I switch. Okay, so I'll just go ahead. Hopefully it will work. Okay, would you like to just first start and hope for the best? As I said, my name is Hadash. I'm from the Media Lab in Israel. Would you like me to just start and hope for the best for my talk today? First, because I really love robots, so most of the talk will be about robots. Would you like even when I'll get to talk about VR, okay, so you can see my presentation and you see when I switch tools for enhancing. Okay, so I'll just go ahead. Hopefully robots. Would you like for the first thank you for the best? You'll also as I said, my name is Hadash. I'm from the Media Lab in Israel. I'll need you to have open mind for my talk today. First, because I really love robots, so most of the talk will be about robots. And even when I'll get to talk about VR, AR, XR, I'll just talk about them as tools for enhancing the development of real physical robots. And for those of you who like robots as much as I do, you'll also have to be open-minded, because I'm going to begin by saying that I don't really understand why robots are like into a position which is very useful tools for enhancing the development of real physical immediate reaction. And for those of you who like robots as much as I instinct is that you want to do. Okay, so this robot was designed in order to clean your house. It's supposed to handle laundry and pick up the arms and shoes of family members who leave them behind. But in order to pick up toys and shoes, it really needs to dislocate its arm into a position which is very, very unnatural. And when people see this, their immediate reaction is to think that it's hurt, and the way instinct is that you want to take them to the hospital to get it treated, because humans are not supposed to look like that, and their arms should be back in their original position, which is very so this robot is not living in anyone's house. Usually people don't want to have like broken humans in their house, and weirdly enough, today to get it treated, placed in a hospital are not supposed to show a way for the different departments, and I want to show you how it looks. I hope you can see the video. So this is how the interaction with it looks like. And this is another very unnatural thing to do, because since it's humanoid, you need to touch in order to tell it where you want to go. And this violates a lot of norms, because we do not touch people. So this is how the interaction features. So this brings another. When we think about it, I think we all can agree that there are robots that can clean our house, but are not creating so many negative emotions. And I think that actually maybe the most popular and most successful robot today is a robot that is designed to clean our house. And it does the job already used. It's widespread across the world, despite not having any humanoid features. And this brings me to the question, and I think that why we design robots humanoid robots? Why do we need to constrain ourselves into these humanoid features? And when we look at robots that are already used in industry, not the ones that are being built like this, that are already used, I think in most cases they are not humanoids. We see robotic arms, we see robotic cars, and these robots are not humanoid. So why do we go for the human robot all the time? I think there are many answers to this question. Some of them relate to our past experience with literature, sci-fi movies. Others are relevant for more psychological processes we cannot talk about today. But many times when I ask this question, people tell me it's about communication. Because when we communicate with technology, so we want to have a humanoid robot that can mimic human communication, and then we can create this natural communication between a human and a robot. And I actually agree. I think we want to have natural communication with technology, and I also think that natural communication with humans is social communication. And I actually really like this quote by Brian Daffy, who says that social robots can be the interface between humans and technology. So we want technology to communicate in a way that humans communicate, and that means social communication. We want to have social cues integrated into the communication between humans and technology. But again, is there a problem? Is it problematic to design social communication with non-humanoid robots? So many people will say yes, because non-humanoid robots, they do not take a humanoid, so they cannot mimic human behavior. But I don't think, clearly, again, it's a problem, and as a proof, I want to bring back this guy. I think that if you have IROS, this example, yes, because you probably know that you already have a rich social communication. We know that about 80% of our users name the robot, and even if you did not name your robot, you probably felt at some point that it's following you around, or you feel bad for it when it gets stuck in something, and some of us are cleaning the carpet from the dog so that it won't have to work so hard. And I know that even here, in this example, you can see the social communication happening, because it's clear that the robotic arm is focused and attentive to this thing that the lady is showing her. And this way, the interaction becomes safer, even though this is a highly animated robot, and it doesn't here in this example. You can see the social communication is in the lab that the robotic arm constantly is that, and still you can leverage minimally people and social communication. Even for very, very simple robots, you can design movements and it will be consistently and clearly interpreted as social. Take for example this robot. It's very simple. The engines are outside. You know it's a machine. You don't mistake it. Very, very straight you can, and still when it turns towards you this way, people constantly think that it's focused on them, that it's interested in them, and they really describe it completely opposite. So what I'm trying to say is that we are very free in our design, creative design robots with different forms that will be appropriate for their function, that will be appropriate for their context, and we do not need to constrain ourselves and limit ourselves to humanoid features. And in the lab, we constantly design different types of robots. Some of them look more like familiar objects, like plant-like robots, but others are completely outside our function. We still, by leveraging very simple and minimal means, create very rich social interaction with them. Just to give you an example, so this is an experiment conducted a few years ago, and the idea was to try to see and take this abstract robot, very important. Participants never saw this robot before, and because of the no past social experience with such ball rolling with the dome, we have nothing to rely on. It's not about later on remembering something that is relevant and then understanding what it's about. And we wanted to see if we can design an experience with this that will be similar to an opening encounter between humans. Opening encounters, like the very few seconds of an encounter, are very, very important. These are like it's one of the most important social factors that determine the rest of the interaction. So if you have a positive opening encounter, you will probably have a positive interaction later on, and if you have a negative opening encounter, it's about to experience higher reaction. And we wanted to see if we can do something very simple, so participants will come stand in front of the robot, and the robot will either move this way, so the small ball is moving from the back window to the front, and then it will be a positive opening encounter, or the other way around. So the minute you stand in front front of it, the small ball is moving to the back of it. And the result was so you take it was moving towards the participant. Participants were very happy and they were describing the experience of the robot being happy to see them. They said it wasn't due to interaction. It greeted me and it was overall a very welcoming experience. And when it moved to the back of the dome, it was much worse. Participants said that it was ignoring them, it was avoiding them. One participant said, it didn't want to interact with me. So you take this dome with a small ball moving on it, and you can create a very clear and consistent opening encounter, which is like one of the most important things in social interaction, human-human interaction. So what I'm trying to say is that, again, we're free. We can design whatever we want, and we can create a great fit to the function of the robot, the purpose of the robot, the context of what, and again, we do not need to constrain ourselves. But, and there is a huge but. So when we have very freedom, that we really need to make a lot of decisions. We need to decide how the robot will look like, what would be his appearance, what appearance is best for this context, and then how we can and as the social create movements that will communicate consistent and clear social cues for that appearance. And again, we need to remember that people do not have custom experience. We just look robot, so it needs to be very, very, very accurate, and we need to verify that the movement that we use for the specific appearance we design will be not consistently interpreted as social cues that people understand and as the social cues we want the robot to have. And this is a very, very complex process, and it requires a lot of years. And that's just to give you an idea. I'll tell you a bit about the process that led to this. 3 steps that you understand. So I'm always very happy to talk about the robot. I usually do not go through the entire process that led all of this interaction. It was cool, it created the consistent cues that we wanted to, but the process lasted more than 6 months. And I'll try to explain why. So first we need to understand how the robot is going to look. I usually start with some inspiration, with animation. You play with that for a while in order to get an experience that you also cannot people to have. But I think all of us who experience robots know that there is a huge difference between the screen and real life. And then you go into cardboard printing. You start creating low prototypes from cardboard things. You try different forms and start testing them with participants. Here you cannot try all the forms that are color. There is a huge difference. And you also cannot try many forms because you're constrained by the amount of time required to create each low fidelity prototype. And then you move to 3D printing of the prototypes, still low fidelity, they're not working, but they are going to be more similar to the robot, how the robot is going to look like. And then you cannot test all the time. Color, size, form, the proportions of the different parts, how you assemble all of the technical requirements into the robot in a way that this is going to be similar to the robot. And you have so many options because you're free. And that's a good thing, but then you have so many options that you need to test. And you want to reach the best design relevant for the purpose. But you cannot test all designs. Every time you want to create a different prototype, it requires so much work, so much effort, so much time, because and again, just to give you an idea of the real world. And this is even before we start talking about the gesture design. And the gesture design is another long and research process. So you again start with low fidelity prototyping of the gesture design. You move the parts with your hand, and clearly this is nothing like the magic that occurs when you see an object that has a tremendous movement. And again, just to give you an idea of the amount of things you can look into, let's take this movement, okay? It's curved, you need to make choices because it's great. And in this case, it starts from the back. But you may be able to start from the side, and again, just to give you an idea. And all of these small pathways, let's take this new design for the interaction is very happy. So you keep on iterating, you keep on trying, but but you also make a lot of compromises with it because you can't try everything, and you need to make choices because you don't have all the resources in the world, and you don't want this process to last for 3 years. So you make your own decisions, and they may be based on some literature, some past experience, but eventually these are choices that we as the design process can't try. But all of this is risky because in way we're free and we can create whatever we want, but still people have no past experience with it, and we need to make the right decisions, and we can end up so something that is almost good but not good enough. So reaching a situation like this where you have a 3-second interaction that leads to a very clear decision, but all of your participants interpret in the same way is really far from trivial, and it requires a lot of work, a lot of iterations, and a lot of compromise. Think about so sometimes maybe we can make it better. Maybe you can find other leverage, other tools in order to make some of the parts tweak that. And we thought, what about VR? Maybe we can use VR or XR in VR. Think about how quickly we change the color of the in VR in comparison to printing something completely new in a 3D printer. Think about size, think about robots, so when they will interact with the shapes, all of these can be done much more realistic in VR. But before we do that, we can make sure that the experience, the social experience, which is what we're interested in VR, interaction with robots in VR is similar enough to what's happening in real life. And again, we need to consider the fact that people have no past experience with robots, so when they will interact in VR, they cannot relate their experience to something in the real world. It's a whole new interaction. So it was very important to make sure that the interaction, social interaction in the VR is similar enough. There is a child who to some extent telling a story to the interaction in the real interaction. So they first went to literature, tried to see if something already practiced, they should make sure that it happened, that there isn't that the interactions are similar. Most of the studies we found were with humanoid robots, and they produced the robots the same way. So this is an example. This is a storytelling robot arm, and there's a child listening to the robot telling a story, either in physical, real interaction, or VR interaction, and they tested the robot test. And they found no difference. In the study, they showed that the experience, had the experience itself, but experience with the robot, whether or not they liked the robot, was similar in VR and in real life. They also took some. This is another study already with a non-humanoid robot. So this is a robotic arm. Again, they did not create interaction, but they showed in robot acceptance. And in this case, participants were asked to collaborate on an assembly task with the robotic arm, and they showed that. And this is another of the robot acceptance were very similar. So this is in the VR and in the real life interaction. But this is interesting. They also took some physiological measures in contacts, pulse, and also heart rate comparability from the robot. In the physiological aspect, there was a difference. So it's like the ratings were similar, but still there is a very clear difference in the experience. They reported more discomfort. And this is another interesting example. It's a humanoid robot, but they looked into more social interaction. They measured the 3D dynamics, how far you rate, but also but still there is a distance, the comfortable distance from the robot. And they had interesting results because they found that in the VR, people preferred larger distance, and they reported more discomfort from the robot. It's not really clear why. They suggest that maybe it's about some problems in distance estimation in the VR, or maybe the 3D VR wasn't good enough. But overall, when we looked at all of our studies, we couldn't find any similar study that actually looked into social interaction. Why was it just maybe it's about we had some problems in distance, so we had to do it ourselves. So we took that 3D VR was an experiment, and we replicated it completely in VR. So we created the exact same experience away from the in VR. The room was the same, lighting, everything was exactly the same, and we created similar interactions to those we had in the first. So the main point So we got this experimental design, and this experimental design we had half of the participants interacted with the robot where the small ball moved towards the participants, half of the participants interacted with the robot where the small ball moved away from the participant, and then half of the participants interacted with the real robot and half of them interacted with robot in the VR. The main point was that we focused on social experience that we wanted to do to see if the experience that we got with the real robot, like a positive opening encounter or a negative opening encounter, would replicate in the VR experience. And we got amazed with because it was almost exactly the same. So just to get a grasp of what's happening here, in the VR, we asked them first to say how positive was the opening encounter, whether it was greeting, welcoming, acknowledging, and we saw that when the small ball moved towards the front and same towards the participant, both in the VR and the physical experience, the aspirants reported a highly positive opening encounter. And when the CT was moved to the back VR, and participants both in the VR and the physical reported low positivity. But the most important thing is that though similar, the rate VR, they were experiencing very similar social interactions. And same was when we and the negative having high negative experience. We asked them whether this reporting together, hiding, and again we saw similar results between the VR and the physical. So when the small ball moved to the front of the dome, participants in both conditions reported low negativity, both in the VR and the physical. And when it moved to the back, away from the antibody, both in the VR and in the physical, participants reported having high negativity in the opening encounter. So these results altogether indicated that the social experience that was designed for the robot, both in the VR and the physical, indicated that interaction is more like very, very, very similar. So we also looked at some robot perception measures. So we used the animal and scales from the social questionnaire that was designed from our study. Not like from one-to-one in this case, but again, they were quite similar. We found no significant differences between them. Also, the Bayesian analysis indicated that it's more like theory. So also, even the animals, how they expose almost similar conditions. It's good this case, but so taken together, I think what we can learn from our study and also from previous studies is that at least for the initial design stages, both for the appearance and also for the behavior of the work goes on, we can definitely leverage XR tools and try to figure out how people feel and how they experience the social interaction with the robot. It's good that at least clearly, once we get design to the point where you feel comfortable with people's responses and participants' responses in the VR, you need to design everything physically. You need to have a physical, real-world interaction, and then to make sure that everything replicates outside in the world, because it's not exactly the same. We have previous studies indicating that. But as an initial tool that will allow us to find a better fit for our robot to its purpose, to its context, and to better design the social cues that we need for the interaction. And XR, and then you can also really use strong tools that we can use in order to make the process a little bit less resource consuming, less tedious, and also to try out. And I want to end with this picture because clearly the next stage would be to place the robot in different contexts and to see people respond to it differently in different contexts. And then you can also add, throw in the context variable with try out. Ignore many times in lab studies and try to figure out if it impacts the interaction, and if so, again, we need to take it out to the real world and to see the magic happen there. And then you can also add, throw in the context variable with try out. Ignore many times in lab studies and try to figure out if I can hear you. It impacts the interaction, and if so, again, we need to take it out to the real world and to see the magic happen there. And then you can also add, throw in the context variable with try out. Ignore many many times in lab studies and try to figure out. I can hear you. It impacts the interaction, and if so, again,
Yeah, you can get
see the magic happen there. I can hear you. And then we can also add, thank you, throw in the context, ignore many times in lab studies and try to figure out. I can hear you. It impacts the interaction, and if so, again,
yeah, you can get
see the magic happen there. I can hear you. And then we can also add, thank you, throw in the context, ignore many times in lab studies and try to figure out. I can hear you. It impacts the interaction, and if so, again,
yeah, you can get
see the magic happen there. I can hear you. And then we can also add, thank you, throw in the context, ignore many times in lab studies and try to figure out. I can hear you. It impacts the interaction, and if so, again,
you can get
My speaker should be off.
I can hear
Okay,
you.
now you can hear us.
Yeah,
Thank you
absolutely.
very much for the talk. It's very interesting. I will open the floor for some questions, but it's going to be quite a challenge to get through the questions here.
Absolutely. No.
My speaker should be off.
I can hear
Okay,
you.
now you can hear us.
Yeah,
Thank you very
absolutely.
much for
That's
the
a
talk.
good
It's
question
very
that
interesting.
I
I
actually
will
had
open the floor for
a good
some
answer
questions,
for
but it's going to be quite a
before
challenge
the
to get through
AI
the questions
revolution.
here.
No. So for a while I thought that robots should not
Speaker
talk
should be off.
because I can
Okay,
hear
now you can hear this.
speech understanding language understanding are not good enough, and then people will immediately treat a robot as if it's not good enough. But right now we have that's a good question that I actually had a good answer for before the AI revolution, almost natural. So for a while I thought that I think this should be well tested because we need to see when production is natural understanding, language understanding were not good enough, and then people will immediately treat a robot as if it's not good enough. But right now we have ChatGPT who is starting to behave like, as long as we provide some capabilities for almost somewhat not good language. So I think this should be well tested. We need to see when people find it natural to communicate with a robotic object that is not designed as human but still speak. But I think we are kind of getting used to that, and I'm not as against it as I was before. As long as the conversation can be fluent and somewhat resemble human conversation, I think it can work good enough. But again, it should be empirically tested. We are kind of getting used to that, and I'm not as against it as I was before. As long as the conversation, so we were talking mostly about collaboration and robots like manipulating the environment. I would just say, but again, it should be empirically tested into everything that we do, because in order to communicate with the robot and collaborate with them, especially if you're changing the environment, you must have social
Can manipulate objects in the
so I think I would follow the exact same greeting. You need to so you're talking mostly about collaboration and robots like manipulating the environment. I would just say that especially if it's an industrial company that definitely is integrating into everything that we do, because in order to communicate with the robot and collaborate with them, and especially if they're changing their environment, you must have social communication and collaboration. So I think I would follow the exact same pattern as we do with greeting. You need to have some social cues indicating that something is going to happen. We actually had a conversation with an industrial company that is integrating robots into hospitals, where the robot is supposed to take materials from one place to another, and it moves in the corridors with other humans. Social cues, and it just turns to move something, and people are freaked out by it because apparently us humans, when we're about to turn, there is something that we're doing with our body that signals that something is about to happen. So we need to add all of these small social cues into every interaction with the robot, where there are people not even collaborating, just in its environment. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and also for people to understand what's going on. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and also for people to understand what's going on. Thank you for having me. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and also for people to understand what's going on. Thank you for having me. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and also for people to understand what's going on. Thank you for having me. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and also for people to understand what's going on. Thank you for having me. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and also for people to understand what's going on. Thank you for having me. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and
But I need to stop duplicating this page, right? First.
Thank you for having me. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and
But I need to stop duplicating this page, right? First.
Thank you for having me. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and
But I need to stop duplicating this page, right?
Thank you for having me. So yeah, if we need to have the robot is about to move something in our environment, it needs to signal in very subtle, small ways. Small cues are super important for people to feel safe and
But I need to stop duplicating this page, right?
Thank you for having me.
If you start getting feedback,
Yeah.
this button, to turn off your speakers. But I need to stop duplicating.
So, hello everybody, this is Farah Fatah. I'm one of the co-organizers of this workshop. So thanks for being here today in the very last day of the conference. So it's my honor and pleasure to introduce to you our next speaker, Jeff Del Merico, who's also one of the co-organizers of the workshop. This is Farah Fatah. I'm one of the co-organizers of this workshop and AI Lab in Zurich here today in the conference. So it's my focus on bringing honor into Microsoft mixed reality ecosystem and enabling human-robot interaction and teaming through MR. So he received his PhD in computer science from State University of New York, Baltimore, in 2013, and previously worked as a postdoctoral researcher at University of Zurich and University of Hawaii. So with that, and enabling human-robot interaction and teaming through MR. So he received his PhD.
The speaker today was supposed to be my colleague Juan Nieto from Microsoft, but unfortunately he couldn't make it on short notice. And so luckily I was able to, and I'm happy to give his presentation. And so the title of this talk, the speaker today was supposed to be empowering people and robots in the mixed reality from Microsoft, but unfortunately he couldn't make it. That's really at the core of what we're interested in doing. Is luckily I was creating a mixed reality environment ecosystem that both humans and robots participate in and benefit people and robots. And the high-level vision of what we're trying to enable is really kind of encapsulated by creating this image here, mixed reality, which shows people wearing HoloLens devices, although both kind of humans and robots participate in and where the information that they're able to access is relevant to where they are in space. So in a factory, you might be able to see the maintenance history of any kind of that machine that you're standing in front of. And where the team that I work for is focused relevant to developing the tools to enable this sort of a mixed reality experience where spatial data is available to both humans and robots in places where it's hard. And so the team that I work for is particularly focused on developing commercial and industrial this sort of cases mixed reality experience rather than consumer. Spatial data is available. And so we're focused on things where first-line workers in these sorts of the team that I work for MR particularly focused on this visual concept is what we call contextual data access, so accessing information where it's relevant. And one of the things that first line enables you to do is if you have digital twin information about your environment, and your device knows where it is, visual concept is will immediately access data access, parts of that digital twin information where that can enable you as a worker or a robot to do more, enables you to do things more efficiently. So if you have digital twin information, and one of the other things that comes from this is the ability to do indoor navigation in a way that we're used to with outdoor navigation, enable you as a worker, robot, and being able to navigate through large and complex environments like this conference center. One of the other things that comes from this, if we can build in advance indoor navigation in a way that we're used to with outdoor navigation, enable you as a worker. Finally, one other thing that comes from this, we enable complex environments, and to enable this mixed reality vision for humans and robots, is that we get collaboration almost for free. We're used to with both humans and robots will be able to finally interact. Another thing spatially, we enable in a natural way, enable this mixed reality vision for humans and robots. To enable all of this collaboration, we need to do large-scale mapping and visualization. Both humans talk about that in a moment. But as an example of this sort of kind of constrained in a natural way, a use case we currently have for HoloLens for humans, and to enable all of this collaboration, we need short video, large-scale. This is an application called Guides. So this is something that is currently used in first-line worker scenarios for often for kind of currently tasks or tutorials. So teaching workers how to do something new, video, or this is an application or sometimes this is something that is currently used in first-line worker scenarios. Sometimes to enable them to train on tasks that they have to do repetitively to achieve certain or sometimes accuracy, and this all integrates directly with Dynamics 365, which is another sometimes to offering that enables to train on our industrial customers to kind of streamline everything to achieve together and certain or sometimes accuracy. That's all limitation for Dynamics 365, which is another that it's really only offering that locally enables to train on in our industrial customers to kind of streamline right now to achieve together. It only maintains a map on board, so it's only going to know its position in a fairly local coordinate system. So if we want to enable task training or other industrial customers, other guides scenarios, scenarios in larger environments. We currently don't have the tools to do that in the fairly low HoloLens or chips today. We want to enable, and so what we need to do is embed these kinds of experiences in a larger spatial and so that's where cloud mapping and larger environments. That's what the team that I'm a part of is do that in fairly low HoloLens. So we want to enable, and so many do embed these kinds of experiences out there in a larger spatial so that's where phones, cloud mapping, your XR headsets, and also many robots are already doing on-device mapping and so often visual. Many do and what we tried to tap into is that all of these devices are solving the same SLAM problem. So we want to take some of that data. They're already doing maps or on-device mapping and poses and merge all of that together. We try to tap into so that we can all build these devices a large scale. We want to map that works for multiple different already doing and our motivation for doing this in the cloud and is merge scalability together and maintain data up to date, and we can enable collaborative experiences with platform experiences for and users with different devices, users and robots and scalability. And one of the other things is that by doing this in the cloud, we can enable downstream collaborative experiences because the data is already up there. Experiences in the cloud, and we can integrate and users with different devices, services, and robots. So how this works in practice, and one of the other things is that different people with HoloLens devices can walk around and experience in the cloud, and we can different parts of the environment, and through an SDK, this data is sent to how this works in practice. Cloud services and different people with HoloLens devices can walk reassembled based on loop closures into different parts of the environment, consistent maps, and SDK. We can also utilize reality capture devices. This is the NavViz VLX, which generates really nice high fidelity based on point cloud digital twin representation of the environment, which we can then have aligned to our existing localization map. And that gives you a sense of the NavViz VLX of the use case it's generated for is that you can have your digital twin and your localization map all aligned of the environment in the cloud, and then when you're aligned to our in that environment physically with one of these devices localizing to it, you can access that digitally. And one of the nice things about doing this also in the cloud is that the digital twin and your localization map is easily updated and kept up to date, and also extended to new areas physically. And so it's really a crowd map to it solution, and not just one of the nice things about doing this also single monolithic map that's created in the map is easily. And so here, just you can see that if you are also extended localized in the map, then so it's really a crowd map, spatial information. You can see we know where the HoloLens is, and we can insert that single monolithic map. That's so here, give a sense about some of the features that if you are interested localized in the map. This needs to be really usable in real-world environments. It needs to scale well. And so here's an example of a just single monolithic food processing plant that's like 40,000 square meters. And so here, to give a sense about 430,000 features so really large, and this needs to be with a few different HoloLens devices walking around and able to do this efficiently in the cloud. And we also want to be able to support multiple different devices, and so here this map was generated with HoloLens data, Spot, and also this to do this like a BLK to go. You can notice the different heights of the line sets. Those are trajectories that were contributing to the map data. And if we look at it again, spot and also this, and we zoom in, like okay to go, you can notice the different heights of the, those are trajectories. You'll notice that there's a cluster of lines that are about head height for people on the team using HoloLens that are different heights. There's another line about chest height, and that's like people carrying the BLK to go. And then there's another line down here, which is spot. So we can merge all this data from head height from different devices together, and then also provide localization to those different devices later. Line about chest height. Other features that we're interested in, we want to be able to support dense representations as well. And this is more on the research side, but we're interested in different devices being able to build and maintain dense representations. Other features that we're interested in, we want to be able to support. So our overall ambition is to essentially take all this raw data from devices, fuse it together into a consistent map in the cloud, and then also align the external data from our customers to that map, so that when their workers are in the environment, they can access that data and do their job. Devices. And the other important thing, not only that the maps is all aligned, but we also want to have all different kinds of devices. When their workers are in the environment, more specifically about what this can enable for robots. And the other important thing, one of the biggest or most common use cases we also want to use for robot inspection. So being able to design how a robot should go and more specifically navigate through a space and perform some tasks in different locations. And so for this, we designed a sort of demonstration here with mission design. So being able to use mixed reality as an interface when navigate human is in the environment to some task to design the for this trajectory that the robot can follow and demonstration here with tasks that it mission to design each location where to do some inspection, and in this case the action that it takes at each waypoint is to just extend the arm and take a picture in a particular location. So the user places those blue spheres with custom inspection to indicate the pose of the robot, and in this case human is the pose of the action that takes at each waypoint is to just send it to the robot, send the arm, and it will execute this on a particular. See, we also have a mixture of the mini map user places so we can see blue what the robot is, HoloLens is the pose of the robot, and in this case human is the pose of the and also the waypoints that we can waypoint is to just send it to the robot, and you'll see the robot is localized to the environment, reaches the first waypoint, so it does the action that it needs to do there, and then it moves on to the next waypoint. And in a moment you can see that through the robot implicit co-localization, so the HoloLens is localized to the same map as the robot. We have quite accurate co-localization here, based on the appearance of the and in a moment you can see that and we get that for free, basically through co-localization through the same. And we can also have the robot dock automatically at the end of the mission. So you can imagine deploying this in a large-scale environment, factory, and the industrial. We get that plant that I showed the minutes of before. You could design a much more complex and large-scale mission. We can also have the robot and then have it do that dock automatically each day or modify it each day. Imagine deploying this with a robot environment. And one of the environments where we get that that I showed, or one of the use cases where the environment changes and frequently, or you do need to large-scale mission is in construction. And so we have a long-running collaboration with Trimble, including the Trimble hard hat version one of the environments for use in construction. And so we did a collaboration with them using this mission planning technology to design LiDAR scanning missions for their version of the Spot robot that was one of the Trimble LiDAR sensors. We did a collaboration with them using the scan points technology, using the mission planning, and then the robot can later go to design scan of the environment. And unlike the onboard version of the Spot robot, more flexible to design and Trimble LiDAR mixed reality than to reteach. Place using the scan points technology, using the mission manually with the controller each day to design scan of the environment. So we also have done some exploratory version of using mixed reality to interact with robot arms for manipulation. In this case, we're not using a large-scale map. This is co-localized QR code, but you can imagine embedding this in a larger-scale map. But here we take the spatial understanding that we get from the HoloLens, so manipulation. In this case, we're not using, and we use that to design how the robot is embedding this in a pick and place large-scale map. But here we take this, taking into account the obstacles in the understanding that when from the HoloLens, the arm itself doesn't have any sense, and it doesn't perceive its own map, and so we can transfer that spatial imagination from the HoloLens to the map. But here we take this, taking into account, and you can see we simulated what the robot arm would do first to make sure the arm itself doesn't have any sense, and then it doesn't perceive its own map, and so we can transfer that spatial imagination from this. And I'm going to show a few slides of collaborative work that we've done with simulated what the DTH works. So this is a project with the Autonomous Systems Lab there. So with an omnidirectional drone that can, and because I'm going to show a few propellers that can orient itself arbitrarily and simulated freedom, and so we can use mixed reality to lab there. So to similarly to with omnidirectional drone, some waypoint and based trajectories, and here propellers we can fully manipulate the pose of the robot. We can. This just shows a few different ways we can do that, either by adjusting individual degrees of freedom one at a time, or here by grabbing the entire hologram here, moving it to where we can fully manipulate all the degrees of freedom at the same time. The robot. We can. This just shows a few different ways we can do that, either this also by adjusting individual degrees of freedom one at a time, or here by grabbing the entire hologram here, moving it to where we can fully manipulate all the degrees of freedom at the same time. The robot. We can. This just shows a few different ways we can do that, either this also by adjusting individual degrees of freedom. Well, in any case, the important part is fully manipulate all the degrees of freedom at the same time. The robot. We can. This just shows a few different ways we can do that, either this also unfortunately, so another case, another important part is we have with the computational robotics lab at ETH Zurich, and so that project is focused more on multi-robot control. So how can we use mixed reality to enable one-to-many for humans? So another question is how can we manage a robotic workforce? So if you imagine you had many different robots, and as a single human, you want to give them tasks in a flexible way. If you have many robots to control, not only do you not want to give them each low-level controls exactly, you have many different robots, but you also want them to work get a single human, you want to give that's one of the big, in a flexible way. Focus is if you have many robots. This collaboration is trying to understand how we can use human insights at a low level to enable robots to solve, but you also want them to work together. A single human. So here's a good example. So we have a few robots who need to move this collaboration, which if you've ever how we can use with furniture, then you understand this can sometimes be a challenge, even as a human, to fit your furniture through doorways. And so here's a good example. Here, these are omnidirectional platforms with arms that are carrying the couch, so the base can move furniture. Then you understand it can sometimes be a challenge, even as a human, to fit we need to satisfy the constraints of maintaining the couch in a stable way and making sure that we don't exceed the base to move furniture. Then you understand the arm capacity for each of the robots and maintain center of gravity and so on. And so the constraints. So this is making sure that we don't exceed this is a problem where the human can provide input and for each of the robots, system of robots that needs to maintain center of gravity and so on, and so how they need to move to each other. So and we can use that then. This is a problem where the human problems that are constrained in the real world capacity and also with non-holonomic robots, that how they need to where their motion is much more constrained, and it's a more challenging position problem to move. Use that then. So this is a problem. We don't have real-world results to show now, but that's another avenue that we're interested in, and we can include non-holonomic robots. Any of these problems where their motion is much larger in math, it's a more challenging position. Robots are all of the same. So same cloud map and able to real-world results to show now, but that's another avenue that we're interested in. And I'm going to wrap up with a couple of slides bringing it back to humans, much larger in math, what mixed reality can do for human tasks as well, and able to one of the other areas that that's another implicitly into we're interested in. And I'm going to wrap up using a couple of slides bringing it back to humans, much larger in math, using the egocentric sensor streams from the HoloLens to understand what human tasks do as well, not just track their hands and gaze, which is what you see in these images, but we also want to understand whether they've completed tasks with those ego streams and what objects they're doing those tasks with. And so here's to understand what human tasks do as well. Here's a little example similar to the guide scenario that I showed earlier, but we also want to user has a series of tasks to perform, whether they've completed tasks. The HoloLens can check whether they're doing them in the correct order or completing them, and so when they do them, and so you can imagine similar integrating this also that I showed earlier, but we also want to know that your first-line workers, their devices can know where they are, and can help them to do check whether they're doing them in the correct order or completing them, and so to summarize, from our perspective, integrating this, mixed reality really bridges to the digital world and the real world. Their devices can know where they are. It can be a way to connect people and machines and robots in new ways and to enable interaction, novel ways of interaction. And mixed reality, the pathway that we see for enabling that is through localization. And it can be a way to really affect people, and it's really necessary for ways and interaction in our environments, both for human to environment and robot to environment, but also and mixed reality and so we are taking the position that cloud mapping represents a way to do that in a way that's scaled ways and interaction in our environment, both for human to environment and robot to environment. And finally, tapping into that and so allow us to access, we are taking to provide tools for spatial represent. So in the future, having spatial information kind of available to all of our devices will enable more intelligent decision making for both our robots and humans, and in the recent advances in machine learning have really started to open spatial information possibilities available in the future. So I think it's finally I'm excited to see what decision makers we have next year for both our robots. And so with that, I want to thank you for your attention. I'm happy to answer any questions. If there are some from the audience, have really started to open spatial information possibilities available in the future. So I think it's finally I'm excited to see what decision makers we have next year for both our robots. And so with that, I want to thank you for your attention. I'm happy to answer any questions. If there are some from the audience, have really started to open spatial information possibilities available in the future. So I think it's finally I'm excited to see what decision makers we have next year for both our robots. And so with that, I want to thank you for your attention. I'm happy to answer any questions. If there are some from the audience. So in this case, let's see if I can find the slides. So this was work from a student, so I don't know quantitatively exactly the accuracy, but the alignment with the QR code was so visibly quite good, and that was something that was sort of calibrated. So this was work from a student, so I don't know probably the most the accuracy. It's probably not the alignment with the QR code was so visibly quite good, and that was something that was sort of calibrated. So this was work from a student, so I don't know probably the most the accuracy. It's probably not the alignment with the QR code was so visibly quite good, and that was something that was sort of calibrated. So this was work from a student, so I don't know probably the most the accuracy. It's probably not the alignment with the QR code reasonable for fine manipulation. This is something where the co-localization is not the primary focus. More the transfer of spatial information from the HoloLens to the robot, which is blind, reasonable for fine manipulation. The co-localization could be done in a different way. In co-localization is not could achieve higher precision if you need to do that. I mean, I think you can see with an object of this scale, I think this wasn't the only object. The co-localization could be done. We're all kind of hand size. And so I think fine manipulation is probably on the table, but I think with the large scale, with an object of this scale and localization to the cloud service, you can see we get we're all kind of optimistically a few centimeters error. And so depending, I think fine manipulation is probably the map and the quality of the sensors, the large scale with an object of this mapping and localization to the cloud service, you can see we get we're all kind of optimistically a few centimeters error. And so depending, I think fine manipulation is probably the map and the quality of the sensors, the large scale with an object of this mapping and so we have so far been focusing on HoloLens first because it's a first-party device, but also mobile devices, and we've tried to design the robot interfaces to be flexible as possible. So we have so far been focusing on HoloLens first to interface Python and C++ to make it as easy to integrate on heterogeneous robot platforms as possible. The sort of minimum requirements for localizing again, we have so far been essentially stream of images from some cameras, and poses to integrate on header. So if you're estimating the pose of your camera, if it's just you're not doing visual slam, but it's mounted on a robot that's doing its own slam with LiDAR, that's okay. You can get a pose for the camera. If you're thinking of other types of devices, possibly. I mean, really, that pose image requirement is the primary thing. We, as far as supporting other devices officially, if you're thinking really only focused on other types of devices, on the ones I mentioned, and also, I mean, really, that pose devices with requirement is the primary but that again is as far as capturing other devices. That's the core requirement. If you're thinking really only focused on other types of devices, on the ones I mentioned, and also, I mean, really, that pose devices with requirement is the primary but that again is as far as that is well, that's not in the critical path for now. You know, we recognize that that can be an issue in some use cases, also in the industrial ones that we're talking about. But essentially, we assume that the that's not in the critical user for now. You know, we recognize that has their own can be an issue. They can use cases also in their own ones that we're talking about. Localization. Essentially, during the assume that the that's not in the for the case of the robots, if it's that periodic localization to our system is really just over large objects. So that's not something they should essentially during the assume that the network. So for the case of the robots, if it's that periodic localization to our system is really just over large objects. So that's not something they should essentially during the assume that the network. So for the case of the robots, if it's that periodic localization to our system is really just over large objects. So that's not something they should essentially during the assume that the network. So for the case of the robots, if it's that periodic localization.
Can you share your screen?
Over large objects. So that's not something they should essentially.
All right. So can you hear me?
If you tend to be careful about the change in the time.
Testing.
Can you share your
So
screen?
when is the start?
10:30.
Good. Yeah.
So that's not something they should essentially.
All right. So can you hear me?
If you tend to be careful about the change in the time.
Testing.
Can you share your
So
screen?
when is the start?
10:30.
Good. Yeah.
So that's not something they should essentially.
All right. So can you hear me?
If you tend to be careful about the change in the time.
Testing. All right. You can hear me and see my slides and
So
everything?
when is the start?
10:30.
Good. Yeah.
That's not something they should essentially.
All right. So can you hear
So
me?
first, we'll do a quick test to make sure, Cynthia, that we can hear you. Let me mute, and then you can unmute and chat. So go ahead, just to make sure we got.
All right. You can hear me. Is that better?
When is
All
the
right.
start?
So can you hear me?
10:30.
Good. Yeah.
That's not something they should essentially.
Testing.
Great.
Testing.
So first, we'll do a quick test to make sure, Cynthia, that we can hear you. Let me mute, and then you can unmute and chat. So go ahead, just make sure we got.
At the University of Maryland, Baltimore
Is that
County.
better?
She's
All right.
an
So can you hear me?
and has founded the UMBC Interactive Robotics and Language Lab.
And it's an
She
embarrassing
did her
background
PhD
too.
in
Testing.
Washington
Testing.
and has done a lot of really excellent Cynthia, that we can hear you. Language, not just for robotics, for behavioral collaboration, publishes both in classical AI as well as modern machine learning techniques, and has a wonderful talk prepared for us. So without further ado, go ahead, Cynthia. Thanks so much.
Testing. All right, you can hear me and see my slides and everything?
Language, not just for robotics, but for behavioral collaboration. I see your slides. It looks like it might be sharing like a second monitor or
Sorry,
something.
you've got a terrible. Okay, let me try that again.
So without further ado, go ahead, Cynthia. Thanks so much.
Testing. All right, you can hear me and see my slides and everything?
Language, not just for robotics, but for behavioral collaboration. You're still just seeing like a monitor. It might be sharing like a second monitor or
Sorry,
something.
you've got a terrible. Okay, let me try that again. All right, you can hear me and see my slides and everything? I see. And it's an embarrassing
Seeing like a
background
monitor,
too.
it might be sharing like a second monitor or
Sorry,
something.
you've got a terrible. Okay, let me try that again. All right, you can hear me and see my slides and everything? I see.
Yeah, we're still just seeing like a space.
And it's an embarrassing
Seeing like a
background
monitor,
too.
it might be sharing like a second monitor.
Share.
They're suggesting there's
I see.
yeah, we're still just seeing like a
I'm
space.
sorry, you've got a terrible echo. Could you say that again? And it's an embarrassing
Seeing like a
background
monitor,
too.
it might be sharing like a
Share. Right.
they're suggesting there's
The only options I'm seeing for sharing are sharing desktops. I see.
yeah, we're still just seeing like a
I'm
space.
sorry, you've got a terrible echo. Could you say that again? And it's an embarrassing background too. Right.
They're suggesting there's
The only options I'm seeing for sharing are sharing desktops. I see.
yeah, we're still just seeing like a
I'm
space.
sorry, you've got a terrible echo. Could you say that again? And it's an embarrassing background too. Right.
They're suggesting there's
The only options I'm seeing for sharing are sharing desktops. I see.
yeah, we're still just seeing like a
I'm
space.
sorry, you've got a terrible. Should I send you my slides, maybe? And it's an embarrassing background.
They're suggesting there's this suggestion, I guess, was in Teams when you were sharing to share just the specific PowerPoint or Keynote window rather than the
Should I
desktop.
send you my slides?
Right. Possible if you see that on your side.
The only options I'm seeing for sharing are sharing desktops.
They're suggesting there's this suggestion, I guess, was in Teams when you were sharing to share just the specific PowerPoint or Keynote window rather than the
Should I send
desktop.
you my slides?
Right. Possible if you see that on your side.
The only options I'm seeing for sharing are sharing desktops.
They're suggesting this suggestion, I guess, was in Teams when you were sharing to share just the specific PowerPoint or Keynote window rather than the desktop.
Right.
Possible if you see that on your side.
The only options I'm seeing for sharing are sharing desktops.
They're suggesting
Should I send you my slides, maybe?
when you were sharing to share just the specific PowerPoint or Keynote window rather than the desktop.
Right.
Possible if you see that on your side.
The only options I'm seeing for sharing are sharing desktops. Should I send you my slides, maybe?
When you were sharing to share just the specific PowerPoint or Keynote window rather than the desktop. Presentation over to the. Possible if you see that on your side.
The only options I'm seeing for sharing are sharing desktops. Should I send you my slides, maybe?
When you were sharing to share just the specific PowerPoint or Keynote window rather than the desktop. Presentation over to the. Possible if you see that on your side.
The only options I'm seeing for sharing are sharing desktops. Purple. Should I send you my slides, maybe? Are you seeing slides changing?
Presentation over to the.
The only option. Maybe I should send you my slides. Purple. Should I send you my slides, maybe? Are you seeing slides changing?
Presentation over to the.
The only option. Maybe I should send you my slides. Should I send you my slides, maybe? Are you seeing slides changing?
Presentation over to the.
Is that working? Maybe I should send you my slides.
So we see your desktop,
Should I send you my
and
slides?
that.
Are you
Oh,
seeing
perhaps this is
slides
the first
changing?
slide I see. It looks like sort of a gradient of colors from purple to blue. Presentation over diagonally.
From purple to blue. Is that working? Are you seeing slides changing?
So we see your desktop, and that. Oh, perhaps this is the first slide I see.
Does that
It
help?
looks like sort of a gradient.
Maybe I
of
should
colors
send you my
from purple
slides?
to blue. Presentation over diagonally.
From purple to blue. Is that working? Are you seeing slides changing?
So we see your desktop,
Okay, I'm showing a
Oh,
single.
You briefly saw white.
Maybe I should send you my slides?
If she has two monitors, she should drag the presentation to the other monitor.
Is that working? Are you seeing slides changing?
So we see your desktop,
Okay.
yeah, because we see one of your monitors. Is it possible to drag
Share
the presentation to the other monitor?
The
If she has two
desktop, but it
monitors, she
doesn't
should
show
drag the
the
presentation to the
interesting
other monitor.
slides section, and I'm not sure how to get
Are you seeing
that.
slides changing?
So we see your desktop,
Okay.
yeah, because we see one of your monitors. Is it possible to drag
Share
the presentation to the other monitor?
The
If she has two
desktop, but it
monitors, she
doesn't
should
show
drag the
the
presentation to the
Interesting
other monitor.
slides section, and I'm not sure how to
Are
get
you seeing
that.
slides changing?
Did that help?
See your desktop,
Okay.
yeah, because we see one of your monitors. Is it possible to drag
Share
the presentation to the other
That's
monitor?
what I did.
The
If she has two
desktop, but it
monitors, she
doesn't
should
show
drag the
the
Yeah, I
presentation
think
to the
interesting
other monitor.
slides section, and I'm not sure.
Okay, I'm showing a single desktop. Did that help? Are you seeing the slides on it?
Okay.
Yeah, we see, yeah, we're just seeing kind of the space desktop background.
That's what I did.
All right.
Yeah, I think interesting slides section, and I'm not sure.
Okay, I'm showing a single desktop.
Did that
So
help?
there's a
Are you
share
seeing
tray
the
and it
slides on it?
shows the desktop, but it doesn't show
Yeah, we're
the
just seeing kind of the
slides
space
option,
desktop
and I'm not
background.
sure how to get that.
All right. Yeah, I think interesting slides section, and I'm not sure.
Okay, I'm showing a single desktop.
Did
So
that help?
there's a
Are you
share
seeing
tray
the
and it
slides on it?
Send the
shows
slides to you.
the desktop, but it doesn't show
Yeah,
the
we're just seeing kind of the
slides
space
option,
desktop
and I'm not
background.
sure how to get that.
All right.
Yeah.
Yeah, interesting slides.
We could try switching you, Cynthia, with
Single desktop. So there's a
one
share
of the next
tray
speakers,
and it shows
and you could maybe email your
the
slides to
desktop, but it
Nico.
doesn't show the
Yeah, I think that's a good idea.
slides option, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go. We could try switching you, Cynthia, with
Okay.
10:30.
So there's a
One of
share
the next
tray
speakers, and you could maybe email your slides
All right,
to
my apologies.
Nico.
Doesn't show the
Yeah, I think that's a good idea.
slides option, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go. We could try switching you, Cynthia, with
Okay.
10:30.
So there's a
One
share
of the next
tray
speakers, and you could maybe email your slides
All right,
to
my apologies.
Nico.
Doesn't show the
Yeah, I think that's a good idea.
slides option, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go. We could try switching you, Cynthia, with
Okay.
10:30.
So there's a
One of the
share
next
tray
speakers, and you could maybe email your slides
All right,
to
my apologies.
Nico.
Doesn't show the
Yeah, I think that's a good idea.
slides option, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go. We could try switching you, Cynthia, with
Okay.
10:30.
So there's a
One
share
of the next
tray
speakers, and you could maybe email your slides
All right,
to
my apologies.
Nico.
Doesn't show the
Yeah, I think that's a good idea.
slides option, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go. We could try switching you, Cynthia, with
Okay.
10:30.
So there's a
One of the
share
next
tray
speakers, and you could maybe email your slides
All right,
to
my apologies.
Nico.
Doesn't show the
Yeah, I think that's a good idea.
slides option, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go. We could try switching you, Cynthia, with
Okay.
10:30.
So there's a
One
share
of the next
tray
speakers, and you could maybe email your slides.
All right, my apologies. Yeah, I think it's a good idea. Slides, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go with that. Switching you, Cynthia, with
Okay.
10:30. One of the next speakers, and you could maybe email your slides.
All right, my apologies. Yeah, I think it's a good idea. Slides, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go with that. Switching you, Cynthia, with
Okay.
10:30. One of the next speakers, and you could maybe email your slides.
All right, my apologies. Yeah, I think it's a good idea. Slides, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go with that. Switching you, Cynthia, with
Okay.
10:30. One of the next speakers, and you could maybe email your slides.
All right, my apologies. Yeah, I think it's a good idea. Slides, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go with that. Switching you, Cynthia, with
Okay.
10:30. One of the next speakers, and you could maybe email your slides.
All right, my apologies. Yeah, I think it's a good idea. Slides, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
And then we'll have you go with that. Switching you, Cynthia, with
Okay.
10:30. One of the next speakers, and you could maybe email your slides.
All right, my apologies. Yeah, I think it's a good idea. Slides, and I'm not sure how to get that.
So why don't we try that? Yeah.
Okay.
I have this video and
Switching you, Cynthia,
introduce
with
some of the research that I have done related with XR.
All right, my apologies.
So today
Good idea.
I'd like to introduce two examples of interactive framework that I use XR as a tool to acquire human intuition, introduce some of the experience for designing shared collaboration related with XR.
All right, my apologies.
And before I started, I would like to introduce two examples, some of the research topics that interactive framework where we have four main research topics. The first one is intuition, tactics, and collaboration experience. It's design focusing on shared collaboration related with. And recently we are trying to. And before I started this research, I would like to introduce how to include and introduce autonomy where we have four main tools. Okay. And the second topic is soft actuator and wearable design focusing on. We have been working on developing and recently muscle-like and industry actuators. We named it twist actuator. How to and by using this we can design soft, wearable, high-power exoskeleton. And the second topic is soft actuator, construction labor, and industry. We have been working on developing. And the third topic is muscle-like pipeline. We are recently working on soft robots for the application by using this. Disaster response and also medical exoskeleton. And the final topic is this is more like a hardware process industry, but not totally related. And the third topic is autonomous vehicles. So whenever myself, software students have full application free time after done three of the disaster response, we also medical injury, making autonomous vehicles. And the final topic is this is more than 10 years of hobby. We finally won the third topic autonomous vehicles position. Whenever myself, software 2019 full application but this hobby project now getting more serious. So you think, okay, make it autonomous and the final topic is totally under 10 years of topic. But finally won the main theme of our research is robot X interactive system. Here X means can be a robot, but this hobby project now getting more. So we are doing some research. So you think, okay, make it autonomous and the final topic interaction robotic arm totally under 10 years of. That's the reason why we named our land. The main theme of our research is robot X interactive system. Here X means okay, so let's get the robot discussion. We are doing some research. I've been doing many years and the final interaction robotic arm totally under 10 years of. So the reason why we named the result of our collaboration with German Aerospace Center, the guy who's wearing HA Okay, so let's get to robot control your remote robot. His name is Jody. I've been doing many years and he can see what robots see through the HMD and the camera, and he can feel what robot want to do. And this is one of the series of the tasks that astronauts in the International Space Station uncovering many drilling tasks, and he can see what robots see, which operation and the camera, and he can feel what robot. Two robot manipulator human interface, and this is one of the robot located in one location that was actual communication of the International Space Satellite. So there's actual satellite drilling about 500. You can see what robots see. So even under 500 millisecond time varying communication delay, the operator can successfully manage the voltage actual communication of the International Space Satellite. So there's one, the hand of the robot, as you can see, was too big. So he was not able to see the head of the whole delay, so he was occluded. The same he could manage both successfully, and there was a feelings of clicking on the haptic feedback. There was one with the help of haptic feedback, he was able to, the hand of the robot manage this both. So we believe he was not able to see close to human, like still like a telemanipulation, he could manage the telemanipulation. And there was but still it was direct haptic feedback. So if you have it, if you are in the you may know what I mean. So directly, it was not human need to provide close to human, like still like telemanipulation. Human always need to command, and it requires a high cognitive workload. So if you have it, if you are in the, and also it risky has operation application to train the operator only. One of the examples for nuclear operator, they need over 200 hours operate training time, but only 50% has to take training because it's really difficult. So this is our justification for train the operator only. If you want to introduce robotics for nuclear carrier, then you have to pay for your robot 200 hours, even more training time, but only 50% has to take training. So the question is how to relieve operators' cognitive workload and lower down the barrier to operating only. If you want to introduce a nuclear carrier, then you have to pay for, and I found very interesting also, even more training. Neuroscientists study the human relieve operators' cognitive workload and lower down the barrier of obstacles. You want to introduce a human brain can consciously no more than, and I found very interesting also, even more training. Neuroscientists that actually explains quite well why the 6 or 7 dogs and remote manipulator operation is extremely challenging and difficult. Because human operator need to understand and see the status of remote operator through the visual feedback, health feedback, and provide proper commands. But it's extremely challenging. The degree of freedom is more than 2.5. Maybe 2.5 is because human operator need to understand and driving the status of remote operator through the visual feedback, health feedback, and provide proper commands. But it's extremely challenging. The degree of freedom is more than 2.5. Maybe 2.5 is we can constrain human operator to we only ask human to control less than 3 degrees and rest of the degree of freedom and provide proper commands. Let autonomy take or something for autonomy. That's one possibility. Maybe 2.5 we can constrain or the other way. Human only ask only high level human do only high level and rest which require low cognitive workload and even allow some mistake or some errors and rest of the fine motion and detailed motion done by autonomy. Human only ask only high level so we call this shared collaboration which require share the burden cognitive process and even allow some mistake. Maybe you have a question that how can we design this autonomy? So recently we have studied and introduced a few interactive frameworks for distributing shared substitution. And XR has been used as a tool to acquire human intuition. You have given us how can we designing this autonomy and distributing this autonomy. So there are two examples, and I want to introduce the interactive framework for distributing shared. First, virtual texture. And XR, if you are in area, then you may know what is called designing this autonomy. So virtual texture is a tool to demonstration. There are two examples and three situations on a workspace in order to improve human performance. So imagine that you need to draw a straight line if you are on the paper, but without any, using any other tool, straight autonomy. So virtual texture drawing a straight line, so that's not that easy. But if you use ruler on a workspace in order to improve human straight line, so imagine that you need to draw a straight line if you are on the paper, but without virtual texture, so this is really a design tool to improve overall operating performance. But most of the researchers see that virtual texture is predefined and given straight line. But this is not true. In unstructured environment and unknown environment, especially for collaboration, virtual texture is not easy to predefine virtual texture. It's mostly unknown and not defined in fact. Most of the researchers see that virtual texture. So we proposed interactive framework for designing the virtual texture environment and acquiring some human experience and virtual texture is not easy to predefine. So look at this mostly unknown and not defined in fact. Most of the researchers. So if you look at this example, interactive framework. Actually, when humans look at one task and understand what tasks need to be done, then human can easily tell what kind of virtual texture is necessary and required and benefit for accomplishing this task. For example, this kind of virtual task. If you look at this example, what kind of virtual texture do you think? Actually, when humans look at one task and understand what tasks need to be done, then human can easily tell what kind of virtual texture. You may think, okay, the benefit of this task. For example, axis of the virtual task. If you look at those examples, axes are aligned, then that will be really beneficial and provide virtual guidance. It would be really nice to accomplish this task and it would be very easy. So, okay, but without this, it's extremely challenging. Even in telephone, especially in telephone. The axis of the virtual task. Nowadays, there are a lot of computer vision and provide virtual guidance. It would be really nice to features this task and even be very easy. So, okay, but without this information as well. So, what if we, especially use those tools, now they help humans to design those virtual pictures. Okay, so for example, when humans, this is the my mouse pointer, for example, operator mouse pointer. If operator move my mouse pointer to the place that he is interested in, then we can list out so several geometrical humans. This is the my mouse cylinder, circle, surface, whatever. If computer vision move my mouse pointer, and human knows what object, what place that he is interested in, then we can simply confirm. Okay, I want to list out. And once we select cylinder, then there are a lot of geometrical properties, whatever. If computer vision move my center point and human knows surface, area, whatever, a lot of information. Then those information also displayed as a pull-down. And once we select cylinder, then we select axis. Okay, those are the primitive geometrical primitive information. Point and human knows surface. Then we need another a lot of information needs to be defined. Then those information also displayed as a pull-down. And select. Once we select the feature from the select tool, axis we select. Those are the primitive geometrical primitive information. Again, point and human center axis. Then we need another. Then two geometrical primitives are selected. Then possible geometrical constraints also highlight or listed axis. For example, a line, coincidence, offset, main to axis. It's like a CAD program. CAD program. This is exactly the same as CAD. Possible geometrical constraints also highlight. Once we define the geometrical constraints, for example, point line, then virtual fixture is done. Main to axis design. With 1, 2, 3, 4, 5 mouse click, virtual fixture. This is exactly the same, which based on the human intuition and what the human wants to do. I think that's very easy. So that's the interactive framework that we propose. And in order to realize this, we design intuit 1, 2, 3, 4, 5 mouse click, virtual fixture, my mouse point, which you can see based on the human intuition and what the human wants to do. That means computer vision will be running behind. So that's the interactive framework that we propose. And in order to realize this, we design simply 1, 2, 3, 4, click, 5 mouse click, virtual fixture, my mouse point, which you can see based on the. And this is done by computer vision is not running behind. That's the interactive framework. So if someone knowledge and experience in computer vision simply we can do much better. And once the feature is defined, and this is, we can select geometrical properties like the center point, center axis, and I cannot read it. And we select ellipse here, and center axis, and automatically the tool geometry is displayed, and we define the geometrical constraint. Then virtual fixture is designed. So that's the way how it works. Very simple. And we have done human subjective study to test the performance. So two conditions are used: direct teleoperation. We compare this method with direct teleoperation, and teleoperation with virtual fixture generation. 8 participants tried. Each participant tried 5 trials per condition, and each trial single peggyhole test with 4 different inclined angles. So there are many different peggyhole with different inclined angle. And each 2 trials, direct and virtual fixture generation, we start from same pose, but every group of trials start from different pose to prevent the learning effect. And we compare the performance with execution time and virtual fixture generation time and NASA TLX. So the average task execution time is drastically reduced compared to direct teleoperation. This is maybe a little obvious because there is virtual fixture guidance, so it's much easier to accomplish the task. So the task execution time is drastically reduced, maybe the half, compared to the direct teleoperation. And if you look at the NASA TLX, the workload also drastically reduced. And maybe also obvious compared to the direct teleoperation, virtual fixture generation based assisted teleoperation drastically reduced the computation time. And interesting thing is average virtual fixture generation time, teaching time is about 3 seconds. So very short, very short. It's ignorable. And we have expanded this idea to different tasks. For example, not screwing task. Yes, not screwing. But why not screwing is that the center axis has to be aligned. Otherwise, it's really difficult to push this. And also cable laying. So when we are laying down the cable, robot have to follow certain contour trajectory. And bell turning. This bell turning. It looks like easy, but especially when you are using gripper and grasp valve and turning the valve, is extremely difficult actually to accomplish that with teleoperation because you have to follow certain contour. Otherwise, this geometrical constraint apply big force and torque to manipulate. So you can easily make robot stop. And pipe sawing task is also very challenging because you have to always maintain certain configuration. Otherwise, it apply big torque to the robot manipulate. And constraint peggyhole, this is what I have already explained. And this is the experimental result, how it works. This is the virtual fixture generated by human operator, and how it help human to accomplish the task. Okay, so I believe that gives you an idea how it works. And not the toy problem, we want to implement this idea to real problem. So with a collaboration with Korea Nuclear Research Institute, we have developed a nuclear plant maintenance system. There's very interesting and challenging issue in nuclear plants. For example, this is the emergency valve. So when the fuel exchange valve of heavy water reactor malfunctioned, then we need to do some emergency valve operation. But this emergency valve is located 10 meter high, with down, facing downward. So it's extremely challenging to turning this valve. And not only single valve there's two valves. So we have to turn two valves at the same time. So really challenging. So we developed a tele-manipulation system, two KUKA manipulator installed on top of the 10-meter flexible boom, and we lift it up and manipulate these two KUKA manipulator. Each of the manipulator insert a tool and rotate the valve. But this is, without the help of virtual fixture, it's impossible to accomplish this task. So as you can see, the video stream and the camera is not that clear and a little blurry, but human can successfully design virtual fixture and manage this operation. That's one example, and I want to move on to the second example of interactive framework. In teleoperation, this is object manipulation task. So of course, object manipulation task is difficult, but if you have an experience in teleoperation, then you may know, okay, approaching to the target is even more difficult and take even longer time. Once you get to the target point, then pushing the button or putting a peg in a hole can be done maybe quickly. But approaching to the target, especially there are a lot of obstacles. It's even take much longer cognitive workload and take much longer time. Many cases, local planning algorithm can do better job in fine motion and collision avoidance. But for cluttered environment, if there is many obstacles, that's most of the case, then planner often fail to find a path. Even this looks very trivial to human. Cannot be done. So we started to think, can we combine this? Can we combine human intention and intuition for planning? I think that's our motivation, because when humans look at the environment, that's also quite straightforward and easy to tell what kind of passage and trajectory is optimal for the robot. So for example, so this is our initial approach, very first idea. For example, if you want to send the mobile robot to some of the location over there, avoiding obstacle, then you can use direct teleoperation, and also we can use path planning algorithm to send the robot to a certain point. But when humans look at this, then okay, everyone can tell, okay, this might be the optimal trajectory to reach the target. So what if we provide an interface for human to teach that? So we thought, what if humans simply sketch on top of the image, video feed, simply sketch a line, and planner use this information to plan a trajectory. That's our initial idea. Very simple idea. So we made a very simple sketch-based trajectory planning interface. So as you can see, so this is the image that human see, and we make an interface that human can sketch on top of the image, based on the assumption that the environment is flat. First. Then planner use this information to plan trajectory, and robot use this as an initial information or reference information to plan a trajectory and follow this. Of course, robot doesn't need to follow exact path of this trajectory given by a human. At any time, human can intervene to modify the trajectory. And we compare evaluate the performance, comparing direct teleoperation and also, conventional planar-based approach, while changing the complexity of the environment. So with a simple environment, there's no advantage, actually. Even direct teleoperation or RRT-based, autonomy-based manipulation approach show much faster task completion time. So shared autonomy-based manipulation doesn't show advantage at all. But as we increase the complexity of the environment, I don't think this is a complex environment at all. But anyway, if we increase the complexity of the environment, then it starts to show the advantage. Direct teleoperation and autonomy-based approach, RT-based approach, shows much longer task completion time, but the shared autonomy-based approach starts to show advantage and complete the task even much faster, even including path sketch time, because sketching path doesn't take a long time. It's less than a second, 0.some second. And we extend this approach to more realistic situation in order to control, manipulate in cluttered environment. And we design the human interface and some of the human intention and intuition acquiring and interpreting algorithms. So again, nowadays we have a lot of sensors available out there to scan environment and build a virtual world. So imagine that we have a camera, laser scanner, a lot of sensor, and we scan environment and build a virtual world, digital twin, and ask the human to explore in this environment. For example, draw a sketch or virtually manipulate the virtual robot in the environment and draw a line or sketch or trajectory. In this case, we don't need to build a virtual world, and the virtual world doesn't need to be precise. And we even allow collision and mistake because we are not going to use this trajectory and information as it is. This information is simply going to be used as a tool to acquire human intuition and intention. We are not going to use this trajectory as it is. For example, we draw a line, then we are going to use it. So that we call intention input interface and intention interpreter. So for example, say we draw a line, and if you have an experience on planning algorithm like RRT or A-star, whatever planning algorithm, mainly nowadays a lot of people use sampling-based planning algorithm. And if you want to use this planning algorithm, anyway you need to tune some parameters in the planner. And it depends on the environment. So by fixing one parameter, you cannot actually find a solution for all environment. You have to anyway tune it. For example, bias search region is very important to reduce computation time and also prevent planner fall into local minimum. And sampling length and collision margin is also very important parameters. If you increase the sampling margin, then planner can expand fast and search fast, but if you have longer than certain lengths, you cannot find a solution in the cluttered environment. So you have to tune it. And collision margin as well. If you increase the collision margin, then you can get the collision-free, safe trajectory. But if you set the collision margin bigger than certain value, then planner cannot find a solution in cluttered environment. So you have to tune it. You have to tune it. And our motivation idea is, when humans sketch path, and we can get some of the very important human intuition and information from this sketch to automatically tune these parameters. For example, sketched region can be used as a biased search region because this is the area that human believe there will be a solution. So we can use sketch path as a biased search region. And sketch speed can be used as a sampling length. When humans sketch in the virtual world fast, that means human believe this area has low probability of collision. So we can increase the sampling length. But if humans slow down the speed, sketching speed, that means there is some probability of collision. So we need to slow down, and sampling lengths need to be adjusted. And collision margin, if human grasp the stylus or tool for sketch strongly, that means human wants to be careful. So we need to reduce the collision margin because it's a closed environment. And gently, slightly, then we can increase the collision margin because there is no probability of collision. So like this. So this is only one simple case. So we can acquire and get a lot of human intention and intuition and use this for planner, tuning the planning parameter, important planning parameters. This is one example for RLT. So this is the planned sketch path. And the distance between two red point means the sketch speed. So if the distance is large, then we can increase sampling length, sketch length. And distance is short, then we have to reduce the sampling length because there is a probability of collision because humans slow down the sketch speed. So by using this information, we can tune past planning parameter for RLT, for example, and any other planner, we can actually find corresponding value. And with small amount of tree expansion, we can quickly and effectively find the solution. That's our approach. And we have tested it more realistic environment and more complicated environment. We introduced 3 scenarios, which is narrow passage planning task with manipulator. So the gray one is the initial pose and green one is the final pose. It looks trivial here for human, but for planner, not that trivial actually. So following this contour and take it out and put it in here. And this one looks straightforward. One space to another space, move through the corridor. It looks like a trivial, but this is not actually trivial for state-of-the-art planner. We compare the performance with many different approach, configuration-based input approach, path-based input approach, virtual collaboration, which is our approach, based input approach, and RLT stop, which is one of the state-of-the-art that we can try, and direct collaboration. And of course, there is some, prior approach, try to acquire human intention for planning, for planning a trajectory. Those two are, those approaches, configuration and path-based approach. Configuration-based approach means in configuration space, if human put several buyer point. And path-based approach means in configuration space again, human sketch several lines. But the main difference of our approach and their approach is their approach need to follow this buyer point and need to follow this trajectory. But our case, we actually do not use this trajectory as it is. We simply use this trajectory to acquire human intention and intuition. That's the main difference. And first scenario, second scenario, and third scenario, our approach shows the best performance completion time. And interestingly, scenario 3, the configuration-based approach, 90% fail. And even state-of-the-art RLT star, planning algorithm cannot find the solution. 100% fail. 100% fails. Right. So that's end of my presentation. In summary, I introduced in this presentation 2 examples of interactive method for distributing and designing shared autonomy. First one is interactive virtual fixture generation method. And the second one is human sketch-based path planning method. And in this presentation, I simply use XR as a tool to intuitively and effectively acquire human intended behavior from the autonomy. So, answer your question.
Much for the presentation. Great talk. So, any question from the audience? Yes.
Good question. So why did configuration based waypoints just not accesses as such as I'm assuming the waypoints are coming from an expert, so they would give an optimal solution.
All right, good question. So even though this waypoint given by the export, but the reconstructed environment is not accurate. It's not accurate, and human can, also make a mistake. So that's the reason.
Able to discern the pitch on like a screw. Essentially, you have the stage of transition. Is that something y'all looked into?
This is also a very good question. So we actually haven't tried to find this pitch.
Okay.
Yeah, but yeah, absolutely. As long as we have precise enough camera and precise enough sensor, why not? We can do that. Yeah.
Thank you. One critical point is the vehicle training. How virtual reality and the reality can make this training.
Mm-hmm. Yeah.
What is your opinion?
Yeah, good point. So all the approach that I proposed is intended to reduce this training time. So without this, support, without this virtual reality or XR support, and this interactive framework, pure direct teleoperation takes a lot of training time and really difficult and challenge to accomplish certain tasks. So all the approach that I propose is intended to reduce this training time. It's a bit short period of training time. We want to make operator who are novice can accomplish certain tasks. So that's still open question. So one by one, I'm trying to introduce. So there are a lot of issues, still many open questions.
I actually have one question. Great talk, thank you so much. So regarding the virtual fixture, is the local virtual fixture mean that the follower robot is restricted, or the operator would also feel the forces of the virtual?
Okay, that's one topic that we are working on. So this is also a very good question. So we don't know yet what is good. Okay, so for example, we can render virtual fixture in local site because we have information, and we can render virtual fixture in remote site. That's another approach. There is advantage and disadvantage. If we render virtual fixture in local site, then human feel the force without any delay, and we can increase the stiffness. So that's the advantage. But there is a situation that the alignment is, little distorted. In that case, the virtual fixture provide wrong, is not perfectly aligned with the real environment. Then it gives an error. And then on the other case, if we render virtual fixture in remote site, then we can use sensor information. So we can provide accurate force information to the operator, but there is communication delay. So there is a limitation to increase the stiffness, and stability become an issue. So there's an advantage and disadvantage, and people said, didn't actually talk about that much. Which one is better? So that's one topic that we want to work on. Yeah.
Great talk. Thank you so much.
Thank you.
So at this time, we go for a coffee break, and we'll be back in 15 minutes.
Yeah, now we have.
I wonder you guys
hear
have
you.
any activity ethics?
I don't know if there's any talks in this or any of the poster
But I
presentations are to do with
This year we didn't have it.
but last year I thought we did.
Last year we did.
Yeah, I think I figured out what's going on.
Yeah. Because one of the important ingredient, also component.
That's why we have you.
Yeah,
Yes, exactly.
I'm the only one.
we had invited, but we didn't get confirmations from other speakers.
Okay. The last day of the conference, not everybody. Yeah, thank you so much. Great talk, and thanks for everything.
You have your panel.
See if we can work this into
Yes, I just wrote her.
So I said to her that we can test with her if she can still
Yeah,
manage
that's right.
to, if she can still manage to. Yeah.
Yes.
Okay,
Cynthia,
great.
you
And you
can
can hear me
probably
okay?
hear us talking about that.
I can hear you. Can you hear me?
I don't have my, we're about to get Nikhil's laptop set up and we can then
But
do
I
the
think,
usual dance. Oh, now I already see your slides. Great, that's great.
yeah, I think I figured out what's going on.
Yeah, perfect.
All right, it's a good start.
Or since we're running a bit behind.
Yeah.
Or
Can't hear me.
going through one
You
of
hear me
these
now?
from the Mr. Cox back at like no questions, save questions for some really high initial thing.
For
Okay, testing,
But,
testing.
yeah.
Yeah. Like we have some buffer
Testing.
for the fun discussion. I put an hour and 10 minutes,
Okay.
and then also maybe we can.
Looks good from our side.
The other issue that is we want to get.
Okay, great. And you can hear me okay?
Like the session so that people can
Okay,
take the lunch
can you
break
hear me?
more or less in the same time.
Yes, yes.
So that's a problem is like that buffer for the panel doesn't come till later.
Yeah, come. Yeah, right. Now the thing is with there are online presentations. So should I? But I've already joined, so
Yeah. No, but we have
All right,
Cynthia's
I'm
slides.
yes.
Maybe
It's all
you
working.
So
Talk.
I should.
I can't hear you though, Cynthia, so because
can't hear-
it is.
Can you hear me now?
We still have the problem of the
All right, can you hear me?
microphones and speaker muting.
Okay. Okay, testing, testing. Okay, great. And you can see my slides? Testing, okay.
Yeah.
Are you seeing slides now?
Yeah, no, I think you can do that. The only thing is the online presenters don't get a chance to discuss.
Okay, can you hear me? Are they changing now?
True.
Okay, great.
How long is the
There are 6. Not this.
All right, phew.
is the phone?
Well,
Yeah.
Okay, sounds good.
Oh, I'm okay, no? Yeah.
Yeah.
All right.
Yeah.
Sorry,
Okay,
maybe
so-
you can't
Wait,
talk.
if you unmute, you undo speakers.
All right, can you hear me?
Now, if
Okay.
I
Do this,
Yes, we
can you
can.
still see my slides? Okay, great. Or are you seeing, and you can see my slides?
So maybe you can try changing the slides.
Okay. Are you seeing slides now?
We see the slides, but not changing.
You did before. Oh, no.
Are they changing now?
Now it's good. Now it's good. Yes.
Okay, great. All right, phew.
So we should be back in 10 minutes. Okay.
Okay, sounds good. Good. Now, if I do this, can you still see my slides? Or are you seeing me? If Hello. Hello. Okay, thanks very much for having me. There've been some great talks already this morning, so I'm going to talk about doing language-based HRI and simulation and how work in this area touches on a lot of different spaces in robotics and virtual reality generally. So the underlying motivation of a lot of our work is building robots that use language, and specifically grounded language, to interact with people. So it's important that robots that go in human-centric spaces be able to interact adaptively. And current robots aren't particularly flexible. We're still pretty bad at robots that can deal with novel or dynamic needs.
Okay, great. Well, welcome back,
My goal
everyone.
is to have robots that can
And thanks for
depend
bearing
on
with us as we've
instructions
had
and
to shift things
information
around
from the people
slightly.
around them to overcome
So
that.
now I
And as
think
you
we've
can
got
imagine,
Cynthia's
this is a pretty
slides and
multidisciplinary
connection all
problem,
working.
since it
So
needs
we'll have
robots and
Cynthia
natural
talk
language
next.
and
And again,
human
if you're just joining
interaction.
us,
And since
Cynthia
the goal
is
is specifically
associate
for robots
professor
to deal with
at
dynamic
UMBC,
environments, it
does
also
amazing
requires
work
learning.
in language,
There's a lot to say in this
AI,
space,
both
but in this
classical
talk I'm
and
going to focus on how
ML
we're starting to
and
address
robotics.
some of the data
And here to
problems
give
by
us a really
using
interesting
learning in
looking talk.
virtual
So,
reality.
Cynthia, thank you.
And the reason
Okay,
we're
thanks
doing
very much
this
for
is
having
that
me.
human spaces are
There's been
dynamic
some
with a
great
large
talks
variety
already
of
this morning,
objects,
so
actions, and tasks,
I'm going to talk about
which pretty
doing
much
language-based
guarantees that
HRI
robots
and
will always encounter
simulation
concepts they've
and
never
how
seen
work in this
before.
area touches on a
So
lot of
there's a
different
need for a
spaces in
communication
robotics
channel
and
to
virtual
allow these
reality
robots to learn
generally.
about the changing environment and its novel concepts from humans.
So the underlying
and also to allow
motivation of a
humans
lot
to
of our
communicate
work is
their
building
intents to
robots
the
that use
agents.
language, and
And
specifically
the core
grounded
idea here
language,
is
to
connecting
interact with
language
people.
to robots'
So it's
percepts and
important that
sensor
robots
inputs.
that go in human-centric
sensor
spaces
inputs
be able
can
to
refer
interact
objects
adaptively.
or actions
And
or
current
higher
robots
level
aren't
tasks.
particularly flexible.
Language is
We're
broad.
still
There's
pretty
a lot
bad
of
at robots
space
that
for
can
the
deal with
grounding of
novel or
sensed
dynamic
data.
needs. My goal is to have robots that can
So,
depend
for
on
example,
instructions
I
and
cook,
information
and I would
from the
expect to be
people around them
familiar
to
with most
overcome
of the
that.
things found in a typical
And as you
Western
can imagine,
kitchen.
this is a pretty
But here are a
multidisciplinary
whole bunch of
problem,
kitchen
since it needs
tools,
robots
most of
and
them not
natural
really
language and
that
human
out
interaction.
that I might
And
find
since the
in
goal
someone's
is specifically
kitchen
for
that I'm not
robots to
actually
deal with
familiar
dynamic
with.
environments,
And a
it
robot
also
might
requires
not be
learning.
either. They're
There's
just
a lot to say in this
atypical enough
space,
to not
but
be
in this talk, I'm going to focus on
And
how
this
we're
kind of
starting to
thing is
address
why we
some of
need
the
to
data
learn from people
problems
on
by
the fly.
using learning in virtual reality.
And here, I'm considering and testing language as an
And the reason we're
interactive,
doing this is that
collaborative
human
problem.
spaces are dynamic
That
with
is,
a
we say
large
a robot
variety of
understands
objects,
language
actions,
if it
and
does what a
tasks,
user intends.
which pretty much
And we
guarantees that
focus on the
robots will
language
always
part of
encounter
human robot
concepts they've never
interaction
seen
because it has a
before.
lot of advantages.
So there's a need for a
It's
communication
concise,
channel
it's
to allow these
intuitive,
robots
it's
to learn about the
pre-existing,
changing
and
environment
of
and
course
its
it's
novel
adaptable
concepts
to a
from
wide
humans,
variety of
and also to allow
situations.
humans to
And when I
communicate
say
their
grounded
intents to the
language here, I'm
agents.
talking specifically
And the
about
core
language
idea
that
here is
refers
connecting
to and has
language
meaning
to
in the
robots'
context
percepts,
of
its
the
sensor
physical world
inputs.
around the robot.
And those sensor inputs can refer to objects or actions
So I'm
or
going to
higher
talk
level
primarily about
tasks.
work that's intended to
Language
make
is
that
broad.
process
There's a
more
lot of space
scalable.
for the grounding of sensed
SimDerail is
data.
the whole area in robotics of learning things in
So,
simulation.
for example, I
and applying
cook,
the
and I would
learned
expect to be
models to real
familiar with most
physical
of the things
problems.
found in a
It's
typical
difficult
Western
to apply
kitchen.
for human-robot
But here are a whole
interaction
bunch of kitchen
problems
tools,
because
most
the
of
robot
them
would
not
need a
really
simulated
that out
person
there,
to learn
that I
from,
might find in
or
someone's
someone in
kitchen that I'm
virtual
not
reality.
actually familiar with.
So that's the idea.
And a
I'm going to
robot
talk
might not
about
be
using
either.
virtual reality
They're
settings
just
to accomplish
atypical
this
enough to
language
not be
learning.
pre-programmed.
background. And this kind of thing is why we need to learn from people. And one of the things I need to point out is that this work on understanding language is intensely. And here I'm considering and testing language as an interactive, collaborative problem. That is, we say a robot understands language if it does what a user intends. So, for example, if someone and we focus on the language part of human-robot interaction because it has a lot of advantages. It's concise, it's intuitive, it's pre-existing, and of course it's adaptable to a wide variety of situations. Visual sensors. And when I say grounded language here, I'm talking specifically about language that refers to and has meaning in the context of the physical world around the robot. Simulation to varying levels of accuracy. So speech is I'm going to talk primarily about work that's intended to make that process more scalable. Hard to model. Sim to real is the whole area in robotics of learning things in simulation and applying the learned models to real physical problems. In the real world, spoken language it's difficult to apply for human-robot interaction problems because the robot would need a simulated person to learn from, or someone in virtual reality. So that's the idea I'm going to talk about, using virtual reality settings to accomplish this language learning. And if we have someone interacting in a VR setting, we don't want them to be trying to enter text. And one of the things I need to point out is that this work on understanding language is intensely multimodal. And people use things like speech and gaze and gesture and body language, and robots have sensors that go beyond vision. So, for example, if someone asks for my coffee cup, temperature sensing could play a role in determining what to do. And historically, a lot of work focuses on learning grounded language from a combination of text and mostly visual sensors. But real human language is very contextual. When we're understanding language, we take a lot of factors into account. World stuff that can occur in simulation to varying levels of accuracy. So speech is very easy to capture in virtual reality, while something like temperature is very hard to model.
Why decorated places?
Here, and I particularly want to call out speech. In the real world, spoken language is a difficult problem. Even leaving aside the questions raised by back and forth dialogue, spoken language is much messier. But when we talk about deploying robots in human spaces, speech really is the modality we're envisioning. And if we have someone interacting in a VR setting, we don't want them to be trying to enter text, which is really hard in virtual reality. We want them to be able to just talk to the robot. And default automatic speech recognition isn't the answer. Not only does it fail often, but it's been widely shown to perform less well on different voices. And that includes women's voices, people who aren't native speakers of Midwestern English, people outside a fairly narrow age range, and so on. So if we don't want to deploy agents that perpetuate existing inequities in technology, we need a better approach. Different modalities of human communication. And to give an example of why we don't want to rely on speech-to-text models in our virtual setting, here's a sample spoken description we got from a worker when asked to describe this object. Hopefully you'll be able to hear it. But also from human interlocutors. And it's already difficult to collect data for human-robot interaction. Here, the worker said white decorative plate, which is relatively clear to us because we can see the object the worker is describing. However, when we put that sound file in a variety of speech-to-text API, we get an utterance that has nothing to do with the object. And that's largely because standard text-to-speech doesn't have any mechanism for taking the physical context the language is grounded in into account. It's proving to be a really effective approach to certain whereas what we really want is something where the grounding model can take both the speech itself and the sensor inputs about the object and the environment into account when trying to understand what a person is trying to convey. How can we go forward with having a virtual human interacting with the So the mechanisms that we use for learning grounded language are very flexible. We can swap in different learning approaches, different language models, and even different modalities of human communication. But that flexibility makes the approaches to learning from language very data hungry. And it's a particularly difficult kind of data because it requires not only a lot of information from robots, but also from human interlocutors. And it's already difficult to collect data for human-robot interaction. And a lot of the time you've got the difficulties of running human trials, but you also have to have a running robot that's performing consistently. For example, by training a person in robot. It's even harder if you want to collect data like speech in a variety of settings. To have a robot learn. So where do we get this much data about the world? Sensor data, but real input from people in the VR setting with it. And sim to real, that is learning and simulation, then transferring the learned models to real platforms. So it's proven to be a really effective approach to certain large data problems in robotics. It's essentially a combination. So the question here is, how can we leverage that idea in a context that has human interaction and a combination of ROS and specifically, how can we go forward with having virtual human interacting with a simulated robot in the simulator? And that's a complex but manageable task. So it's key to note that it requires building a simulator that can be used to manage the robot's behavior, simulate the sensor data that the robot is taking in, and place the person in the VR setting interacting with the robot in a virtual reality setting. Which is good, because the ultimate goal is to be able to... Broadly, our goal here is to build a simulation environment where humans and robots can engage in robotically realistic interactions. We'd like it very much if more groups could take advantage of that. And a lot of the time in HRI, the goal of simulation is to learn more about the human side of these interactions. For example, by training a person in robot use. And this is just a video. But our goal here is actually the flip of that side of that, to have a robot learn from the interactions using simulated sensor data, but real input from people in the VR setting with it, most notably including spoken language interactions. In the environment itself. And one of the things I'd like to so we built this river simulator, and the way this simulator is built, it's essentially a combination of Unity to do rendering of the environment for both the person and the robot, and a combination of ROS and Gazebo for actual robot control. So one of our design goals was to not need to write separate code for the robot in the simulator versus in reality. So it's key to note that as far as the robot is concerned, it's receiving sensor input and conducting actions. No part of the robot system knows or cares whether this is happening in a physical world or in a virtual reality using either a cave setting, which is good because the ultimate goal is to be able to go back and forth between those settings. And this makes it easier for a variety. And I should mention that we're not the only site using this simulator, and we'd like it very much if more groups could take advantage of that. So I encourage you to talk to me about that possibility. This way, the entire interaction can be performed remotely. And this is just a video of us controlling a robot in one of the hospital room settings we're working with. And if you're familiar with ROS, you can see that this is standard. In the bottom, we have the robot's sensor inputs, and the top view is from a camera placed in the environment itself. Advantages for fast. And one of the things I'd like to point out is that robotics research is expensive and difficult to conduct in a variety of settings. It's really hard to arrange to just bring a robot to, for example, a hospital room, because there are physical constraints and IRB difficulties. So one of the things I hope is that when we demonstrate that sim-based learning can be used for human-robot interaction, that it will open up areas of research that are currently difficult. But in fact, we don't necessarily. So we're working with this interface where real people can interact with virtual agents using either a cave setting or off-the-shelf commodity hardware like gaming headsets. And this makes it easier for a variety of people to engage remotely. Meanwhile, the agent is receiving simulated perceptual data that's in the middle image here, along with the person's speech and motion. So we explored a few. This way, the entire interaction can be performed remotely and then stored and replayed using different models for the robot's sensing capabilities as needed. What the robot has learned is then transferred to the real robot. And given the infrastructure of River, this kind of thing is simple to achieve. And the fact that we're doing all the simulation in Unity has significant advantages for fast prototyping. It means we're able to use a variety of sources for scenario development. It also makes it easier to do in-house development. So this scenario is the main dining hall at my institution, with a lot of individual objects that can be interacted with, like if the robot is following instructions for collecting a meal for someone. So we tested this with a user study, and here the picture on the right is a picture of the actual dining hall. So you can see the simulation is fairly detailed and very clear to the robot sensors. A robot could follow human instructions. But in fact, we don't necessarily want perfect sensor data of the kind of high-fidelity simulation. And we did find that implementing because real robots don't have perfect sensing, and we want to give the robot a fighting chance to overcome the sim-to-real gap when we try to transfer everything we've learned to physical robots. And in terms of matching. And the best way to do that is to reduce the gap by making the simulation as close to reality as possible. So we explored a few different ways of adding sensor noise, some naive approaches, and some more data-driven approaches that consist of learning from samples of real sensor data. Instruct a robot through the process of performing a task with them. And given the infrastructure of River, this kind of thing is simple to achieve. A ROS sensor effects node is built into the simulation system that reads the ROS simulation sensor measurements and filters them through the sensor effects node. And the output can be published in a way that introduces realistic sensor effects into the sensor data that the robot is receiving. On improving the simulation only where it's necessary. So we tested this with a user study in which we trained a language model on language descriptions paired with sensor data, both with and without noise, and tested to see how accurately a robot could follow human instructions in a kitchen setting, which we conducted in both virtual reality and on a physical robot. And we did find that implementing noise models improves both the robot's accuracy and people's perception of how well the robot is doing. So one of the studies in terms of performance and in terms of matching the perceived behavior of what people are referring to when they give us grounded language about objects. So broadly, the experiments we're currently running are ones in which people are asked to describe a variety of objects in the environment, then asked to instruct a robot through the process of performing a task with them.
And here
the task is packing a lunch. And when we've collected data from people doing this, the next step is to set up approximately the same setup in a physical environment. It doesn't need to be exactly the same setup. And see how well the robot can follow instructions for that task without additional training.
So here the
That physical transfer work is currently underway, and then we can iterate on improving the simulation only where it's necessary.
And it's possible to see some relationship between the head pose and the
And one of the things we're working with in this experiment is the fact that labeling the object the person is referring to is a kind of supervision that we don't want to deal with in real deployments. We need to understand from modalities like gaze and gesture what people mean when they say, for example,
so then we shift to
put the tomato in the
approach where we
basket.
try to take into account
When people are talking about a variety of objects,
so
each candidate object accumulates interest from the gaze until one
So
of the
the
studies we're doing is trying to
threshold.
understand how we can use gaze
And
and
this
head
prior
pose
makes
to
targets
understand
that
what
have been
people are
looked at in
referring to
preceding
when they
times
give
more
us
likely
grounded
to be
language
chosen.
about objects.
So it functionally smooths out the noisy gaze data that we saw previously.
And the first thing to try there,
And we
the
can use
sort
the
of
same
naive
experiments,
approach,
because
is to
everything
consider
that
a
happens
vector
in
of someone's
simulation is
head
captured,
pose and
so
how
we don't
gaze
need to rerun
pose
experiments
and how it
to
intersects with
participants or
objects.
anything.
And here we're
And
using
we can
point
see that
clouds
this
obtained
approach
from a
gives a
connection
cleaner
both
idea of
simulation
where the
and
participant is
reality,
looking.
and just
And by
asking
and
what the
large, the
angular
calculated
distances
target
between
for
that
what a person
gaze and
is
the
talking
points that
about
comprise the
overlaps pretty
objects,
well from the
where the
ground
shortest
truth.
distance is assumed to be what the person is looking at.
And the real
So here the blue bars represent ground truth,
language
the time that we know a person is
just
actively
head pose
describing
in
particular
simulation
objects.
to label the
And it's
specific
possible to
object
see
that a
some
person is
relationship
describing
between
as
the
they
head
speak.
pose and the ground truth
And
object.
evaluating that,
But this
we find that
naive
we
approach
perform
turns out to be
reasonably well
messy
on an object
because
retrieval
people in
task
simulation
virtual
or in reality
in which
move their
someone says
heads and
something
eyes
like
quite a
candy
lot
the
when they're
apple.
interacting with
And the system
someone or
has to use the
something
learned
like a
model of language
robot.
to correctly identify the task from a set of alternatives.
So then we shift to a Bayesian
And it's
approach
worth
where we
noting
try to
here
take
that
into
two
account the
objects on
previous
which we
point that's
perform
being
really
looked at.
poorly,
So
sort of
each
the apple and the
candidate
mug,
object
are
accumulates
comparatively
interest from the
smaller and
gaze
somewhere
until
in
one
the
of the
middle of the
possible
cluster of
targets reaches
objects.
some threshold.
So it's intuitively
And
more
this prior
difficult to
makes targets that have been
determine
looked at in
what's
the
being
preceding
looked at
time
from the
more
sensor data
likely
that
to
we
be
have.
chosen. So it functionally smooths out the noisy gaze data that we saw
And while that
previously.
work is relatively successful,
And we
it's
can
not
use the
quite as
same
interactive
experiments
as
because
we'd like
everything
to
that
see.
happens in
We want to know
simulation is
whether a robot
captured,
can
so we don't
engage
need to
in a more
rerun
direct
experiments with a new
interaction
set of
with the person
participants
in
or
both
anything.
virtual reality
And we can see that this
reality.
approach gives a cleaner
We're
idea
pushing
of
a
where
lot
the
of our
participant is
language-based
looking,
experiments into a
and that by and
makerspace
large the
setting,
calculated
which has
target
the
for what a
advantage
person
that
is
there are a lot
talking
of
about
different kinds of
overlaps pretty
interactions
well
and
from the ground
tasks that can
truth,
occur.
with the ground truth.
So next we consider a small-scale joining task in which a person
And
a
the real
robot are
question
working
here
together
is
to build
how
a
well
simple
can we
circuit
learn to ground
using
language
conductive
about
cutting.
objects using just head pose in simulation
And a lot
to
of
label
the
the
time in
specific
shared
object that a
manipulation
person is
tasks,
describing
we have
as
the
they
human and the
speak.
robot working in a shared
And evaluating
workspace,
that,
maybe
we find that we
doing
perform
handoff,
reasonably
but not
well on an
directly
object
working
retrieval
on the same
task in
object
virtual
at the same
reality,
time.
in which
So
someone
we're
says
exploring
something
not
like,
only
hand
how
me
well
the
our
apple,
simulated and
and the
real
system has
dyad
to use
here
the
can
learned
build the
model of
circuit,
language to
but
correctly
how well the
identify the
actual
task
virtual
from a set of
environment is
alternatives.
working. Both for
And it's worth
understanding
noting here
robots'
that the two objects on
capabilities
which we
and for how
perform
people
really
find the
poorly,
interaction.
sort of the apple and the
And
mug,
here the interaction
are
is actually
comparatively
flipped,
smaller
and
and
the
somewhere
robot
in
is
the middle
providing
of a
grounded
cluster of
instructions to the
objects.
human using
So it's
language,
intuitively more
asking for
difficult to
components
determine
and
what's
asking the
being
person
looked
to
at
move the
from the
blocks
sensor data
around,
that we have.
rather than focusing on human speech. And one of the failure modes
And
we
while that work
encountered
is
when we
relatively
piloted this
successful,
work is
it's
that
not quite as
conductive cutting is
interactive as we'd
squishy.
like to
It's a
see.
soft
We want
body,
to know whether a
which allows
robot can
simple
engage in a
virtual
more
reality
direct
and
interaction with a
extended
person
reality
in both
can't
virtual
model.
reality
In
and
Unity,
physical
everything
reality.
is rigid.
We're pushing
So
a
we
lot
have
of our
people who
language-based
held the buddy
experiments
blocks
into
too
a
close
makerspace
together,
setting,
and they would
which has the
deform
advantage
into
that
each
there are a
other
lot
and
of
short the
different kinds of
circuit.
interactions and
So now
tasks
we're
that
working
can
on building
occur.
soft body dynamics.
So next we
into
consider
rhythm,
a small-scale
because a lot of
joining
the real
task
world is
in which a
compliant
person and a robot are
non-rigid
working together
in
to build a
important
simple
ways, in
circuit
ways that
using
we
conductive
can't,
cutting.
we can't just work around.
And a lot of the time in shared manipulation tasks, we have the
So
human and the
basically
robot
what we're
working in a
testing
shared
here is first
workspace,
the
maybe
human
doing
robot
handoff,
dyad's ability
but
to
not
complete the
directly
task.
working on the
The
same
second,
objects
and
at
more
the same time.
importantly, the difference
So we're
between
exploring not
simulation
only
and
how well
reality
our
from an HRI
simulated and real
perspective,
dyad here can
both in
build the
terms of
circuit,
task completion
but how well
and
the the actual virtual environment is working, both for understanding the robot's capabilities and for how people find the interaction. And here the interaction is actually flipped, and the robot is providing grounded instruction to the human using language, was working with asking for components and asking the person to move the blocks around, rather than focusing on human speech. And one of the failure modes we encountered when we piloted this work is that conductive putty is squishy. It's a soft body, which a lot of simple virtual reality and extended reality modelers can't model. In Unity, everything is rigid. So we would have people who held the putty blocks too close together, and they would deform into each other and short the circuit. So now we're working on building soft body dynamics into River, because a lot of the real world is compliant and non-rigid in important ways, in ways that we can't just work around. So far, I've been talking about doing headset-based virtual reality.
So basically, what we're
also
testing
the idea
here
of
is
doing
first
other
the
kinds
human
of
robot
immersive
dyad's ability to
environments.
complete the task.
So what I'm showing
but
here
second,
is the
and more
pi-squared
importantly,
facility,
the
which is a
difference
partial
between
K2
simulation and
immersive
reality from an
environment
HRI perspective,
consisting of a room
both in terms
size
of
6
task
by 4
completion
curved
and in
wall
terms of
with
the
10
user's
bezel 3D
experience.
monitors, plus a motion tracking system.
And we found
computing
that broadly
cluster.
speaking, from
And
the
this is
human
useful for
perspective,
participants who
the
find
tasks were
traditional
really
head-mounted
similar,
virtual
even though
reality
one was in
less
this
than
mostly
ideal.
unfamiliar
For example,
VR
people
setting,
get the
and one
motion
was
sick.
working with an
They
actual
can actually
robot.
engage in some of the
Most
same
people
kinds of
found the physical
interactions
setting
in
more
this immersive
comfortable,
environment with
but other than
simulated
that, the
robots.
reactions of our group of 20 participants was surprisingly consistent,
Another
which
facility
hopefully
we
means
have
that the
we've been
human data
using for
we're
this
collecting in the
project
VR
is the
setting will
photogrammetry
translate well
rig,
to the
which can
physical
take
world.
pictures of someone or
So there
something
weren't major
from all
differences in
angles around it
participant comfort,
simultaneously.
understanding of the
And this lets us, with a
instructions,
little work, have
frustration with the robot, the intuitiveness of the interaction,
So the robot, when it
or
sends
how
in the
people, how
person it's
pleasant people
interacting
found
with,
the
can
interaction.
have a simulated person instead of just one of a small set of avatars. We can also
Now, in
use the
doing
rig for
all
large
this, it's
objects or
worth
for the
noting that we have a
robots
couple of
themselves and add
tools or
kinematics
really
to the models
facilities that have
constructed
helped
that
to make
way.
the simulation more effective. So far, I've been talking about doing
aside from large
headset-based
things
virtual
like people
reality,
and robots,
but there's
we're
also
also
the idea of
interested in
doing
working
other
with
kinds of
virtual
immersive
versions of
environments.
objects people might find in
So
the
what I'm
world.
showing here is the
In
pi-squared
order to talk
facility,
about
which is a
human-robot
partial
interaction,
K2
we
immersive
find that we want to
environment
deal with assets
consisting of a
found in
room
sort of
size
home
6 by 4
environments.
curved
And
wall
since we're
with thin
focusing
bezel
on a
3D
robot learning about
monitors,
them from
plus a
sensor
motion
data, we
tracking
need those
system and a
assets to be
computing
high
cluster.
quality.
And this
And
is
a lot of
useful
what's
for participants who
available in
find
virtual
traditional
reality is good
head-mounted
enough
virtual
for a human
reality
to
less than
recognize what
ideal.
it's supposed
For
to be,
example, people
but
who
not
get motion
necessarily
sick.
close enough
They
for
can
a
actually
robot to
engage in
learn a
some of the
world
same
model
kinds of
from it.
interactions using this immersive environment with simulated robots.
So we went to something called the GOLD data set, the grounded language data set.
Another facility we
about
have that we've been using for this project is a photogrammetry rig, which can take pictures of someone or something from all angles around it simultaneously. And this lets us, with a little work, have high-quality 3D models of individuals.
And
so the
we're
robot,
aiming
when
for
it's
as
sensing the
lightweight an
person it's
asset collection
interacting
process
with,
as possible.
can have a simulated
And what we
person
found
instead
is
of
that it
just
was
one of a
actually
small
easier to
set of
create models
avatars.
of random world
We can also use the rig
environments
for large
photogrammetrically,
objects or for the
using a
robots
cell phone
themselves
camera
and add
scanning an
kinematics to the
object.
models
And
constructed
this is
that
the
way.
sort of task a physical robot can do with objects in its environment.
And aside from large things like people and robots,
And in
we're
addition to
also
having
interested in
models
working with
suitable for
virtual
using in
versions
virtual
of the
reality,
objects people might
one of the
find in
goals
the
of this
world.
work is actually to
In order
determine
to
whether
talk
we can
about
label
human-robot
objects using
interaction,
large
we
vision
find
and
that we want
language
to deal with
models,
assets
such
found
as
in
Clip
sort of
from
home
OpenAI.
environments.
So that we
And
can
since we're
explore how
focusing
people
on a
give
robot learning
instructions
about them from
objects
sensor
without
data, we
starting
need
with
those
having
assets
people
to be
label
high
them.
quality.
And the
And a lot of
baseline
what's
answer is you
available
can
in virtual
definitely make a
reality
good
is good
start
enough
this
for a
way,
human to
although it
recognize
depends
what it's
heavily on the
supposed to be,
object.
but not
But in
necessarily
particular,
close
since
enough for a
robots may
robot
see
to
objects
learn a
from
world
these sort of
model from it.
atypical angles, like this banana scene end on.
So we went to
We're
something called the
exploring how well
GOLD
these
data set,
models
the
can
grounded
handle
language
object
data set,
identification
which
from
is
a
about
variety of
2.5
weird
dimensional.
angles.
It's a data set of real
And it
objects
varies a
with
great
images
deal
taken
from
from
object
many
to
angles
object,
using
but
both a
also
camera
from
and
angle to
LiDAR, so you
angle.
can do 3D
So
object
here, green means that the
reconstruction.
model
But it doesn't
successfully
contain
produced the
actual
labels that
3D
included the name
models.
of the object.
And we're
like
aiming
scan
for as
opener.
lightweight an asset
And what we
collection
see for a
process
lot
as
of objects
possible.
is that it deeply
And what we found
depends
is
on
that it was
the
actually
angle.
easier to
So we
create
can't
models
get
of
just
random
throw
world
large
environments
models at whatever the robot is
photogrammetrically
seeing and get a
using a
clear
cell phone
identification.
camera and scanning
Things
an
like
object.
labeling via
And this
gaze
is
and
the sort of
gesture
task
plus
a
language
physical
are
robot
still
can do
more
with objects
consistent
in its
net,
environment.
especially if we're talking about atypical objects or idiosyncratic
And in addition to
labels.
having models suitable for using in virtual reality, one of the
I'd
goals
also
of
like
this
to
work
note
is
that if
actually
this
to
approach to
determine whether we can
human-robot
label
interaction studies
objects
works
using
out,
large vision
it
and
has the
language
potential to
models,
broaden the
such as
accessibility
Clip
of
from
HRI
OpenAI,
research.
so that we can
And what
explore
I
how
mean by
people
that
give
is the
instructions
total
about
setup
objects
necessary
without
to do
starting
a
with having
complete
people
study
label
with a
them.
simulated robot.
And the
is a
baseline
computer and a
answer is
VR
you can
headset,
definitely make a good
which has
start
two
this way,
advantages.
although it
It's a
depends
much more
heavily on the
accessible
object.
outlay for research
But in
groups that might
particular,
not be
since
able to set
robots
up a
may
full
see
robot
objects from
lab,
these sort of
and it's a much more
atypical
portable examples, like this banana scene.
You can imagine
and
taking it out of the usual.
We're
cannabis
exploring how well
settings
these
to,
models
for
can
example,
handle
a city
object
library,
identification from
and
a
potentially
variety of
moving
weird
away from the
angles.
monoculture of experiment participants.
And it varies a great deal from object to object, but also from angle to angle. So here, green means that the model successfully produced a label that included the name of the object, like
some of the initial
Canada.
studies we've done.
And what
about
we
the
see
river
for a lot of
simulator, which I
objects
want
is
to
that it
reiterate, we'd
deeply
love to help you
depends
get
on
set
the
up and
angle.
running.
So we can't
We've got a
get
lot of
just
future
throw
work to
large
do
models at
in
whatever
that
the robot is
infrastructure.
seeing
For
and get a
example,
clear
River is built
identification.
to allow people
Things
to
like
connect
labeling
remotely
via
using
gaze
their
and
own
gesture
VR
plus
headsets,
language are still
so
a more
that,
consistent
experiment
net,
participants don't have to
especially
be
if we're
in a lab
talking
or a
about
space with
atypical
us at all.
objects or
And we'd like
idiosyncratic
to figure out
labels.
how to take advantage of the population of people with internet connections and
I'd
VR
also like to note that if this
capabilities to do
approach
larger
to
scale
human-robot
studies.
interaction studies works out, it has
Meanwhile,
the
there's a
potential to
robust
broaden the
conversation
accessibility of
happening in the
HRI
machine learning
research.
community about bias
And what I mean by that
discrimination
is the
in burned
total setup
systems.
necessary
And
to
part of what
do
we're
a
working on
complete
is
study
finding
with a
ways to collect
simulated
more
robot
broadly
is a computer and a
representative
VR
data and learn from
headset,
that data in
which has
broader
two
ways.
advantages.
In the interest
It's
of
a much
bringing
more
some of the
accessible
ideas from
outlay
those
for research
conversations
groups
into
that
the
might not be
robotics
able
and
to set up a
language
full
space.
robot lab, and it's a much more portable arrangement. You can imagine taking it out of the usual campus settings to, for example, a city library, and potentially moving away from the monoculture of experiment participants we tend to see. Is both feasible and transfers well to real robotics. So I've talked about performing HRI studies and simulations using real people in virtual reality. Some of the initial studies we've done about the river simulator, which I want to reiterate, we'd love to help you get set up and running. We've had a lot of future work to do in that infrastructure. For example, River is built to allow people to connect remotely using their own VR headsets, so that experiment participants don't have to be in a lab or a space with us at all. And we'd like to figure out how to take advantage of the population of people with internet connections and VR capabilities to do larger scale studies. Meanwhile, there's a robust conversation happening in the machine learning community about bias and discrimination in learned systems. And part of what we're working on is finding ways to collect more broadly representative data and learn from that data in broader ways, in the interest of bringing some of the ideas from those conversations into the robotics and language space. So broadly, language is a complex space that has a lot of associated components and draws on a lot of fields. But the takeaway is that doing HRI in a sim-to-real setting is both feasible and transfers well to real robotics, which means we can do a lot with less effort and less infrastructure, while addressing some of the large data problems some of us see in our problem spaces. There's a tremendous pool of And of course, all of this work was done with a large set of talented collaborators and students who get much of the credit for the work here. So I hope this has given you a bit of an overview of the work we're doing in this space, and I'd be delighted to take any questions. Thank you so much. It's only got, it has, you know, a limited number of objects in it that the robot can actually move that are manipulable. But again, a day to build a new scenario environment.
Great, thanks, Cynthia. So I think what we'll do is people will tell me questions and then I will
sort of individual objects with a lot of characteristics and things, like the dining hall setting and the makerspace setting, took on the order of a small number of weeks to set up.
Let me start off with one. One thing that I think goes happens a lot behind the scenes in some of the work like this is actually creating the virtual environments themselves.
It's not work
you showed a
that can be
few
done by,
examples, and they look highly realistic. Can you talk to us a little bit more about how are the environments themselves being created?
If you're using tools that have this. So one of the advantages of using something like Unity is there's a tremendous pool of existing sort of assets and environments and work that people have done on building things out. So the hospital scenario that I showed in the little video took us about a day to build. It's only got, it has, you know, a limited number of objects in it that the robot can actually move that are manipulable. But again, a day. We have considered to build a new scenario environment. Right now, and the scenarios that have more sort of individual objects with a lot of characteristics and things, like the dining hall setting and the makerspace setting, took on the order of a small number of weeks to set up, you know, maybe 2 weeks each. Conductive putty. So it's work that is important, that has to be done by people with a particular skill set. It's not work that can be done by, you know, just, it's not something that can be crowdsourced, for example. But it's not particularly onerous if you're not using, if you're using tools that have this sort of broad uptake and have a lot of components and things for them already. Haptic gloves. So.
Got it. Thanks. Other questions? Go ahead.
Consider time period feedback as part of the process.
So, have you considered tactile feedback as part of this process?
We have considered it. It is not trivial right now. Tactile feedback is largely vibrational rather than force-driven. And when people are doing things like working with a robot to build a circuit, the force that the robot is applying to, for example, you know, conductive putty when it's pushing an LED in, is important. But I think any haptics would be better than no haptics. The real reason we haven't pursued that more is that we've got this idea that there's, you know, many people out there with virtual reality headsets, and we'd like to be able to tap into that pool of people. There are many fewer people with things like haptic gloves. So.
There's another question over there.
We're talking about simply, one of the benefits is the cost of experiment is a lot less as we can perform how many experiments we want. And if we were to say apply that to something like learning from demonstration, is we would like the let's say the teleoperator to teleoperate something with simulated code. But in your experience, have you ever felt like people behave differently with a simulated environment? As
my work is focused on language, and the work that we're doing in the sort of language understanding, we've consistently found that people use language very consistently between the simulation setting and the real setting. We haven't seen. We have yet to identify sort of major differences. In terms of using it for something more like teleoperation, then there's a lot of HR work on using SimDrill for like learning from demonstration and teleoperating robots, how you can control a robot in this kind of safer learning setting.
The question was more
but
targeted
I think a lot of the differences that they're seeing
maybe operation
in that,
of robots.
that's
so
the
thinking about
kind
a
of
use
thing where
case
something
of
like haptics
teleoperation
becomes
for
really
data
important,
collection for doing
where interacting with the robot
for
physically
example, might we see differences in how people are operating
has
the robots?
significant differences.
Have you
but
seen
in
any
terms
sort of
language,
issues in terms of like these
like if you're using
discrepancies,
language to try to tell
and
the
how we might
robot
be able
what to
to
do, we haven't
summary?
really identified major ways in which people differ. They seem to adapt very comfortably to the different environments. So my work is focused on language, and the work that we're doing in the sort of language understanding, we've consistently found that people use language very consistently between the simulation setting and the real setting. We have yet to identify sort of major differences. In terms of using it for something more like teleoperation, then there's a lot of HR work on using SimDrill for like learning from demonstration and teleoperating robots, how you can control a robot in this kind of safer learning setting. I think a lot of the differences that they're seeing in that, that's the kind of thing where something like haptics becomes really important, where interacting with the robot physically where you has significant differences, like, but in terms of language, or, like if you're using language to try to tell the robot what to do, we haven't really identified major ways in which people differ. And they seem to adapt very comfortably to the different the wide variety of data that comes from people and from different robot sensors. There aren't yet these sort of large models that make it possible to
You're talking a lot about using
working on the individual components in kind of a meaningful way.
Language.
And
so
I would like it if there
these,
were, right? I would like it if
what's your
I could use
thoughts on
something like
some of these newer models are
to just take in a video and do all the language grounding and have it solved.
Give it images
but
as well.
right now, I don't think the data exists
some of these
to make
questions,
that
or
quite
do you think
feasible
like
for all of the different
maybe we'll have
modalities.
end-to-end learning systems for this, or do we still need to think about these explicit features that we're encoding like Gaze?
I think ultimately we will probably see end-to-end systems that are capable of taking a lot of the spaces where you have less data, like thermal imagery or depth data. So although we're working heavily on sort of multimodal learning systems, and how can we work with the wide variety of data that comes from people and from different robot sensors, there aren't yet these sort of large models that make it possible to avoid working on the individual components in kind of a meaningful way. And I would like it if there were, right? I would like it if I could use something like PBT to just take in a video and do all the language grounding and have it solved. But right now, I don't think the data exists to make that quite feasible for all of the different modalities we care about.
And I think now we're shifting to some of the short paper poster presentations. And are we having a short? We're just going to go straight into it. Yeah. Okay. We'll just go straight into it. So I think our very first author is going to be Shivam Sanwani. And did you get your slides already? Okay, perfect. And just as a general announcement, since we're running a bit behind and we don't want to run too far until lunch, we're probably going to reserve questions to be pretty minimal. especially for in-person presenters, because you can talk to them at their posters during their coffee breaks. For online presenters, since you don't have that option, we'll try to pick a few questions, but our goal is to try to get the schedule back so you can get to lunch more or less on time. So doing our best for them. Right. Yeah. Oh, and I should mention that this talk, the first 4 talks, so this talk and the 3 following talks are all being considered for an award for best posters at the conference. So if you have thoughts on this and you're very excited by some of the work that you're seeing in the first 4 talks, come chat with one of us to kind of register your vote for that work as being one of the awarded papers.
Should we are you able to? Oh, yes. Awesome.
Yeah. Hello. Yeah. Okay, let's get started. Good morning, everyone. This is Shubham Sononi from Interactive Robotics Lab at Arizona State University. And I'm very excited and well caffeinated to present our paper comparing static and dynamic signals for effective human-robot collaboration. In general setting of human-robot collaboration, we always observe that not only human communicates with the robot, but also the robot communicates their intentions through different signaling techniques. One of which could be auditory signal, where natural language can be used to communicate with the human. Another one could be motion signal, where anthropomorphic gestures can be done by a robot. Third could be visual signal, where structure light sensors or like some sort of structure light can be used to indicate robot status to the human partner. In this talk, we are primarily focused on visual signals. And the main question that we want to ask and to answer is that, does all visual signals have same effect on human-robot collaboration? To this point, our primarily contributions are mixed reality framework for signaling, their comparison of proposed visual signals, and their information theoretic analysis. Here is example of our proposed visual signals in the real life. To provide these visual signals, we leverage our prior work called intention projection. Central to this system is the stereo combination of projector and camera. This some sort of technology is used in projection mapping. So here we basically use vision-based tracking to obtain real-world information, and in tandem, projector augment this information and project it on the real world. So let's talk about the first signal that we want to propose is the static mode. It informs human partner about robot's upcoming goal. And this can be done by projecting red semicircular disc in front of the goal object. As you can see, it indicates clearly about where a robot's going to go as a static goal. Next is the dynamic mode, where we render a virtual twin of the robot and project it onto the tabletop. This indicates clearly about the planned motion of the robot and gives clear idea about robot's upcoming action. And this dynamically updates the information about robot plan in space and time. Third one is the dual mode. It's the basically combination of both static and dynamic together. So we basically get understanding of robot's goal and how it's going to go there. And no projection mode is the one which we use for the baseline to compare against proposed visual signals. So the main question here is which one of the mode is better? Static, dynamic, dual, or no projection? To test that, we propose 2 hypotheses. First one talks about task efficiency, that one of the projection mode is better than no projection mode. Second one is the cognitive load, that projection mode has the low cognitive load compared to no projection mode. Hypothesis 1 specifically talks about objective analysis. And hypothesis 2 is about
subjective analysis. To test the hypothesis, we devised generic tabletop manipulation task. And for this task, we basically created an experiment where we put 18 cubes in 6x3 grid fashion on the table, out of which 12 cubes are randomly assigned to the human and 6 cubes are randomly assigned to the robot. The information about cubes assigned to the human can be seen on the laptop display over there. Furthermore, we conducted a human subject study, which was approved by Institutional Review Board. And for the study, we found that we got like 22 participants. All of them volunteered for this task. No monetary compensation were given. And all of them performed the task with all different 4 modes in the random order. We also asked participants to fill up the NASA TLX, which we use for the subjective analysis. And also while they were performing the task, we recorded their actions through vision sensor, and post-hoc we annotated the data for human action, robot actions, and virtual stop and the static goal popping up. So those kind of time series, we annotated that, and we use it for the objective analysis. So let's talk about the results. So this results specifically talk about the hypothesis 1, and this is our objective analysis. Here we define the task efficiency as a relative finish time between robot and human. Basically, it talks about like how fast a human finish compared to the robot, and higher the relative finish time, faster the human finish before the robot. And as we can see from the left histogram, that around in dual mode, we found that across 22 participants, they finish around like 6 seconds faster than no projection mode. And also the other projection modes were like comparatively faster than no projection mode. On the right side, we have the statistical analysis. And here we see that dual mode and static mode are significantly faster than no projection mode, which supports our hypothesis 1. So this results specifically talk about the subjective analysis, where we conducted raw analysis of NASA TLX. And as we can see here on the left side, we have on average low cognitive load in the dual mode compared to other projection modes, and also no projection mode. On the statistical side, we found that dual mode and static mode are significantly have significantly low cognitive load indices compared to no projection mode. Okay, that was like subjective and objective analysis. So in addition to that, we leverage information theoretic measures, one of which is the transfer entropy. This talks about how much information is transferred from one time series to another one. As we can see here, for virtual stop to human peak and static goal to human peak, for those 2 time series, we see there is the highest transfer of information in dual mode, which basically supports our hypothesis 1. And this gives us clear understanding that without doing subjective and objective analysis, we can use information theoretic measure to like guess what would be the findings of our experiment. In addition to this, we conducted conditional entropy analysis. So this basically gives us understanding of how much uncertain one time series given another time series. And in this one, we found that how much human actions were like affected by robot actions. And as we see in no projection mode, human was more uncertain across like all the tasks performed by like human partners. And in dual mode, there was the lowest uncertainty. This tells that we can also leverage a conditional entropy to understand how much human robot collaboration has improved for different modes. So in conclusion, we found that not all visual signals are equal. What does it mean? That if we combine both static and dynamic signals together, it improves human-robot collaboration. Also, it shows that there is a highest transfer of information and lower uncertainty for human actions.
Right.
In addition to that, we developed a mixed reality-based signaling framework.
Can you hear me, Nikhil?
And along with we
I think my mic
gave a
is,
means to show that we can use
okay,
information theoretic
perfect.
methodology. Code for our implementation is at this
All
repo,
right. I
and
think there is the
feel free to
echo.
talk
I
to
think
me
it's
at the
clear
poster
now.
podium. Thank you very much.
All right. All right. Perfect.
And I think for time, we'll just save questions for the poster podium. Because there are a couple people that are online that have to go before lunch.
Perfect.
Time zone differences.
Thank you so much. Hello, everyone. I'm going to represent our short paper, Immersive Remote Teleoperation, Gaze-Driven Approach from Sampling to Rendering. This is the work I have been working on with my colleagues on team, Sarah Anastasia and Nikhil Deshpande. He's already in Detroit with you. If you have any comments or questions, if you would like to talk more, you can contact him later. So I would like to start by introducing what teleoperation
Right. Can you hear me?
Basically, starting from doing work at a distance.
Can you hear me, Nikhil?
So doing work at
I
a
think my
distance
mic
in
is,
the context
Yes,
of
we can hear you.
teleoperation
You can share the
refers to
screen.
perform tasks, operate machinery, or control equipment remotely in environments that may
All right. I think there is the echo. I think it's clear now.
like far distance for
Yeah, it looks like we can see the slides. So
to go into
next, we're going to
So,
have Jonas
the operator is not
Tepera
physically
giving
present
us
at
a
the remote
talk on
location,
teleoperation.
where the
So
work
we
has
should be able to hear you and see your
performed,
slides. So go
but
ahead whenever you're ready.
instead it uses or he or she uses robots to carry out tasks.
Thank you
from
so
a
much.
distance.
Hello, everyone.
We need to ask
I'm
if
going
there
to
are,
represent our short paper,
any
Immersive Remote
technological,
Teleoperation,
perceptual, or
Gaze-Driven
cognitive
Approach from Sampling to
when doing
Rendering.
work remotely.
This is the work I have
So
been
one of the
working
things
on with
that we
my
can see
colleagues on
is the
team,
remote
Sarah
environment
Anastasia
is
and Nikhil
assumed fully known
Deshpande.
and
He's already
unknown.
in
It's
Detroit
not
with
known.
you.
The
If you have
perception
any
is
the
incomplete,
comments or questions,
and
if
we
you would
assume
like to
that
talk
network
more,
latency
you
is
can
input.
contact him
There is a
later.
network latency and
So
input
I would like
limitations.
to start
We say
by
there is a disaster
introducing
environment,
what
so things became
teleoperation is, or
unstructured.
basically
And
starting
because of
from
this
doing
reaction
work
to change,
at a
so the
distance.
environments became
So doing
slow,
work at a
and
distance
eventually
in
it
the
affects
context of
the sense of
teleoperation
presence,
refers
and
to the
it
ability to
also
perform
invokes
tasks,
cyber
operate
secrets.
machinery, or control equipment
So
remotely in
different
environments
research has
that
been
may
working on
be
improving
inaccessible
remote
or
teleoperation, or
hazardous or
working
like far
on
distance for
certain
a
tasks
human being
remotely.
to
So
go and to
nearly
operate.
all attempts that
So
attempts that are
the
trying to
operator is
solve
not
this issue
physically
have
present
focused
at the
on
remote
either on
location
the robot or
where the work
transmission,
has
or
to
maybe
be
in
performed,
between.
but instead
So
it
instead here
uses
what we are
or
trying to
he
do
or
is
she
to
uses
focus on the
robots to
user
carry out
and then
tasks from
improve
a distance
the
side.
remote teleoperation
We need
task
to
to
ask
improve
if there are
the link between
like
transmission
any
and the robot.
technological,
So
perceptual, or
we
cognitive
used to have been working on this,
constraints when
taking
doing
inspiration
work
from the human
remotely.
visual system towards to
So
designing
one
a
of the
new
things that we can see
kind
is
of
the
control
remote
mechanism
environment
or
is
a new
assumed
data
fully known
flow
and unknown.
pipeline.
It's not
So
known.
as a human
The
in
perception
the loop,
is
we were
incomplete,
the first work that we
and
have
we
been working
assume
on
that
was to
network
study the
latency and
human
throughput.
or the
There is
operator.
a network
So
latency
that's
and throughput
physically to
limitations.
study how a
We say
human
there is a
visual
disaster
system works
environment,
in
so
the
things
visual
became
cortex, or
unstructured.
also in the brain in
And
visual
because of
cortex
this
1 or in
reaction to
the
change, so the environment
photoreceptors on the
became
retina.
slow,
If you
and
closely look
eventually
at
it
it, we
affects
see
the
high
sense of presence,
quality
and
in the
it
0
also
degree in
invokes the
eccentricity
cyber
in the
secrets.
retina. And that is
So
have a
different
huge,
research has been
let's say,
working
brain
on
size in the
improving
visual
remote
cortex 1.
teleoperation, or
And then
working
this visual quality
on certain
acutely
tasks
exposed
remotely.
across
So
the
nearly all
periphery.
attempts
So this is the
that are
first
trying
work
to
that
solve
we
this
have been
issue have
working on
focused on
to
either on the
optimize the
robot
data
or the
flow
transmission
from the
side, or
robot
maybe
to the
in between.
to the
So instead here what
teleoperator
we
or
are
the
trying to
user.
do is to focus on
So
the user
the
and then
first task that
improve
we did was like
the
we
remote
remote
teleoperation
remote
task, to
environments,
improve
and we send
the
or
link
stream
between
them to the
transmission
user.
and the
So as
robot.
you can see in the video,
So
we have a high
we
quality video
used to
that's
have been
streamed
working
and
on
it's
this,
lagging.
taking
But
inspiration from the
instead, what
human
we
visual
did was
system
we
towards to
optimized it
designing
for
a
the
new
user that's looking at.
kind of
So if
control
the
mechanism
person is
or a new
focusing on
data
a certain position,
flow
that will be high
pipeline.
quality, and then the
So
quality of
as
the
a
point
human
cloud
in the
will be
loop, we
compressed
were
or
the first work
suppressed
that we
across
have been
the
working on
peripheral
is to study the human or
However,
the operator.
doing this
So that's
systematic
basically to study
point
how
cloud
a human
sampling,
visual
it
system
it
works
also
in the visual cortex,
lose
or
or
also
miss
in the
some
brain in
important
visual cortex
information.
1, or in
As
the
you can see here, there
photoreceptors
is
on the retina.
a photograph
If you
that
closely
was
look at
attached
it,
to
we
the
see
frame
high
that's attached
quality
to the
in
wall.
the
But
0
the
degree in
person if he
eccentricity
is
in
not
the
focusing
retina,
on and that is have a huge, let's say, brain size in the visual cortex 1. And then this visual quality or acuity, it falls across the periphery. So this is the first work that we have been working on to optimize the data flow from the robot to the teleoperator or the user. In this workshop, so the first task that we did was like we reconstruct remote environments and we send or we stream them to the user. And so as you can see in the video, we have a high quality video that is streamed and it's lagging. But instead, what we did was we optimized it for the user that's looking at. So if the person is focusing on a certain position, that will be high quality, and then the quality of the point cloud will be compressed or suppressed across the periphery into object categories. However, doing this systematic point cloud sampling, it also lose or miss some important information. So you can see here, there is a photograph that was attached to the frame that's attached to the wall, but the person, if he's not focusing on that, so when we see the visual quality, so there is a significant information loss and then a plant. So in order to compensate this information loss, we propose on our original forward sampling pipeline an object detection and segmentation pipeline. Objects are under segmented. So here, this is the pipeline that we are proposing in this workshop, that where we added a scene understanding module, that where we try to understand the remote environment and then compensate the visual so information loss on the periphery. So what we do is we take two kinds of object segmentation and understanding techniques. One is semantic, that is deep learning neural network that is going to classify remote environments into object categories. So you can see here as an input, as you can see here, synthetic data set that there is a plant and a couch, and then we go through this pipeline and it will give us masks. And these masks have an ID, a confidence value, and bounding boxes that we can exploit later from the geometric maps. So when we see the visual quality output of this, it will give us a couch and then a plant that is going to be segmented out, which is what we need. But then it also shows that there are some limited limitations. So as you can see here, as you can see in the second picture, objects are under segmented. So that means we are losing information to have a complete and the pipelines run also, and we added this together into our previous work less than 30 we are going to apply the full frames per second. So in order to compensate this, what we tried was to exploit the depth maps. So if you see closely the depth map, there is a depth discontinuity, as you can see, and if we could exploit this, and then we can extract the objects actually into categories or surface or areas. As you can see here, there is a piglet and a toy that we can identify easily without any colors and texture, and then we can say this is the toy or the difference between. So taking inspiration from this, what we propose is to extract edges from the geometric maps or from the depth maps. Once we have the edges, we combine them as a component, and then we can put them or merge them together to come up with a single, fully connected component. So the green circle is the fixation. So as you can see here, we take the semantic segmentation outputs and the geometric segmentation outputs, and then we merge them together to have a complete segmentation. Where you can, and we added this together into our previous work that where we are going to apply the fluid sampling together with object detection to improve the information loss in the peripheral view. That is laggy and there is a latency. So here is the output that where the user is going to look at. As you can see, the couch is preserved as original quality, but the background where the operator is looking at is sampled according to the photoreceptor distribution. In this video, we showed significant sampling just because to show the difference between the preserved quality and the foveated samples. And in the remote side, this is what we are doing. We take an input RGBD and then we segment them out with using semantics and the geometric mask, and then we project it into 3D to further sample point clouds. As you can see here, the operator is looking at, so the green circle is the fixation points where we are sending from the user side to the remote side to sample. So we did experiments. So we did a remote teleoperation experiment where, as you can see on the left, is the real world where we have to ask users to pick and place which is a ball into a ball. So there is a first experiment is going to use only the original point cloud that is lagging, and there is a latency because of that. And here, so we take that as a reference, and then we combine the foveated sampling with sampling with foveated segmentation with foveated sampling, and we call it FS experimental condition. And then we just only kept our previous work that is using the human visual system, and we call it FV. And the other experimental condition that we took is just only stream segmented objects and do remote operations. The latency and the bandwidth. And here is the output that we see. So as you can see in the video, this is the real world experiment where the robot is going to pick, where the person is asked to pick this ball and then put it into the rate we get, let's say, mold. And all the experimental conditions are on the right. And so as this video is running, I will show you how what the operator is going to look at. So the first experiment is how they will be RF condition, which is the reference condition. As you can see here, the operator or the user is asked to pick this ball and then put it into the target. And here, as you can see, the real robot in the model, they are trying to match. So the point cloud that is reconstructed using from the point clouds is lagging behind. So when we are using the foveated plus semantic segment or object detection pipelines together, as you can see here, when the operator is picking the ball and then putting it into the target, and the point cloud aligns into the real movement, which means it's improving the latency and the bandwidth that is needed. And so if you can see it here in the picture, that these are the results that we see, where we calculated the latency required and the bandwidth improvement that we get out of this. Users reported. And the third condition is the FS condition, and the other one is the SS condition, where we are putting actually improved. And we checked also the execution times, where the task, how they executed this time. And as you can see, the RF condition, the reference condition takes quite so as a really long time, but all the other conditions are improving bandwidth and latency. And the other important thing here is like when we are designing for a human ability to choose among different conditions. So where we ask users and whatever they see, or if the visual declarations that they apply is visualization of their quality of experience. So 5 will be imperceptible and 4 will be perceptible but not annoying. If you have any questions, and slightly annoying 3, and 2 and 1 are annoying and very annoying. And then we take this arithmetic mean score and then we calculate it for each conditions. As you can see here, the FS condition is closely 4.5, which users reported that it's perceptible or more than perceptible, but it's not annoying. And also for FV conditions are actually improving. And we took 50 participants and between 21 and 35 participants, and they all reported that the FS condition is much performing. So as a conclusion, we can see that there is a significant reduction in bandwidth and latency. It improves the user's quality of experience, and it also created another kind of ability to choose among different conditions or settings based on task and user requirements. And it provided innovative way to improve the state of the art in immersive visualization of remote real-time 3D reconstruction or teleoperation tasks. Thank you so much. If you have any questions, you can let me know, and then I will answer.
Great. That's the next speaker. So we don't have time for questions. If you do have questions, you can hop on Teams and write them in the Teams chat. You can also come and talk to Nikhil as well, who's involved in this work.
Perfect, thanks.
Let's see. Next, we're going to have Frank Riegel, who's going to be telling us a little bit about XR and mobile manipulation as well. And as a reminder, this is, again, another, both the last one and this one are also forward consideration.
Is Deepam Patel in the room? Okay, I'll come to you.
All right, thank you for the introduction. My name is Frank. I am from the University of Texas at Austin. And today I'll be presenting our work titled Using Augmented Reality to Assess and Modify Mobile Manipulator Surface Repair Plans. So in industrial environments such as the chemical, oil, chemical manufacturing facilities, maintenance and inspection engineers struggle quite a bit with surface corrosion. Surface corrosion can occur on different types of equipment as well as structural surfaces. But to elongate the life of this equipment and this structures, typically you could just apply a protective coating and get you a few more years to keep the plant running. To do this today, typically operators need to get out in the field, build themselves some scaffolding, put on all the required PPE, and spend hours on end actually spray painting or coating this type of surface. There's an initiative now within the industry to do this robotically, one to increase efficiency as well as improve safety. In current ongoing work within our lab, we have a team working on the ability to actually identify this corrosion from an autonomous mobile manipulator using combined LiDAR and RGB data. And then we've actually demonstrated the ability to repair this surface corrosion by using a dual-arm mobile manipulator there with a custom designed end effector that can actually spray the corrosion. But the problem is within this industry, pretty much anything you do, you need some sort of supervisor to sign off on it, no matter if you're human or a robot. So there needs to be some sort of interface that could be used for non-experts within the field to actually visualize the corrosion that's identified by the mobile manipulator, ensure that what the robot identified is not actually a critical piece of equipment, such as the pressure gauge here or a ball valve. Also, give the user the ability to use like human intuition to provide some sort of mask or a buffer around this, critical pieces of equipment to ensure no overspray gets on a glass gauge. And then also the ability to give the user the opportunity to actually confirm and execute those robotic repair plans. So the current state of the art within industry is using these tablets or gamepad controllers that operators typically will carry around with their hands in the field. Now, I probably don't need to explain the issues with these in an extended reality workshop, but they're not the most natural. They remove your situational awareness around the environment, and they're just a nuisance to carry around. So therefore, we envisioned and developed a solution that uses an augmented reality headset, the HoloLens 2, to pair a user with a mobile manipulator using prior localization and communication framework we published back in 2022 called AUGRI. And we built up on top of that a situational task accept and repair module, or STAR for short. Essentially, this augmented reality-based module enables the user to actually receive notifications from the mobile robot that's in the field when it's identified corrosion. It's able to visualize images as well as point cloud representations of the planned coverage path. And it also is able to give the user the ability to actually use holographic exclusion volumes to mask critical pieces of equipment that may be, in the plan to be covered with some sort of protective coating. And then also gives the user the ability to actually confirm or reject to actually perform the work. So I'll go ahead and just play a quick video of the module in action. So here you can see a user wearing a HoloLens 2 received a notification from an autonomous agent that's in another part of the lab. The autonomous agent sent this notification. The user was able to open the notification and visualize an image of what the robot found. Now, in this case, the user was concerned that there was a critical piece of equipment. So the user actually went up to that physical location of that equipment and visualized the point cloud of what the robot plans to use for its trajectory planning to perform surface coating. Now, the user noticed that there was a critical pressure gauge there that was actually being covered by the robot's repair plan. So what the user did is it clicked on the interactive menu that we provided, and up popped a exclusion volume that's usually able to manipulate, scale, and rotate within the real world to actually mask off, almost like using blue masking tape, but with the HoloLens. So once the user was happy with the placement of the exclusion volume, the user can then verbally or through a GUI interface in the HoloLens click send. And on the back end, what we're doing is we're taking that exclusion volume, the confinements of it, and removing all the points that were within that. Then the user is able to visualize the modifications to the coverage plan point cloud and observe the robot go and perform the work. Now, another novelty of this work is the fact that we provided the HoloLens 2 users an actual reference frame of where the robot plans to navigate. So in industrial environments, these are very dynamic environments. So having a reference frame of where the robot needs to actually go to get the most surface coverage is very useful. And in this case, while the robot's navigating there, the user can remove certain sorts of tools that may be in the way or other building or construction supplies that may have been in the plant while these repairs are going. So you can see here that the robot navigated into position and is able to go ahead and actually perform its surface coding. So in conclusion, we developed an augmented reality-based module to enable users to work with autonomous mobile surface repair robots within industry that can enable them to receive notifications, visualize the coverage plan, modify that coverage plan with exclusion volumes, and actually confirm or reject the plan. Future work plans to enable the user to perform free-form exclusion volumes. So essentially, you can draw a circle or a square with your pointer finger and remove those points from the coverage plan. We also have thoughts of extending this to a telepresence situation to where we can actually extract the 3D model of the object that has surface corrosion, and we can have a full remote situation to where the user can actually align these exclusion volumes from a completely different location. And then also perform system capability studies as well as system usability studies
regarding
in regards
multi-user
to
immersive
user workload
remote robotics interface using mixed reality. Again,
so that is all.
was
Thank you very
was
much.
done by my
I'd be more
colleagues
than happy
and
to
me
discuss in the
and
posters
Deshpande.
in the room next to us. If you want to learn more, go ahead
I would
and
like
scan the
to
QR code.
define somehow what teleoperation is. And teleoperation is actually a technical term for operating an unmanned machine system or robot from a distance. Remote teleoperators sit in a control center and use a robot from afar to perform
Great, thank you, everyone. Next, we're going to shift back to Jonas again
might be
for
practical,
a
dangerous,
second
or
talk.
impossible for a human to accomplish in person. So this technology has many applications, including exploring hazardous environments, conducting search and rescue missions, performing maintenance in remote locations, and even
can you hear me?
Procedures with
Okay, yep. So we'll go ahead and mute, and we should be able to. Yep, we can see your slides here. So go ahead.
There is a high-Q robot that we haven't designed here in IIT, and it's trying to extinguish a fire. In this presentation, I would like to present our research work regarding a multi-user immersive remote robotics interface using mixed reality. Again, this work was done by my colleagues and me and Deshpande. About this project, I would like to define somehow what teleoperation is. And teleoperation is actually a technical term for operating an unmanned machine system or a robot from a distance. Remote teleoperators sit in a control center and use a robot from afar to perform tasks and operations that might be impractical, dangerous, or impossible for a human to accomplish in person. So this technology has many applications, including to support exploring hazardous environments, conducting search and rescue missions, performing maintenance in remote locations, and even enabling surgical procedures with precision from a distance and medical facilities. As you can see here in the video, there is a high-Q robot that we have been designing here in IIT, and it's trying to extinguish a fire using by teleoperated by, let's say, a human user. So this project was coordinated by Nikhil Deshpande. If you would like to know more, he is there. He's one of the organizers, and then you can discuss in detail about this project. But I would like to more talk about the multi-user part of the challenge that will be on the to assess the remote environment and facilitate the informed decision making, remote operators rely on the robot's camera or sensors to perceive the data communication between the robot and video and data captured by this device must be transmitted between the robot and the remote operator for analysis and decision making or to support the decision on a single user. However, the disasters can disrupt communication networks, lead to delays, signal loss, or unreliable connection between the operator and the robot. Eventually, it affects the situational awareness and creates extra stress on the operator, which will affect real-time control and decision making. So while remote teleoperation advanced, improving or addressing these challenges in disaster scenario remains ongoing research and development. So here on this paper, I would like to present the mirrored multi-user immersive remote telerobotics interface using mixed reality. So this work focuses on distributing the challenges that will be on the operator into multiple teleoperators or users. So here we have a remote site component where robots are, and there will be a host server that is facilitating the communication, the data communication between the robot to the multiple users. So we believe this approach will significantly reduce fatigue or stress that is going to be occur on a single user, and then also it introduce promotes or introduce collaborative decision making, and in the end enhance both the efficiency and the safety of or transform the data. So the proposed system has three main components, as I said: the remote part, the host server, and the multi-user side. And the remote environment side would consist the LiDARs for localization and mapping, an RGB image acquisition device, and the robot itself where we check the value requirement for each user. And the host server will have a dedicated server that's dedicated to do acquisition or re-encoding or reconstructing data that is coming from the remote environment. And VR-based interface. So usually in disaster environments, between the host and the user, the constraints of there is a constraint on limited network and the network latency is huge, or there is a very limited bandwidth. But between the host and the user, it's relaxed, and then we can assume that there is a high bandwidth. That was so the host server captures the incoming RTP packets or point cloud packets, and then it decodes and re-encode them or transform the data into a different kind of encoding to where to transmit and send it. So basically what we did was our proposed mechanism for a video and point cloud data. We re-encode or we change the RTP headers where the destination IP addresses, and then where we check the bandwidth requirement for each user, and then we re-encode and then re-transmit back to each user. And the task here on the user side, we have a multi-user virtual reality-based interface where we could have a 2D, 3D, and VR-based interface. But on this implementation, we only have implemented a multi-user virtual reality interface where the operator could control the robot using the Vive HTC Vive motion controllers, and then he can see the robot model and the real environment through HTC Vive Pro. The user to grasp and put it. So we did an experiment that was from Luxembourg to Genova, which is around 863 kilometers, where we did a teleoperation task. And the operator will be in Luxembourg, and then here in Genova, in Italy, where the robot is going to be. So here, as you can see on the left, we have two users. One is in Luxembourg and then one is in Genova. They see the environment that is in the user left here, and the operator could see the robot model in VR, and then they could see each other and they can communicate to perform the task. And the task here is to move the red ball. Again, similar task with my previous presentation. So here to move this ball and then maximize the bandwidth to the ball. Minimize latency. And as you can see here, just only using 2D videos or stereo videos, it will be very difficult for a single user to operate and to perform this task. Meanwhile, while they are doing this task, the other operator or the supervisor will help the user to grasp and put it into the desired target location. And eventually, this operator will try to also open the door remotely. This project on here and real teleoperators and then how it also helps them to perform the task. So we studied this, and then we say lots of let's say results, and it creates a collaborative virtual reality environment that empowers multiple users to engage in interactive robot control from a distance. And we created a host server that is responsible for efficiently distributing data from a remote side to multiple users by re-encoding again with a different bit rates. And it maximizes the bandwidth usage and minimize latency, and in it's ultimately enriching immersion across the virtual reality interfaces for remote environments. In upcoming iterations or work, we will try to leverage machine learning or AI techniques to enhance the robot capacity to make, let's say, informed decision or semi-autonomous decisions. And then we will try to understand the impact of this this project on real teleoperators or subjects, and then how it also helps them to perform.
So can you see my screen now?
So thank you so much. I think I have some minutes. If you have any questions, I would like to hear it. Thank you.
Right now, I can hear you. All right, now I'm on the presentation.
All right.
So you see the presentation window now?
Thanks, Yas. So that concludes our 4 award nominee papers.
So
we're going to do one more presentation and then we'll break for lunch.
It's a pleasure to be here. My name is Sefer Madani. I'm a PhD student in robotic surgery.
So one more.
In McGill University Robotic Surgery
and
Center.
So for that, we've got Julia.
Today, I'm going to present some of our initial
we
work
switched it.
on the domain of universal calibration frameworks for mixed reality assisted robotic surgery. So mainly we're going to delve into the clinical aspect.
If you want to go ahead and share your screen.
Mixed reality, particularly in the surgery. But I can hear myself somehow. So the clinical need basically for so can you see my screen now? The use of mixed reality in general. I can't hear you. Stemming from what I'm going to tell you now. So basically, right now, in some procedures such as spinal fusion,
right now I can hear you.
Okay, great. Yeah, so we can see your slides
that you can see, for example, here
and hear you. So
right now I'm on the
when you are ready, go ahead and take it away.
Yeah, there we go. So you see the presentation window now? Through the vertebral body.
Okay, perfect.
Perfect.
So hi everyone.
It's a pleasure to be here. My name is Sefer Madani. I'm a PhD student in robotic surgery in McGill University Robotic Surgery Center. Today I'm going to present some of our initial work on the domain of universal calibration frameworks for mixed reality assisted robotic surgery. So mainly we're going to delve into the clinical aspect. Very dangerous. That's why companies like Medtronic mixed reality, particularly in the surgery domain. And like the clinical need basically for the surgical navigation system and the use of mixed reality in general is stemming from what I'm going to tell you now. So basically right now in some procedures such as spinal fusion there are some pedicle screws that you can see, for example, here on the anatomy.
I'm trying to also select a good pointer.
Yeah, there we go. So for example, we have to pass it through the vertebral body with very accurate dimension and spatial perception, because any inadvertent protrusion into the spinal cord canal, it can cause like irremediable consequences for patient and for the surgeon and the whole thing. So it has been adopted. That's why initially they used to do lots of fluoroscopy and X-rays, 50 or 60 X-rays in one session of surgery, and that was like cancerous for the surgeon, for the patient, very dangerous. That's why like companies like Medtronic came up with this OR that they do an initial registration of the anatomy and like on the back of the patient, register that anatomy into the surgical navigation system, and as you can see here, they try to fine-tune the trajectory of the instruments which is tracked by the navigation system. And it's a very hard thing to do generally in the OR, because the hand-eye coordination and always having an eye on the different screen, like ways away from the surgeon, away from the incision site. So that's all imposing lots of cognitive load, and this has been the topic of today's also presentation. So that's why basically we have to get into the MR and mixed reality incision site surgery and looking away, like relieve some of the problem in the OR for the spine and neurosurgeons. And it has been adopted for a while in different ways. 3D model not the best still, but in neurosurgery and spine there are some available technologies, and the key is to basically like being able to see through the skin, because right now the practice is super invasive, very large, like 10 inches of incision basically the are being happening on the back of the patient. So basically we have to be able to see through the skin without the need to harsh a very huge incision and just see the anatomy below. So major challenges to this basically is degrees. So that's basically why you have we need a robust real-time anatomy tracking and localization method for on the OR table, and we know the answer to that. That's the surgical navigation system. Also, we have to accurately render that 3D model and register it into the mixed reality scene, so the surgeon can focus on the incision site instead of looking away and do its job. So the research question basically now is to how to localize and render the anatomy 3D model that is like reconstructed through CT or MRI or whatever inside the MR scene accurately and reliably, because basically as we discussed, Dr. Jeff and Del Marico from Microsoft was also like mentioning this stuff. So basically the perception, particularly perception of these MR devices are not that accurate in terms of spatial accuracy, especially when you are dealing with like human in surgery. You need sublimeter accuracy and infuse the accuracy for angular motions like 0.1 degrees. So that's basically why you have to infuse 3D anatomy into the augmented reality interface, such as Microsoft HoloLens 2, Apple Vision Pro, whatever, to the surgical navigation system, which is trusted, and in real time render the 3D anatomy of the patient, which is connected. And here is our system architecture. So it's we have a real time computing unit. We have the anatomy, which is like registered. It easily can be boiled down and like fixated to one navigation array. And in order to tackle that surgical navigation system, and also one navigation array is connected to the head-mounted display, or it's not a head-mounted display, it's a mixed reality interface, HoloLens 2 Unity board, let's say. And it's being constantly tracked accurately with respect to each other, and this is basically done through one incision, and that's not no longer super invasive transformation matrix that you can see like the mathematical problem, the problem that we have to tackle if we want to use and infuse the accuracy and reliability of the surgical navigation system to render and very accurate navigation array 3D anatomy into the patient body is finding the homogeneous transformation matrix between the optical frame of a mixed reality camera and the position that we have between these two. So basically, navigation array which is connected and easily letting that camera to be tracked by the navigation system. So this is basically it easily can be boiled down to a hand-eye calibration problem. This is before in order to tackle that very fast and easy, we use just a fiducial method, like a fiducial marker we have over here. That's the center of our board, center of the virtual scene, Unity board, let's say. We have that from the Euphoria engine. We have the surgical navigation system giving us the relative position of these two. And basically here, it's a very simple homogeneous transformation matrix that you can see, like the position of this optical frame with respect to the board frame is equal to here is the reconstruction of this the relative position of these two with respect to each other. The navigation array between these two, the calibration path and the navigation array is connected to the camera, and the last one is the rigid position that we have between these two. So basically, you can always solve for this easily, straightforward, and you can register your anatomy. The reality has been rendered from this concept of mathematics. The one which is localized by the navigation system. This is the one that we are interested. This is before registration, and after we register it, it matches the reality. And basically, right now, you infuse successfully that accuracy of anatomy, crazy fine accuracy of the navigation system into the augmented reality interface. Here we are using a very accurate robot. For experimental setup, we are using our surgical robot to just basically imitate a surgeon's head motion. But basically, the presence of robot is here for and also spatial, just imitating a surgeon's head motion. Here is the reconstruction of this scene in reality. So basically, you have this mixed reality camera, you have this mixed reality camera IR tracking array, you have the calibration pad, that R reference, the W, the fiducial marker, surgical navigation system, and the MRC rendering unit. And localized through the basically, again, I'm trying to show you like how these matches the reality and the other one is details, and how localized like the reality has been rendered from this concept of mathematics that I told you. And basically, to just cut it short, we tried to do this experiment. So we were trying to see, okay, up to some extent, we can localize that anatomy 100% overlapping with a decent accuracy that we trust the surgical navigation system. So here we are using a very accurate KUKA robot, KUKA LVR Med 14. I'm sure the community know about the accuracy of the system to like follow a few paths, like the circular paths, linear G-shaped paths, lemniscate, and also spatial dome-shaped paths. And basically, we are trying to localize that camera, localize that frame that the camera and basically would be happy is relying on and localizing. Let me show you over here my email address and becomes clear. So we are trying to localize this position once it's detected and localized through the Vuforia method, which is the regular visual fiducial method, and the other one is basically the localized through the surgical navigation system using our registration matrix. And we see that like there is an excellent match between the reference and the optical method, that we can barely even see like they're 100% overlapping, and it shows their error is much less and everything is all good. And basically, to recap, we have successfully infused the reliable sub-millimeter nice surgical navigation system technology into the mixed reality scene and register it. There are lots of complications associated with these concepts, and our team is basically working on it, but this was one of our first steps towards it, and it was an honor to present it to this community. And we would be happy to hear from you. Feel free to reach out through this QR code, my email address, and here are the institutions supporting our work here in the McGill University Sarcoma and Orthopedic Surgery Center. Thank you very much. I'm happy to hear any questions. Thank you very much, Jeff, for everything. If you hear me, thank you.
Great, thank you. And thanks, everyone. So that wraps up our first session of poster presentations. So we will break for lunch. If you can, try to keep your lunch to 45 minutes. When we come back, we're going to do one additional poster presentation and then 3 more keynote talks. So we're going to try to get the schedule more or less back on track. If you can keep your lunches to 45 minutes, which we know is short, so do your best. So we will resume at about 1:15 with the next talk. So thank you, everyone.
Thank you very much, Jeff, for everything. If you hear me, thank you.
All right, welcome back everyone. Going through the technical sessions again with the setup and everything. But now we'll have a talk by Deepak Patel, which is a poster talk. And he has his poster across the hall if you want to ask questions with him. Go ahead, Deepak.
Hi everyone, my name is Deepak Patel and I'm a PhD candidate in computer science at Purdue University. Today I'll be talking about remote teleoperation of social robots via virtual reality, a multimodal affect learning approach. In today's world, there are significant challenges that we must address, especially in healthcare, where many isolated or elderly individuals often suffer with loneliness and lack of emotional support. Further, healthcare professionals are frequently unaware of their patients' emotional distress, making timely intervention very difficult. If we come to education, during remote learning, educators find it very difficult to effectively monitor student engagement. There's a persistent issue of inflexible teaching methodologies that don't adapt to individual student needs. These problems underscore the need for innovative solutions that can genuinely understand and respond to human emotions in varied contexts. To address the challenges we have discussed, we are harnessing the recent advancements in social robotics. Our primary aim is to deeply understand and respond to intricate human emotions. By seamlessly integrating virtual reality with a cutting-edge multimodal affect learning model, we achieved nuanced emotion recognition. Let's picture robots that can provide emotional support to the isolated or the elderly. Same way in education, envision robots that not only adjust their teaching methods, but also keep and monitor the students based on their engagement. It's about leveraging technology to truly resonate with genuine human needs and emotions. Emotion detection in teleoperated robots has historically been one-dimensional, primarily non-multimodal. But this approach had its own issues. For instance, facial recognition has often been compromised by factors like inconsistent lighting, varied viewing angles, and personal facial differences. Similarly, speech analysis also struggles with challenges from accents, diverse languages, and ambient noise. And while physiological signals provide a deep insight, the dependency on extra sensors has made it less feasible in many of these scenarios. Clearly, there is a pressing need for a more comprehensive solution, and this is where our work comes into play. Our solution seeks how robots understand and respond to human emotions. We introduce a multimodal affect learning approach in VR to holistically understand the operator's emotions. First, we harness the capabilities of advanced VR sensors to meticulously collect a wealth of data. Next, we fuse diverse modalities since we don't rely on single source, as we want to ensure a more nuanced understanding of emotions. The heart of our approach is the M3ER framework, which stands for Multimodal Emotion Recognition Framework. It's designed to simultaneously process multiple cues, capturing the intricacies of human emotions. And lastly, once we have the understanding, we put it into action using the DeepQ network. We guide the robot's interactions, ensuring they are not just reactive, but emotionally attuned and empathetic. To start with, we have employed the Oculus VR system, which is equipped with a wide array of sensors. This allows us to map facial expressions to emotions in real time. Further, by analyzing auditory cues and linguistic nuances from user speech, we get deeper insights into their emotional state. All this data is then structured into a multidimensional time series encompassing visual, auditory, and physiological cues. Once we have the data, the next step is fusion. Using a strategic late fusion approach, we synthesize data from various modalities to get a better idea of the user's emotional state. Each type of data is processed through a fusion network and then unified. This consolidated data is then fed to the M3ER model. Let's have a look at that model. Our M3ER model stands as the foundation of our emotion recognition system. It's uniquely designed to simultaneously process multiple cues, facial expressions, linguistic nuances in text, and variations in speech tones. But what truly sets M3ER apart is its innovative multiplicative fusion. This fusion technique is not only combines cues, but intelligently emphasizes the more reliable ones and suppresses the less consistent ones. In cases where certain modalities prove ineffective, M3ER even generates proxy features to maintain accuracy. With this holistic approach, we don't just detect isolated emotions, but grasp their complex interplay, enhancing the model's generalizability across various datasets. With the emotional state recognized, our DeepQ network comes into play. The DQN is structured with specific neural network architectures and parameters. These help in translating the emotions into actionable insights for the robot. By maximizing the cumulative rewards, our robot becomes not only effective, but also emotionally attuned to human nuances. Navigating the challenges of real-world implementation is very crucial for our system. The unpredictability of real-world settings, coupled with varying lighting and noise, poses significant challenges for our VR data capture. This also underscores the need for an exceptionally resilient RL controller. As we adapt to these diverse environmental factors, we emphasize that the precision in detecting human emotions remains at the forefront of our endeavors. As with any groundbreaking technology, ethical considerations are of prime importance. We prioritize user data privacy, ensuring robust security measures, and obtaining clear consent. We are also conscious of the system's potential misuse and are taking steps to prevent manipulative uses, especially in sensitive areas like customer service. Moreover, ensuring our system's accuracy is critical, especially in high-stakes situations, for example, surgery. Misinterpretations can have significant consequences. In conclusion, we have pioneered a transformative system for robot teleoperation using VR. Through the integration of a transformer-based model with reinforcement learning, our system stands out in accurately detecting a spectrum of human emotions and precisely steering robot actions. This work highlights the potential of robots with enhanced emotional intelligence. Robots are not only adaptable, but deeply attuned to human emotional needs. Looking ahead, our commitment is to refine our system by training on various comprehensive data sets and ensuring heightened robustness. Further, we are investigating the integration of advanced modalities such as haptic feedback to enhance richer emotional understanding. Such innovations and adaptability are pivotal in positioning our system to excel across diverse real-world settings. Thank you.
Thank you very much, Deepam. If you have any questions for Deepam, you can always go to his poster across the hall. He'll be available in the coffee break as well.
Thank you.
Thank you. Let's see. We good? Yes. Okay. Welcome again, everyone. Our next keynote talk is going to be by Professor Maru Cabrera, who's an assistant professor in the Rich Minor School of Computer Information Sciences at UMass Lowell. Before that, she was a postdoctoral researcher at the University of Washington, working with Professor Maya Kakmak in the Human-Centered Robotics Lab, actually. So she's continuing her work in human-centered robotics at UMass Lowell. And her research interests, of course, along with human-centered robotics, are collaborating tasks in home environments, which some of the stuff we will see today over here. And also with an emphasis on inclusive design to assist people with disabilities or older adults aging in place. So this approach draws on interdisciplinary intersection between robotics, AI, machine learning, computer vision, and extended reality. So welcome, Professor Cabrera.
Thank you. Thank you, everyone. So yes, I'm here to talk about leveraging XR and human-centered approach in assistive robotics. This is very broad, but for this talk today, and this kind of shows you my path throughout my works during my PhD and my postdoc. And I'm going to focus on this system for surgical telementoring using augmented reality and some of the work that I did during my postdoc related to user preferences in robotic systems. And what I hope you'll get out of this talk is that all of these systems are going to have strong considerations of the user when we are making decisions on these systems. So now that I am an assistant professor at UMass Lowell, what you see here is kind of like the wedge, this wedge in the middle. This is where I want to stay in my research interests. So I want to combine aspects of human-robot interaction, human-centered design, and accessibility. And of course, this aspect of augmented reality, virtual reality, or extended reality into how can we conduct interdisciplinary research in a way that is more inclusive in terms of the users that can reach this technology. So let me just start with this first topic during this project I worked during my PhD, and it's related to assistive technologies in surgical applications. This work was done funded by the Department of Defense. And the idea behind it, the motivation behind it was to increase the sense of co-presence between a mentor and a trainee in a situation where it was funded by the military. So there was a strong aspect of motivation by the military. Someone is deployed and they may have basic surgical training, but not specific surgical training. So they can get the assistance from someone that is stateside. And then we can reduce the amount of distractions and focus shifts that they need to do to accomplish the task that they are being guided through. What happened? Nothing happened. Okay, so the current gap that we have in most common telementoring systems that are out there, we see here on the top, that is the typical system for the person that's conducting the surgery. So they need to be looking away at a monitor somewhere else where they need to remap whatever they're seeing into the space that they are working. And then we see on the other side of the mentor that we have very limited tools for interactions or to be able to read the room or understand the context in which this surgery is taking place. So I brought here the full promo video. I don't know if it's going to have sound because of the setup, but you can see here that it starts somewhere in Afghanistan. The military is deployed. They're doing some mission. The sounds are really funny. I will share with you later the website if you are interested in watching it with sound. But they're saying, yes, man down, we need to extract. So what happens is this person gets sent to an advanced location somewhere, and they contact the mentor who is stateside. Okay, yeah. Phone call, they are saying, yes, I'm going to get the system. Wish I can make this go faster. How about if we make it go faster a little bit? No. Oh, man. Well, I will share with you the the end of it. But the system works in a way where they are showing annotations much like this, but they are able to move and present the annotations based on the field of view of the trainee. So when this project started in 2015 and it ended in 2018, this is where we started with 2 tablets on the trainee side. So we had 1 tablet where we were adding annotations, and then we were anchoring these annotations so that the annotations would be robust to translations and rotations. As you can see here, this first approach still had a lot of problems. If you can notice in the bottom part of the right picture, or yes, your right picture, the rendering is not transparent. So you can see how the person's hand is displayed somewhere else and is not directly, the proprioception is a little bit wrong. So that was the first motivation that we had to improve this system so that we could make it truly transparent. And we took advantage of infrared sensors and depth sensors, as well as this Fire phone that was from Amazon, so that we could remap the perspective on with respect to the face of the person that was looking at this. And you can see here the alignment of the hand and the arm is a lot better than the previous picture. So these were some of our initial tests to make this truly transparent. This was also taken at Purdue. I'm sure our previous speaker is going to recognize the building. Okay. So hopefully this will play. I have no confidence. But after we were using tablets, we moved to the HoloLens, to a head-mounted display. And you can see here the overlaying of the annotations. So we had annotations that were lines, annotations that were tools. The annotations are lefty because one of our developers was a lefty, so we had some issues there, but you kind of get the idea of what's going on here. And in the inset, you can see the actual person that is wearing the HoloLens. So we tried this. This was a mock abdominal incision task that we were trying here. So you can see the placement of the tools. We could see dots where they're supposed to continue the cut. Hopefully I'm going to do this and it's going to continue. Yes. At this level, we conducted an experiment where we were comparing our different methods of interaction with the head-mounted display. And we also did an analysis on what would happen if the tablet had been there. Because yes, we started with the tablet because it was a good first step, but we wanted to move past this. And if we had kept the tablet, that would have meant that doctors, as you see here in the left, they would have had to reroute or remove so that they could adjust to the technology that was placed there in the first place. So you can see here in this inset is the presentation of the instructions that the condition with the head-mounted display they were looking at. So yes, we reduced placement errors by 45% in this first task that you see on the right with the landmark annotation, landmark placement, and about 92% for the one with the abdominal incision. Let me talk a little bit about the mentor side now. So the mentor side also started with another tablet where we started with a GUI design where they could have different tools, different lines, and they could create these annotations that would be sent to the trainee. We were interested in providing to the doctors additional methods of interactions that were non-verbal, that were based on gestures or that were based on them executing some of the tasks that they would normally do. So we conducted this Wizard of Oz experiment where we took a very large interaction screen and took them through a procedure of a fasciotomy. And then we would advance based on this, but this is what the trainee did. What would you tell them to do next? We had one version of the experiment where was a single doctor that was working, and we also did this in a collaborative manner where we had several doctors working. They had access to their own tools, so that then the annotations that they picked up the tool, it would appear on the interaction screen. And this experiment was extremely interesting because it led us nowhere. So all of our hypotheses of let's provide all of these to these surgeons and they will be really excited. At the very end of this experiment, they said, give me a way to draw lines, give me a way to add tools, give me a way to add points. I don't care about anything else. And it is important. So it was a learning experience more for us than for them, because then it allowed us to then focus the system in something that they would actually use. You can see here, this was the final version of the mentor side. It was a large TV which had touch capabilities. I think I have a video a little bit later, but then we minimized the presence of tools and lines and dots, which was what they were interested in. So basic framework was related to this. We also added another experiment, which I can talk later on if anyone is interested, because we were using a network. So we explored a little bit what would happen if there were network delays. So we were playing with the idea of visualization of future steps on the trainee side, so they would have a way to mitigate network issues. So disclaimer for everyone, what is coming, it's going to be a picture of a cadaver leg. It's far away. If you can think about it as a potty leg, as a fake leg, think about it. If not, cover your eyes, I'll tell you when to look again. But this was one of our final clinical tests for this system around 2018. We went to Indiana University. And as you can see here, we were basing ourselves off of a fixed camera that was on the top. So you can kind of realize from this picture that there were calibrations and remappings that were occurring between the fixed camera on the top and the location of the HoloLens, because then the mentor was doing the annotations based on the fixed camera on the top, and then that had to be remapped through the correct perspective so that the trainees would be able to see it in the correct place. We did this experiment both in a condition where they had no mentoring and a condition where they did. And then we had a second test that was in the field. We actually went to a military base in Virginia, where we were able to do a different procedure. This was not a fasciotomy of the leg, but this was a cricothyroidotomy. So it's a procedure that happens on the neck for an airway. And you can see in this video what the mentor was seeing as they were operating, okay? So they would be able to draw lines, and then the person wearing the HoloLens would be able to receive. So the system also had another jump because there was no fixed camera anymore. There was no transformation between perspectives, but then there was an adjustment on the frame that was used to create the annotations in, so that we could also have a track of how the movement has been done, so that the projections were correctly placed in the correct frame that was in the street. So with that, I'm going to close this section. And these were most of the people that were related to my work there at Purdue. And now I'm going to jump and talk a little bit about user preferences for assistive robot systems, because this is a very unique topic and I did not do everything related to extended reality. I decided to focus on this project here that was robotic limb repositioning with supervised autonomy. So the idea behind this was people that have mobility limitations need to be moved so that they don't get sores and quite constantly. So in a way to expand their level of independence, could we rely on robots to assist on some of these motions so that they can instantiate those on the by themselves? So how can we perform limb repositioning with a robotic system and an accessible robotic interface to improve their quality of life? So we were basing ourselves here on programming by demonstration. So there would be an example from a human on how to conduct the motion that we were interested in. We started with motions of the arm, of elbow extension, or what was the other one? Rotation. I forgot the names. Flexion and extension. There you go. But the idea was that these trajectories were going to be saved, and we would have landmarks that were going to be augmented and visually available for the users so that they could create changes or modifications on the trajectories based on their preferences using an accessible interface. So you can see here, it was based on a web design. You could run on a phone. And because of accessibility, then all of these buttons can be accessed through input devices like neck buttons or sip and puff devices. And they could choose the correct exercise and the correct extremity. And then you would see here how they have access to each of the landmarks, and they would be able to move them as needed. This was work that was done with an undergrad, Shinyi Wan. And now I want to spend a little bit of time of whatever is left to talk about I call it the beginnings of current work. This is something that some of my students are working right now, but is very much in raw stage. So one of the projects that I'm involved in at the moment relates to VR games for youth with cerebral palsy. So how can we take advantage of both the immersive experience that VR provides with some of the haptic feedback that you can get of platforms and also of devices, so that we can give these kids that are doing this therapy some of the encouragement and some of the experience so that they can relate these motions to things they do in real life or in their day-to-day. That is one of the projects that we have at the moment. The idea is that we will have different conditions. So one of them will be just with the robot, one of them will be just with the VR system, and one will be with the combination of both, so that we can establish the preferences of the users and what do they feel is promoting their functional movement and their willingness to adopt something like this in their therapy so that they keep doing therapy. The other aspect of augmented reality that I am trying to include in my research is related with collaborative tasks at home. So it is more on the side of, yes, the robot has learned to perform X task. So how can we use this information from learning and convey it back to the user so that the user can provide not only, yes, you did a good job, but also if the user may submit a correction, all of these terms of learning that are a little bit abstract for the lay user, how can we convey them in a way that makes sense for people to give feedback or to make annotations, and those annotations be remapped to something the robot can use in the learning and then incorporate. So as a more both attacking a little bit of explainability and adaptive learning in a way. So that is what I have for you today. I was planning for 20 minutes, but I am happy to answer some questions. Thank you.
Very much. Yes.
Like you have the remote user that's drawing the line.
Mm-hmm.
You have the actual user that's performing surgery. When the line is drawn, it's projected onto that engine for the three dimensions, right?
Yes.
Yeah.
Yes. The beginning, when we were using the tablets, we had to stay within the realm of the 2D because the picture was based on color. But with the HoloLens, we were able to put them in a way that they continued with the shape of the depth that was perceived by the HoloLens.
Was that more helpful for the surgeons, or did they not?
Yes and no. So, for instance, one thing that happened to us in that clinical test when they were using the helmet, the HoloLens, is that the weight of the device is still too heavy for them to be looking down for extended periods of time. So, so that is something that is still a little bit of a challenge. And to make the HoloLens work outside, we did a little bit of magic. We had some palm trees covering. Yes. Because of the anchoring that we were using and the type of procedure that we were using to anchor the information, the information that the mentor receives is only the color, right? But then you can, if you have in the 3D space, you have where those colors match in the depth, then you can relate the annotations in the position in 3D. Thank you.
Speakers come up.
back now.
You speak now. There is a little bit.
Yeah, but that's comes through my speakers. If I remove it, it's gone. So I wonder if I'll be able to play back the video then. Sorry.
Maybe you can mute it.
So
when you're playing the video, you can unmute it, then mute it back.
what do you want? You are going to need to mute?
Yeah, I can just look.
When I play the video, then you'll be able. Then I need to. What do I do? Then I connect this. Or yeah, you want to try? We'll try. All right.
Okay. So you're okay?
Yeah, it is good. It has maximized this. This we get to see by next slides, whatever. Okay.
Okay, our next speaker is going to be Mr. Carlos YSP Gonzalez, who's a research engineering director at Reality Lab Research at Meta USA. Currently he's supporting research engineering and machine learning infrastructure for telepresence applications, so very relevant for this workshop in virtual reality and augmented reality. You almost have referenced the latest podcast with Mark Zuckerberg and Lex Friedman. So he previously worked for over 7 years in self-driving at Uber, ATG, and Aurora companies, leading the development of perception and prediction algorithms. He's gathered 10 years of experience at National Robotics Engineering Center and working in automation for agricultural machinery, including development and deployment of fully autonomous tractors in Florida. He graduated with honors from LaSalle School of Engineering and received an MSc from Carnegie Mellon. And he's authored more than more than 20 publications and 30 patents as well. So please welcome Carlos YSP from Meta.
Well, thank you for a very kind introduction, Nikhil. Yeah, I am honored to being able to speak here. And today I will talk about needing seamless telepresence through photorealism. To get started, I want to talk a little bit about history of communication. I mean, this is a very simplified version. I think one big breakthrough that we had through the history was the invention of the postal service. This then enabled for the first time two people that were remote being able to communicate at distance with some latency. That that was a big breakthrough. So it took more than 2,000 years for the next big invention, in my opinion, was the telegraph. This actually severely reduced the latency. It is still required to convert speech into like some code, right, to be able to communicate. This was addressed not much after with the telephone. This was the first time that two people could communicate at distance in real time, like with no latency. And not so long after, I mean, I put here 1930s of the invention of the video calling, but this is where I did some research. Looks like that was the time that then they were able to communicate two television systems in reverse and have like some sort of something similar to video calling. Obviously, this technology has advanced very significantly in the last years. Now you all have smartphones, you can experience this. So I wanted to talk about video calling a little bit. So as good as this is, you can see it has a few drawbacks. So I'm going to just point, and you're all very used to this, point, one capture scene of how video calling looks like today. So you have a person in the top right of this video speaking, but when you look at the others, it's unclear if they are paying attention. I'm going to assume they are all paying attention, but it's unclear. And why is it unclear? What's missing here in this experience? I think there are many things, but there are two very important ones. The first one is there is no eye contact. It's very hard with this type of system to establish eye contact. And eye contact is arguably probably the most important factor in communication, to have like some engaged communication. And that's missing here. I think there is another big piece missing that probably you identify. Is the lack of some shared context, shared space in this case. There is a lot in communication, there is a lot of non-verbal cues, that unless they have some common space of some like a place to reference, some coordinate systems, right? They fall into basically they don't have any meaning, right? In this case, the lack of shared space has this problem, right? We don't know, for instance, the person on the top left, what is he looking at, right? We miss that context. So on the bottom left, that person could be actually playing Minecraft. We don't know, right? This context we don't have, and then this is one of the issues of this type of system. Now compare, just to make this even more clear, compared to this scene, right? In this scene, they all, the eye contact is there, and then it's a shared environment. This allows a lot of like verbal cues to be present, and then non-verbal cues and signals to be present. For instance, you can see different body gestures. You can see eye contact, expecting reaction from some other person. You can see also hand gestures and a bunch of other signals that flood this scene, right? So ideally, this is the type of communication we like to have. This is would be like to be present in the conversation. So going back to my history diagram, this is the some of the history that I think big breakthroughs that we had in the history of communication. And I think we need something better than video calling. Ideally, some sort of environment where we can have interactions as naturally as we will have in real life. And I think the next step in the next breakthrough in communication is going to be the telepresence. Let me talk some more about this. I mean, now I'm going to play a video that has some sound, but let me introduce our VP of Research in Reality Labs Research at Meta. And he gives some idea, I mean, that was from last year, about where we are today. And if you look at this presentation, one of the things that Michael said is it talked about codec avatar technology. So let me explain, spend a few slides explaining what is a codec avatar. And to explain this, I think I need to frame a little bit what problem we are trying to solve. So let's say we're going to communicate to people, right? These people are separated by some distance. They're going to put these two lines to reference this. Okay, so the first thing we're going to be doing for now, this is what the technology we have now, is give them a headset. And now we need to put some sensors in the headset. So you can see here we put some cameras. These cameras can see parts of the face, the eyes, the mouth, etc., parts of the body too, right? And when you look at the receiver side, let's consider the right side, the receiver, this is what we want to display. We want to display two videos, one for each side, left and right, and also binaural audio, right? So very quickly identify some of the challenges here, right? So the first one is what the sensors measure on the transmitter side is very, very different from what actually needs to be displayed on the receiver side, right? That's the first big difference. So this is, we're going to call this a lack of symmetry. And that makes it very different from, for instance, telephone or video calling. In telephone video calling, wherever the microphone gets is what we need to reproduce on the other side. Here is not the case. The second big difference I'm going to lay out here is we need to produce, we need to render views that are relative to the receiver position. So the receiver is going to be moving through the environment, through a virtual environment in this case, and then we need to be able to render on that view. And that means also rendering things that the sensors cannot see. So look at, in this case, in this final image, we are rendering the back of the avatar, but there is no sensor on the transmitter side that can see that. So there has to be a little bit of, let's call it hallucination, or some way to complete the missing information. Okay, that poses the problem. And now with that in mind, let me describe what is codec avatars. So again, we have a transmitter and a receiver. We're going to put some sensors on the transmitter side. This is, we already talked about this. This is the type of information that we'll be collecting. And now we're going to send this through some encoder function. And I'll describe this one in more detail. This encoder will take this info, so some version of it, transform it, and then send a code. And on the receiver side, already explained what we need to display. These two egocentric videos and the binaural audio. So we need to add something else. We need to add a sensor that can measure where we are in the, sorry, I'm always one frame behind. We need to add a sensor to measure where we are in the relative to the environment. And the final piece is what we call a decoder. A decoder is going to take the transmitter information, is going to take the position of the head and the receiver's end on the virtual environment, and needs to be able to produce this video. Okay, so with that said, this is basically the definition that we have for codec avatars. It's these two functions, encoder and decoder, that are able to enable these telepresence systems. So now I'm going to explain piece by piece what these functions do exactly. So starting with the decoder. So again, this is a function that the goal is to render a video for the left and right eye of the avatar, also binaural audio. And then the inputs are going to be the transmitter state, which I try to put in this diagram. So this transformation of sensors through the encoder that give you a code, that's the transmitter state, as well as the position of the receiver in the virtual environment. Okay, so what kind of function can generate this? You can think this, if you want to solve this, you could do brute force, right? This could be, oh, sorry, I missed one step here. This might be a little hard to do for every single person in the world. So what we do is personalize this to a specific, to every person. So this decoder function is personalized for every person. Now, if we want to do this, we can apply brute force. So imagine taking the two inputs, again, the viewpoint and the expression, and create this matrix. All we need to do is populate this matrix. If you imagine every row here, what it will contain, for instance, is fixing the view, and they have all possible expressions the avatar can make. Here is another example, right? And the same for the rows, that will be fixing the expression and modifying the viewpoint. So if we can populate this matrix, this would be our decoder function. All we need to do at this point is index. So the transmitter sends the code, that locks the row, the viewpoint locks the column, and then whatever is in that matrix, we just display. We actually built that system. This is the room that we built. We have a few of those, which is like hundreds and hundreds of cameras, all pointing to the center, and then we have a person in the middle making all possible expressions, and it all gets captured. With this system, we can actually populate this matrix, so basically solving it by brute force. This is the type of information that we get, right? And as you can see, there is a lot of detail. We want these details. I want to be able to reproduce every single imperfection we have on the skin or wrinkle in the hair. We want to make sure it's as accurate as possible. There is one piece missing though, and this is discrete. As much as we put as many cameras as we could, there is steps between cameras, so the viewpoints are discrete, and also the expressions are not all possible expressions one can make. So we need something to interpolate this, right? And for this, we use machine learning. So we take this data, right, and we use some machine learning to smooth that out, right? And you know there are many techniques today. We'll talk about a few that are able to do this. One small detail missing here is we cannot directly apply machine learning to this data. We need to teach machine learning something about the 3D world, that there are rotations, and rotation work in the 3D world in some way. There is something about geometry, etc. And that's why we have to do some processing. We take this data, we do some processing, fix geometry on it, put some landmarks to make sure that there is no drift in the geometry. But in the end, the goal is to have 3D geometry for every frame and the texture for every frame. And now with this, all the machine learning needs to do is take expression code, take the view code, as you can see here, and from this, render geometry and texture, and then we use a differentiable renderer to put the two together and create the avatar you see on the right. This allows us to plug in expression codes into this neural network, and then those change both geometry and texture, right? And then can create the can be put together to rasterize the avatar. We can also at the same time change the viewpoint and then have the control on this avatar. We call these drivable avatars. Okay, that's for the decoder. Now, if you look at the encoder, again, going back to this diagram, we're going to be focusing on this part here, right? So we need to produce a code that the decoder can use as expression code. So how do we do this? I mean, let me explain what this problem we're trying to solve. We need to map the images from the headset, the video on the headset on the left, to something that produces a code such that the decoder can rasterize an image of an avatar that has the same expression. Right? That's the optimization we try to solve. So to understand this, I'm going to play back this video, but before, let me explain what this is. So we are going to be seeing RGB images here. The RGB images is the output of a decoder. When given a code, the decoder will produce an image with that expression code. And the purple images are the ones captured by the headset. Those are real images. So everything RGB is fully synthesized. Everything in pink is real images captured from the headset. So the idea is the two should match, except for the domain difference of the color, the expression and the geometry of both should match. So what we do is we have a neural network function that will take the sensor images, combine them and produce a code that can be random at the beginning. And then we are going to send the code to the decoder, and then we're going to call the decoder multiple times for every viewpoint where each of these cameras is. And we need to make sure they match, right? So after optimizing, this is the process that we get, right? As you can see, it's not quite perfect, but both images, at least in terms of expression, they match closely, right? And that's the goal, and that's how we optimize the encoder. Okay, so we put this together, put here some references. This was 5 years ago, and this is kind of the result we could get. Now we could have conversations in virtual reality between with their avatars between two people, as you can see here. So this type of avatars that you see here were being rendered using geometry and texture, right? And we've made some changes to make them look better. And that's what we're gonna be showing this slide, right? So one of the big changes we make is make volumetric avatars. This is basically taking advantage of neural fields, right? And what we do is we use ray matching. We have the network to output different cubes with information of the volume that cube contains. And we have these cubes to be matching and tracking parts of the face. And then we finally use ray matching to complete the scene. And the results of this is we have, you can see in this video, we have a lot more realistic avatars. One of the things that this technology works a lot better is in places where the geometry is not as well defined as in other parts of the face. For instance, the hair or the inner mouth, this type of technology works a lot better. Okay, so with that said, you're still seeing all I have been showing so far is just heads, right? So let's talk about bodies. The body solution is very similar. There's not much to say here other than we have a bigger room. So this room now can accommodate full person, and then we can see everything, including the legs. So we do captures here, and then we almost repeat the same process, right? And here's an example of it, right? So the code now contains information about the full body, the face, also the hands, and then the neural network basically has to output more pieces of it, right? It outputs, all these pieces of the body, and then there is a differentiable renderer that puts all together. The fact that this differentiable is important because they allow us to optimize the end-to-end, comparing against the real images that we collect in these capture systems. And the avatar you see on the video playback that you see on the right, it was fully synthesized. Okay, so that's about the basic technology. So at least to give you an idea the work that we've been doing for a few years. There is one part that I haven't talked, which is the shared space. How we now connect everything into one space, right? And for this, I'm not going to go much in detail. I mean, we use also neural fields. There are a couple components that we use. One that is more static about geometry, and we pre-compute all that to make it run real fast. And there is another one that is view dependent to model the light that we have to compute online. And we also need to make it fast to run real time. So if you want to know more about this, there was a presentation in SIGGRAPH this year by one of my peers, Michael Solhofer, which he has a YouTube video I recommend to watch. So this is the type of result that we get with our technology on neural fields, right? As you can see, you're seeing a video, somebody wearing the headset, moving around a virtual environment, and it's photorealistic. Pay attention to everything that is view dependent. For instance, the reflections on the floor, on the TV, this is all reproduced with very high fidelity, which is the intention. And yet, here's another example. You see on the bottom left, Michael, again, my peer, walking through the environment, exploring one of our capture rooms, which is being synthesized with this technology. So now let's put it all together. And you're going to see problems, right? If we take our avatars and then we take our photorealistic environments, we put it together, something doesn't match, right? There are a couple points that we need to be careful with. One is the lighting. So on the avatar on the left, you can see that the asset in this case doesn't really match the environment because the lighting that we used to capture him in the capture room doesn't match that synthetic room, right? And on the right, we try to make match the occlusion, but the point is the decoder needs to be aware of the environment to be able to rasterize these avatars properly. So we're going to fix this. We're going to color the environment. And then to be more specific, this was our function before. The decoder had the expression and the viewpoint as two axes of inputs. Now we also need to add lighting. Highlighted here in yellow. So we have this cube now, right? We have like 3 main axes that our decoder we need to index from. And what we did is add lighting to our capture rooms. Now we have a lot of controllable lights. We know the 3D position of every light. This is very important for the definition process. We need to know where the light comes from. And you can see in the middle is the image that we get when we turn on all the lights. So we alternate some frames with all the lights on. And then some frames only have one control light on, right? And then that's the image you see on the right. And this combination of information will allow us to make train models that have this additional dimension that we can control. I put some reference here, but the important part now is that with these decoders, we can control the light. We can do 2 things. We can have one light and then move around the environment. We can also add a full environment, RGB lighting environment, as you see on the right, and then render the avatar matching that lighting. And you can see how much of a difference it makes. So to grab this part, this is our base network technology. All we did is add the environment. So now we can control also the environment. We can also control the expression code at the same time, and then we can also change the viewpoint. These all 3 axes independently can be controlled for the decoder. And we have year and a half ago, we did a real-time demo where you can see one of our avatars, and with one of the Quest controllers, we can change the light, and you can see how we can model really well the near-field effects of lighting, as well as shadows and other effects. Even the refraction of the light on the eyes is also being modeled quite accurately. Okay, so that's basically what is codec avatars, right? Is this technology that, given a set of sensors, right, we can pass this to an encoder that will give us a code. And now with the code, the transmitted code, as well as the viewpoint and the environment, we put all together. We can render geometry, some sort of geometry and texture. In the case of volumetric, this is more implicit model, but it's still similar. There is a geometry and texture. And we can render the final avatar. With that said, I think I'm going to play another video that has sound. So this is this interview that few seconds of this. So maybe it's enough for you to go and watch this video on YouTube. But that's kind of the type of technology. This is only the beginning. Now you can imagine this can be extended to other AIs, right? Imagine that now you can work, for instance, have teams of engineers with some of the engineers are AIs, and then they have full body, and then you can actually ask them questions or have them as part of your team. I mean, there's many possibilities. Or we have this this meeting we're having here today, and have some people sitting in some of these seats that are remote, but are part of the audience, right? Anyway, there are. You watch this presentation, they go over a lot of topics surrounding this area. So what's next? So what we're trying to do now is make sure all of you can enjoy this technology, right? So we're trying to scale this. I'm not going to go a lot in detail in this, but here's some reference to read. But the idea is that you can take a picture of yourself or do a quick scan with a cell phone. Now we have universal models trained with many identities, and we can actually kind of fine tune or adapt to how your or condition the images that you capture for your avatar and create very quickly avatars for yourself. Here's another example of many avatars created this way. So we have improved over this. So this is the results were from a year ago. Obviously, these avatars don't look as good as the one you've seen, but the idea is to work on this, make it scalable, and narrow the gap between the non-scalable technology to this one. So let me then wrap up here. So I'm going to say that myself, like many of you, live far from some family members and friends. And I think I already pointed out how I think video calling is not enough. So the experience that we have when we do video calling is detached or different from what we have in person. So there is a need to close that gap, right? So I'm looking forward for some sort of technology that enables this remote communication in such a way that is indistinguishable from in-person communication, or at least narrow that gap as much as possible, right? And then I believe this is possible. I show a few things in this presentation. I believe telepresence will be probably the technology that will narrow the gap. We already talked about codec avatars and some of the things we've done to make them more realistic. I think photorealism is going to be very important for this. And finally, I think it's important that we bring this technology for everyone to use, right? So this is the scalable part that we're working on. And with that, I just want to thank my peers and the diverse team that we have working on this. There's a lot of people on this, and thank you for listening to the presentation.
So I just want to start by saying that this was an amazing talk. Thank you so much. It was impressive. And I love the way that you connect all the research you've done to the practice. So I think it was amazing talk. Thank you so much for being here and presenting to us.
Thank you.
So I have a quick question. I want to know like your thinking and general methods thinking about like haptics in this context, right? So I mean, I know it's a bit out of box of what you just mentioned, but I would be interested to hear your opinion.
Yeah, it's not out of box. It's just the haptics is very, very hard, right? So if you have the controllers, you can already enjoy certain applications. For instance, if you try the table tennis game, where the haptics is so good that almost you feel right there. You can almost do the same kind of feeling and gestures that you would do in real life. But you have to wear something, like in this case, a controller, right? So there is research, published research, also on gloves, that you can use a glove, and then you can have a lot more detailed sensing, all along the hand. But I think this technology still has a way to go. It's these practical limitations and mechanical limitations to make this, something that everyone can experience.
Is it if you can share, is the direction that your company is thinking of?
That's an important part. We're looking into this.
Okay.
Can you talk a little bit more about, you showed a couple of examples where it was not just doing face, but full body reconstruction. When you're doing that live, I mean, it made sense to me how you could do that with the facial reconstruction, because you have a few different viewpoints that you get live. Can you talk a little bit more about the process for doing the full body reconstruction?
It's very similar, right? It's, I mean, maybe there are some factors that make it more difficult. Maybe that's what you're thinking about, like there is clothing, and then you can change your clothes, appearance, etc. But in terms of viewpoint, right, it's the same. We capture images all 360 in all possible directions. Right?
I mean, like, yeah, not for the initial data set. I mean, I want to run this live. I want to be able to understand that I'm sitting here with just the headset on. Are you mounting downward facing cameras? What are we doing?
So you're asking about the sensing of your position with the headset cameras, because they are not, we have cameras looking down, so you'll be able to see parts of your body. Obviously not everything. You have some, if you take your hands and put them on the back, that's not there. So we need to do something with this, something plausible, right? But not necessarily accurate, but at least when there is sensor data. So the key thing here is the encoder needs to take whatever information is available from the site, right? And then do the best it's possible to transmit information to the decoder. And it's part of the decoder to make that plausible, to make it as realistic as possible. Ideally, matching exactly, but when there is no sensing, you cannot do anything. If you have one leg cover or something and you cannot see, that's the problem. We have cameras looking down, so you'll be able to see, quite a lot, right? But not everything. Okay, that's a good question.
I'll show you this part. First got a little bit. I'm wondering if there's any ideas on how you might render some object and show it to that person via
Yeah, how you share objects in the virtual environment or pass them along. Yeah, all that type of interaction. That's open research. That's also very hard. I mean, the hope is like some of the talks here we've been discussing about how teleoperate, right, and how we have robots. I think it has some similarities with this. I think this part is very hard, especially. Somebody asked about, I think you asked about haptics. Without haptics, right? Unless you're wearing some control, it's even harder. Right? You don't get to, to feel, right? But yeah, good question. Yeah, that's open research.
So last question.
So question about the problem of delay in your context. Like in this multiverse, let's call it. So when you, for example, in this virtual reality or augmented reality, and then there is a delay between us. So your interaction in your world and my world is basically doesn't exist in the same time axis, right? In your world, you may, I don't know, throw this at me, and in the other world, I mean, you hit me, and the other way, I have already moved, right? So is there, do you think there would be a kind of predictive modeling, something that can take care of it, or this is the direction that people should think of?
Yeah, I'm gonna get that back to you almost, right? But how is that different from telephone or video calling? So in video calling, you have the same problem. Like when there is lag in the network, then yeah, there are multiple options. Most of them just freeze because there is nothing to show, right? Is it worth doing, faking something about how the future could look like? I don't know. Maybe the best point there is just there's no communication, just freeze it. That would be more application specific. I'm gonna say like this: the bandwidth here is a lot less than with video calling. We don't transmit the video. There's a neural network compressing all the transmitter state into a small code. I think we have 200 values or something. It's not that much. So it's very, very small bandwidth, a lot less. So the hope is it's going to be less affected by bandwidth of the network than video calling. But maybe like telephone will be the thing. But yeah, no, that's a good question. I mean, probably freezing is the best answer at this point if there is no communication.
Yeah, I mean, the 5G and 6G, I mean, that can also be a direction. Great, thank you so much.
Let's thank the speaker again. Thank you.
Just a second, yeah.
Okay, thanks for your patience. It's my pleasure to introduce our next speaker. Giuseppe Loiano is assistant professor at the New York University and director of the Agile Robotics and Perception Lab. And before he was at NYU, he did a lot of great work at the GRASP Lab at UPenn, a lot with Agile flight and multi-robot systems, and he's continued those research areas at NYU. He's the recipient of many awards from NSF and DARPA and many others, and is the author of more than 70 papers. And it's my pleasure to have him at our workshop.
So thank you very much, Jeff, and the organizer for the invitation and the introduction. And, our work is mostly on the robot autonomy, and we focus mostly on drones. But today I'm going to basically give you an overview of how we try to couple that with the mixed reality interfaces for enhancing spatial awareness and interactive navigation of both the human and the robots. So before we go into the details, I just want to give a quick introduction, about the lab. We're around the New York University. We're about, 10, 11 PhD students, plus several researchers and postdoc. And today in particular, I'm going to focus on the work of Luca, who is a postdoc in my lab, and Sanket, who is, a researcher, just finished his master and decided to stay in my lab. We have also several master students that, contributed to the things that you're going to see that gives a lot of support from an engineering perspective. And most of the tests you're going to see are realized in this facility. So we have a full indoor motion capture system with Vicon, and then we have also 3,000 square feet indoor arena for testing our navigation pipeline, as well as the experiment you're going to see that we have human and robots collaborating together through mixed reality. So where is the opportunity? So there are several areas that really need strong collaboration between human and robot. And this is very clear, especially in the mobile robotics area, and not only, in other areas like manipulation or healthcare and so on. So we have search and rescue scenario, emergency response, where a robot needs to go inside, but there needs also to be the possibility for a human to actually have a great interface with the robot and understand not only the robot, what is the robot seeing, but feel part basically of the experience and of the environment for better interactions with the task, and to possibly solve the task faster. There is evidence that, in the next couple of years, we're going to have an explosion of warehouse automations, where basically human and robot will start to collaborate together in a seamless manner. You need to think about shelves where, you will have drones, you will have ground robots, and you will have humans that need to find ways to interact with these machines, both from a physical perspective, but also from a cognitive one. And then if you see the industrial revolution, you clearly see that, we started from mechanization, we went to mass production, and people think that, the industry 4.0 is just the end. But in reality, industry 4.0 was just systems that were basically interconnected and exchanging information. There was very little, robotics in those systems, except, these were considered, pretty much entities that were connected on the network and were exchanging data to solve mostly repetitive tasks, like in automotive industries, or with some level of flexibility in the way the task could be redefined and reshaped. While in the industry 5.0, we really look to have a human-robot collaboration, cognitive system, customization in the way that the human can interact in a seamless way, but can also, the machine should provide the right level of flexibility according to the human needs and the type of task that the human would like to basically execute. So what are you can see that this is, other typical areas are, for example, the area of collaborative construction. There is a lack of manpower in this area, and it's really needed, the ability to have machines that physically interact with the human, but potentially from another location. So there is the need of basically let the human feel the experience of interacting with the robot, but not, in direct physical contact with the machine, just for safety reasons and purposes. So what are really the needs and challenges, I would say? We need increased safety intuition and possibly faster execution that this kind of, novel interface needs to enable. We need human-robot remote and safe with interaction feeling. So we really, for example, in this kind of task where you have a clear interaction, you really need, potentially have the person in another room and experience the same kind of feeling of, physical interacting with the load in this kind of construction task. And then we need exactly to have increased, we need to increase, the human and robot each other awareness, I would say. And the other one that's a little bit down is that I just want to mention that we need to basically elevate this kind of machines to teammates. They cannot be anymore just provider of a specific service. So what are the challenges to go over there? We should go if you see a little bit what has been done in this area, certainly you see some tactile interface, you see some joystick. And these are, the initial system where you still had some kind of basic interaction that was following the command and control, let's say, paradigm. And we certainly want to go beyond that. We want to go beyond the simple teleoperation. And if you think about drones, there is also another problem. Many times to operate this machine, you need expert pilot. So the idea is to really go beyond, the need of expert pilot and have intuitive and easy interface that really is the process of interactions with the robot. And, we need also to think about the robot safety as well, and not only about the human safety. And in addition to that, you have this field has kind of evolved. People have started to use, mixed reality or virtual reality in this kind of, mobile robotic task. And mostly it has been done is, reproject very simple task, for example, reprojection of a map or of a drone view in the user field of view, or basically, merging satellite maps and robot maps in a sort of mini map representation for the user. So what did we propose recently? And this is something we just submitted. It's basically a novel teleimmersive framework for spatial visual interactions and navigation between an aerial robot and the human using mixed reality. So we have basically an alignment of representation in terms of, bidirectional spatial, that allows bidirectional spatial awareness. You can see here that we have an egocentric representation. We have also an exocentric representation of the environment, combining both human and robot maps. And at this level, there is also the possibility to customize, so it gives the right level of flexibility that I was mentioning. So customize the type of environment according to the human and robot needs. So you can potentially add on top of this representation also virtual object and virtual element that gets added according to the task, keeping the level of safety that is required, because you basically have objects that are, just virtual object, but you can use those to actually verify that your system is working. We'll see a type later of multimodal virtual physical interaction where we actually embed basically an admittance control into this system to provide assisted navigation to the human. And then, there is, I was mentioning this level of environment customization that is provided to the user and the robot. And I want to say that, it's not only the user that receives that, this pipeline is bidirectional. So both the human and robot have the ability to have this kind of view. We have different level of abstractions, so according to the need. For example, for a navigation task, an octomap may be sufficient, but maybe if you want the reconstruction of the environment, you need the mesh. So these are also provided internally, and we bridge basically physical and virtual world together. For example, in this case, the user is basically enabling can command basically the drone in another room. So it's basically in an adjacent room. There is a wall in between. Thanks to the use of mixed reality, it's able to go beyond the line of sight. To give you an idea of does this work, basically, we merge basically different representation from the point, we merge the point cloud of the HoloLens and of HoloLens 2 and of our drone as a visual inertial odometry system, and then we build the representation different level of abstraction, like we can have an octomap, or we can have also basically the mesh of the environment. Then at this point, once you have this kind of representation, what kind of things can you start doing? So, for example, expert pilot generally command the drone using a joystick, or directly providing low-level control to the drone, which is kind of difficult for a person that has never interacted with this kind of robot. So the person basically has a minimap view of the environment. They have a merged map together. And what happened at this point is that the person, it's the most intuitive thing that can start to draw a trajectory in the minimap. And it's expected that the drones will follow this trajectory, which is kind of what's happening in this case. So we have, we provide this assisted navigation characteristic and framework, but there is one problem. So the environment might be unknown, so the user may go through part of unknown environment when it's describing the trajectory, and then the user is not gonna say, okay, let me draw the trajectory over here so that it's free space compared to other area where it's occupied. The user simply wants to do a trajectory, and the drone needs to basically execute it. So what happens in this case, and you're going to see a little bit the details, is that the user may plan a trajectory which may also go through obstacles, but then at the bottom there is a planner that's taking care, based on the trajectory of the user, to define a new trajectory that's as close as possible according to some metric to the one defined by the user, but it's basically avoiding the obstacles in the environment. This could be very useful, for example, in search and rescue scenario, or in collaborative manufacturing or warehouse automation, where the user needs to define a task. Meanwhile, it's basically in another room. So this is basically the entire architecture. So our platform is completely autonomous. So it's mapping the entire environment. On the other end, you see that we have the HoloLens 2, and we use some of the functionality that are provided also by the HoloLens interface. So we have an hologram visualization, a mapping, and an hologram interaction. And on the other side, we have the classic framework, autonomy framework of a drone that's based on the mapping system, localization, common visual inertial odometry, and then planning techniques where most of the innovation is. So to give you a brief overview, and then I want to show a video just to make it a little bit more interactive, is basically what happens. So the user basically defines this kind of trajectory. This trajectory is subsampled, and actually before it's subsampled, it's scaled to the minimap. From the minimap to the real scale, from the minimap to the real world. And then once that happens, basically there is a planner that's acting on top of the trajectory to ensure that basically the trajectory the path of the robot avoid the obstacle, while concurrently being as close as possible to the user-defined path. These are some of the mapping of the entire. You saw the lab that I've shown you, the 3,000 square feet. This is actually the 3,000 square feet, plus we have the corridors actually on the side, the hallway, and you can see that this is the human trajectory, this is the robot trajectory, and basically map are merged together. This is what happens basically in real time. There is a user working in the hallway. The robot is basically already in the room. They aligned their system, and this is the combined map and this is the one from the Vox block from the robot directly. And you can see that this is the process of the user defining the minimap. So the user define basically a trajectory, can be either a trajectory or a goal, and then after that, basically after this type of interaction, the trajectory will go through the obstacles, and you can clearly see that the robot is actually assisted by the planner to not execute exactly the trajectory that the human prescribed, but to be as close as possible while avoiding the obstacle in the environment. This pretty much works in real time, so you can see it was lots also of integration effort that was done to make the framework also compatible with the drone, ROS, and so on. So that's That's pretty much the idea. Then we can go toward the end. I'm just going to speed it up. And that's when, there is the, you see these is defining waypoints. And then based on these waypoints, basically those are scaled and the trajectory is generated. And this is the case that the robot is going around and it's flying while avoiding obstacles thanks to the element planner. The person on the back is just a safety pilot, just to avoid any let's say any disaster with the drone. Let's put it this way. And so this is kind of an assisted level of navigation, but the question is, can we do more? Can we give the human the real feeling of the interaction between the robot and with the robot using this kind of mixed reality interface? So we basically, provide two additional ways of interacting. One is called free physical virtual interaction, and the other one is assisted physical virtual interaction. This is really the human now is in the loop, is not generating simply a trajectory anymore. And in the first one, we're going to see that this is enabled through an admittance controller, where, that's driven by the human force, which is proportional basically to the distance from the current marker to the one that the human would like the robot to move to. And, so there's going to be two. In the first modality, what happens? Basically, the robot is free to move according to the human intent and motion. But we need to provide a safety layer in case of obstacles. So there is a repulsive force as soon as the human is trying to basically drive the robot into an obstacle. In the second one, actually, this will be very interesting. So this force is disabled, but pretty much the admittance controller works on top of a planner. So we have a variable admittance controller. The planner runs. The human can still decide, how much he wants to pull the robot from the original trajectory. So, for example, the robot needs to go from PSI -1 to PSI because that's its original path. But at the same time, on top of this trajectory, there is an admittance controller that allows basically the user to pull the robot from the original path and allow some kind of interaction if compatible with the safety of the path, with the safety of the planner, basically. So that's the idea. So we'll see basically that there is a damping-based physical virtual force feedback, there is an obstacle physical virtual force feedback, and there is a planner based on physical virtual force feedback. So you can see in this case, this is the FPVI, so it's the free interaction. You can see how the forces go and how these modify, thanks to the admittance controller, the different position of the robot. And while exploring, basically, a repulsive force is always active from the observed obstacles. This repulsive force, as I mentioned, prevent the user to collide into the obstacles with the robot. And the MR basically also enabled the user to see through obstacles. Eventually, it's needed. And here you can see more in in real time. So that does it work. We have a classic admittance controller, which is based on the force input that's given by the user, and this is the sum of the force of the user plus the repulsive force that's taken care from the obstacle environment to avoid the user collides into the obstacles. And in this case, the repulsive force, just to focus on that, is basically the repulsive force for each voxel, and then all of them gets combined. And once this gets combined, you basically can generate a trajectory that, are going to go around the obstacle, but not going to feel inside. And this is, we have an exponential decay. So you have more force as closer you are basically to the obstacles. In the second case, we have so in the second case, actually the repulsive force is disabled, and we'll only have the user force. That's why here it's still active, but I just put this just to focus on the repulsive force. So the idea here is that, you have a planner. The planner might be an RRT or any type of planner you may like. And basically, this is driving the robot from S0 to Sn. but you know that you want to leave some kind of freedom to the user to interact with the drone in case, you know, you want, for example, to explore some specific area around the path, or you want to turn the robot to get some specific viewpoint of the environment. So how do we do that? We basically, on top of the RRT, we implement basically the same admittance controller, and with a variable admittance controller. Actually, this is a function of the angle that's given between the pulling force of the user and the original trajectory of the robot. You can define this D according to different ways, but I think we define an exponential way if I'm correct. And you know, this has been proposed a lot in the industrial manipulator, but has never been, you know, really implemented in a really, formulated in robotic system working in a structured type of environment. So this is the thing. So now the user can basically interact. And, you know, if it doesn't interact, the robot goes to its original goal. If it interacts, it tries to be far away from the original trajectory. If the safety margin of the planner are respected. So the user can move basically the robot if it also respect basically the safety layer that's provided by the planner. So we really have, in this case, that, you know, the user is literally feeling the experience basically of interacting physically through a mixed reality interface with the robot, while the robot is also has an autonomy pipeline to go to the final goal. And you can see that this is the case. For example, this is the goal, the user, this is the original RRT, and the user can basically interact with this system, and these are some more results. So you can see that there is a, you know, for example, it's preventing to go into obstacles. The planner has already defined some set points, and then, you know, in this case, you don't need the repulsive force that I had in the free navigation, because the planner itself is taking care to avoid obstacles, and then the admittance controller just gives some margin around the trajectory, the original trajectory of the robot. And this, you can see some videos. So you can see that the planner is acting, but there is also the user that's, you know, deciding to, at some point, define a new path to go through the area. And, you know, if there is you know, at some point you can also disable, if you want, the APVI and go in FPVI mode. But the idea is that, you know, the user can do whatever he or she wants, compatibly with the safety of the region. And when it's come back, you know, the planner is restarting its expansion and so on. So just to give you an idea about, you know, what so this basically, it's clearly bridging, you know, the physical and the virtual world. The user is capable of directly experience the force feeling during the interactions, despite not being even in the same room, and despite, you know, not even feeling that there is an additional layer of planning that's provided for safety to the robot. So this both increase the robot safety, but also the human safety at the same time. So I just presented basically a teleimmersive XR framework for spatial virtual physical navigation and interaction with an aerial robot via mixed reality. I think the key element were, you know, bidirectional spatial awareness, the ability to have, you know, aligned representation that were, you know, understandable and interpretable, both from the human perspective and the robot perspective. There was a multimodal virtual physical interactions that, you know, enable to understand the feeling, enable the user to get the feeling during the interaction with the robot that was not only physical, but also visual. And then we went for sure beyond the command and control solution. I think there is lots of potential in this area, especially with, you know, the new XR technologies that are coming out to integrate robotics in this kind of system, to speed up the task, to improve the user experience, and also to make the user more comfortable during the navigation, the co-navigation task with the robot. And especially, I know I can see, you know, human robot teammates really working in search and rescue scenario, and also in warehouse automation problem. I think there is the need of extended use case study to compare, classic interaction with MR solution. Like in this case, we're performing user case study. Actually, that's a collaboration with Farokh, where we try different types of interfaces, and we also try different types of visualization that are provided to the user to see which one makes the user more comfortable, and if it's, also a good one for the robot. There is, to ensure that there is no human overload. I think that's something that's underestimated. So we want to make the task as possible as relaxed for the human. And I think there is the need to scale this to multiple human and multiple robot. I think that will be an interesting future avenue, and to combine, different sensing modalities. Right now we combine, some kinds of touch with the visual, but, you can combine voice, audio, and other types of modalities for increased collaboration. And that's pretty much all, and I'm happy to get questions if any.
We have time for a couple of questions from the audience, if anyone here wants to ask.
So that is so we did that, and that's part also of the user case study that we are doing. The problem of the velocity commands, that depending on the type of gains that you use and so on, that becomes very sensitive to the user. And some of them feel that, they may lose the control of the robot and not get it back on time. So that is what we notice. But definitely it's an option that you can, the system allows. Hopefully, in a bit of time, if the paper, gets out, we'll release also the entire framework. We'll open source it basically, so whoever wants to use it is able to use it. But that's what we basically experience. That's a modality that's available, but that's not the one that a user prefer. If you are a pilot or an assisted pilot, then you may want to use that with your joystick, and that makes the pilot more comfortable. But for someone that has no experience, that's basically one of the major goals of this work. It's not the most preferred one, actually. Yes, please. So that's something we're adding. Right now, the admittance control is simply based, on the forces proportional to the distance that the user is moving. So there is not really the user can interpret from the visual and from the marker. Let's put it this way. But we are using now basically a telehaptic interface system with Farokh has been integrated into this framework, and we're seeing that we're making actually part of the studies that if you use it or not use it, does it make a difference? And so we just finished all the data collection. We had over 20 people that had from no experience to a little of experience with the system. Basically, we're just explaining them the task that was to go through the other side of the room with the interface. And there are some interesting results that we're gonna show. Yes. Yes.
I think one more question in the back corner.
Great, so that can be done in different ways. So the first way is that the user is actually going with the marker and initializing the system directly on the drone that's on the ground. So it's spatially aligning the HoloLens frame with the frame of the drone at the beginning. The other way is, to use the classic techniques of image matching to find basically for localization of visual place recognition, and then compute the transformations. That's another option. And then Microsoft has also a nice framework to basically, once that's based on that, basically that using different images, you can basically from different devices, you can basically align the spatial frames. But in most of the experiments, to make the process easy also for the user, where just the user was, was having also fun. There was people that never used it, go there, they put the marker, and then they leave this. Okay, thank you very much.
Thanks. Thank
To the 3.
6, 7, 8.
Thank you. Can everyone hear me? Yes, okay, great. Hello, everyone. Thank you all for joining this presentation. So welcome to this workshop presentation on a 3D mixed reality interface for human-robot teaming. This is a joint work between me, Boyang Sun, Mark Poliface, and Herman Bloom. So let's get started. We begin by giving some context to the problem. So imagine you're a first responder in a search and rescue scenario, and you want to command a robot into the field to assess the damages. And you need to command the robot
so
while maintaining situational awareness.
Presentation now before the coffee break.
We present our
the first poster is by Julia Chen, and the topic of the paper is a 3D mixed reality interface for human-robot teaming.
Interface
so Julia, if you hear us, the stage is yours.
Through drag and drop. Can everyone hear me in real time? So on the left here, we see an operator controlling the robot in the field using a hologram in a mixed reality device. Hello, everyone. Thank you all for joining this presentation. And on the right, so welcome to this workshop presentation on a 3D mixed reality interface for human-robot teaming. This is a joint work between me, Boyang Sun, Mark Poliface, and Herman Bloom. Real-life scale to truly have spatial understanding. Let's get started. We also present a virtual map overlay that we begin by giving some context to the problem. So imagine you're a first responder in a search and rescue scenario, and you want to command a robot into the field to assess the damages. And you need to command the robot while maintaining situational awareness. And we present, therefore, we present our mixed reality human-robot interface, which has two main features. And the first of which is a mini-map interface for remotely controlling a robot through drag and drop behind the curtain in a map that updates in real time. So on the left here, we see an operator controlling the robot in the field using a hologram in a mixed reality device, which here is the HoloLens 2 limitation. And on the right, we see the robot, to control the robots on moving to the goalpost specified by the human operator just a moment before. And the top right shows and since you also need to have visuals about the environment in a real-life scale to truly have spatial understanding, we also present a virtual map overlay that accurately overlays this virtual map from the robot onto the real world. So here, effectively, the operator wearing the mixed reality device can see through walls and have a better understanding of occluded scenes, for example. So on the right here, we see the first-person perspective from the operator as they step behind a curtain, and the curtain should occlude the entire scene behind it, but with the overlay visualization, the operator can still see what's behind the curtain and get an idea of where the robot is and what's happening inside the environment. There are a couple of prior we wanted to build a system such as this because other robot control interfaces face limitations such as only being able to control the robots on a 2D plane. The works on the right here show that the robots can only operate in 2D planes, and the top right shows a map overlay that is also just a 2D plane, some occupancy map. Another limitation is surroundings, and not being able to command the robot to locations outside of the line of sight. So the bottom right images, or the bottom images show the operator controlling the robot with waypoints that must be set in physical 3D space. So here you see the waypoints, and the robot executes the trajectory along the waypoints. However, whereas we would like to have a human-robot teaming interface that can move robots around in 3D space and be able to control them without having to be in the same physical location. And this brings me to the methodologies. So additionally, with regards to visualizing the 3D map created by the robot, there are a couple of prior works exploring the idea of seeing through walls with mixed reality, and they have shown really nice applications of it, but they either need an initial external or manual alignment step, such as the work on the top, or they are not a mixed reality interface, such as a VR interface on the bottom. And this thereby limits the operator's own spatial awareness in their own immediate surroundings. And in our system, we do not require an initial alignment step, as the robots in mixed reality device use visual registration to co-localize. Additionally, we use a mixed reality interface, which still allows operators to be grounded in reality. However, nevertheless, these prior works all show the potential for using AR or VR as an interface for human-robot teaming, which we hope to further improve with our work. Then let's operators send goal poses. And this brings me to the methodologies, where we check if the pose is viable. The entry point into our system using the dense where the devices each send their sensor data, such as IMU, odometry, and images, to a local mapping system. These local submaps then get sent to a central server, where they get accurately registered through visual registration into a global frame of reference. So now we basically know where the HoloLens and the robots are with respect to each other. And here we mentioned that our visual SLAM system is mainly built off of MATLAB 2.0, which is a really nice real-time multi-agent SLAM system into which we could integrate the HoloLens. And the output of the server is an SDF, the robot and HoloLens device poses, as well as a point cloud representation of the global map. To get a better global map representation, the point cloud and poses then get sent to our mixed reality device, where we are able to visualize and overlay. And also the robot control mini-map interface then lets operators send goal poses to a planning system, where we check if the pose is viable and then plan a trajectory using the dense reconstruction from the mapping server. And finally, this path gets executed by the robot. Oh, sorry, before I go into so now we go into a bit more detail about the mixed reality interface. The main idea of this overlay mode is and on the left here we show the overlay mode, spaces, and this is enabled by the real-time visual SLAM we are running in the background. At a curtain, because we need an accurate transform between the global map frame and our HoloLens visualization frame. This is why it was important to have the real-time visual SLAM in the system, such that the HoloLens and robot agents are continuously being co-localized in real time and simultaneously. The mapping server continuously optimizes the transformations between submaps from different devices to get a better global map representation, and submaps are also continuously sent as the devices move around in the environment. It is also worth mentioning that we are also able to incorporate as many robots into the system as we like, but we were limited in both hardware and compute. Now on the right, we see the mini-map. We still need to give mode a trajectory to execute. Before I go into the mini-map mode, I would like to mention that the main idea of this overlay mode is that we are able to basically see into occluded spaces. So once again, here we see that the operator is looking at a curtain, but is able to see the scene behind the curtain with the 3D map being accurately overlaid onto the environment. And now on the right, We show the mini-map mode, and this is again a multi-robot control interface where we can send goal poses to multiple robots in real time and simultaneously build our map of the environment as we send robots to more areas within the environment.
Is to make the
And with a system such as this, operators can
operators don't have to be
have
extremely
spatial awareness,
whether they command a robot
yet still
too closely to a wall.
Sorry, with a system
especially if
such as
there are
this,
narrow
operators
corridors
can be
that are in
remote,
theory
can
still
operate the
traversable.
robots remotely,
And
yet
lastly,
still
once we
have complete
a
spatial
viable
awareness
pose,
of
we
their
find a
own surroundings.
trajectory using an
And
RT
now once the
path
operator
planner,
sets a goal
and then
pose
the
in the
robot
interface,
executes
we still need to give the robot a trajectory to execute, which is why we need a planning system. Which brings me to the next part.
Conducted a user study to test
planning.
the effectiveness of our robot control interface.
So within our path planner, we're able to plan trajectories between 2 points in 3D space. This is because we estimate the ground plane using a surface point cloud, and this allows our operators to command robots in spaces with multiple floors. Additionally, before finding a trajectory, we also introduce a pose viability check. This check will verify the traversability of the given poses. Otherwise, it will try to find a nearby pose for the robot to traverse to. And the purpose of this pose is to make the robot control interface more forgiving. So basically, operators don't have to be extremely precise about whether they command a robot too closely to a wall, especially if there are narrow corridors that are in theory still traversable. And lastly, once we have a viable pose, and note that we find a trajectory using an RT-inspired path planner, and then the robot executes this trajectory.
Shows the user completing
And this concludes the overview of our human-robot teaming system.
The task
in ARVIS. We also conducted a user study to test the effectiveness of our robot control interface.
which potentially
We designed the user
HoloLens
study
an
with 4
advantage
main
in these
tasks.
in
The
terms of
first
speed.
task involves
Now,
moving
as for
one
the
robot
results of our study,
from one location to
tasks
another.
2 to
The
4
second through the fourth task involves moving multiple robots, and the users are asked to move the robots from predefined starting positions to ending positions. The metric we measure here is the time it takes for a user to complete the task.
Additionally, we think that it's possible the equal performance for task 1 could be due to the
we compare
necessity
2
of an
different
additional
interfaces
practice round
in this user study,
the HoloLens.
so ARVIS versus the HoloLens.
Nevertheless,
And on the right, we
regardless
show
of
an
the number of
example with
agents
our
or
task
the amount
4,
of practice,
which
the
is where the
HoloLens
user is
interface
asked to
performs
place all
equally
3
well
robots in the
or
scene
better than the ARVIS
into the kitchen area surrounding the dining
And in
table.
conclusion,
And note that this
we
is a
present
2-story
a
environment, and the robot will plan and
3D
execute
human
trajectories in
robot
3D.
teaming
So the
mixed
top
reality
image shows the user
and this
completing the
mixed
task in the
reality
HoloLens,
interface is
and the bottom
helpful
image
for
shows a user
intuitive
completing the
robot
task
operation
in
and
ARVIS.
spatial
And our
understanding,
intuition is that
which
the
is lacking
ARVIS
in
viewpoint
screen-based
is rather
interfaces, and we
unintuitive
show
to
this
control,
through
which
a user
potentially
study.
gives the HoloLens an advantage in
And
these
in the
tasks
future,
in
we
terms of
hope
speed.
to extend this
Now,
interface
as for
to
the
more
results
complex
of our study,
human-robot teaming tasks such
2
as
to
in the
4
case of search and rescue,
show a statistical
factory
significance
inspection,
in that the
etc.
HoloLens times are faster.
So
We
can
posit that
find
this could be due
this
to
open
tasks
source
2 through
HoloLens
4 involving
application
multiple agents,
online at this
while
GitHub.
task 1
And
only had
we
1
also
robot
have
to be
our,
controlled. Additionally, we think that
paper
it's
available
possible
on
the equal
archive.
performance for task 1 could be due to the necessity of an additional practice round for the HoloLens. Nevertheless, regardless of the number of agents or the amount of practice, the HoloLens interface performs equally well or better than the ARVIS interface. And in conclusion, we present a multi-agent 3D human-robot teaming mixed reality interface. And this mixed reality interface is helpful for intuitive robot operation and spatial understanding, which is lacking in screen-based interfaces, and we show this through our user study. And in the future, we hope to extend this interface to more complex human-robot teaming tasks, such as in the case of search and rescue, factory inspection, etc. So you can find this open source HoloLens application online at this GitHub, and we also have our paper available on archive. And,
So because of the time limit, we are gonna skip the question. Yeah, because of time limit, we're gonna skip the question, but please feel free to approach the, to send an email to the authors and then find the paper here and then find the GitHub information and ask your question. So thank you so much, Julia and authors for presenting at our workshop. So the next speaker for the next poster is Jose Rodriguez. And the topic of the poster is multi-user extended reality interface for telerobotic operation at CERN.
Hello, everyone. I'm Jose Rodriguez Nogueira, and I'm going to present our poster about multi-user extended reality HRI interface for telerobotics in operation at CERN and with collaboration with the Polytechnic University of Madrid. These are the contents that I'm going to talk about. I'll try to be fast. Well, first of all, I'm going to explain why do we have robots at CERN. So at CERN, there are different accelerators and facilities. So to keep these machines working, we need to do inspection, maintenance, and operations of these facilities. And in these experimental areas, there are some kind of risk of contamination and some surprises. So that's why we need robots there. Then every inspection that we do in these harsh and semi-structural environments, we can find different challenges for our robots, like, for example, magnetic disturbances. There are delicate equipment that are not designed for robots, big distances, communication, the short time we have for these interventions, and so on. So in consequence, we have built our robots that they should be very modular to be able to change its architecture, as you can see in the picture on the right. That we have the same base, but we can add different robots and different configurations to each specific task that we have to develop. And we also have some commercial robots like Telemax, Theodore, and in general we have around 20 robots in operation right now. So once we have our robot ready for the intervention, we have to give our operators a good user-friendly interface. So here you have the current user interfaces that we have developed. We have an old one developed in WPF, that it's a 2D GUI, which we have moved to Unity. So now we have everything in Unity, and we have developed this 2D, one 3D, and another one XR, AR user interface. So thanks to move everything to Unity now, we can change from one interface to another one in a very easy way. So what we have done is combining all these 2D, 3D, and AR user interfaces to let the operator move between one and another one, just clicking a button or going to the keyboard, using the HoloLens headset. This also gives the option to do multi-user operations using the same device. So this could be useful for some situations where there is only one device, one laptop, and we need 2 or more users there. Then this is the architecture that we have designed. We have different common modules that, for example, the code and the 3D objects like the robot, the virtual robot arm that we are going to use, that is shared between one user interface and another one. This helps us to add more modules in an easy way. Then the users can interact between each other with verbal communication or gestures, and it's a very flexible and modular HRI. And the last part is once we have developed everything, we have performed some tests in our laboratory, our mockup at CERN. Let's show you the video here. Okay, so first we did a test with one single user. There you can see the setup with the 2D GUI, and we can see the 3D images of the robot. We can enable the point clouds, the cameras, and we can set up everything to do the teleoperation. We can move the robot and moving it on top of the table. We can move the 3D model on the screen. And of course, we can do some task position, movement, or task velocity. Here we develop a multi-user experiment. The first user was moving the robotic base using the 2D GUI. So first, on the video that you can see above, the user was moving the robot until one position, and then the second user was moving the robotic arm with the HoloLens to move the robot in a position where it was looking at this sensor that is a beam loss monitor to take a picture. He was moving the robot in task velocity and in joint by joint, so he could take a picture in the end and finish the test. So in conclusion, we have developed a new multi-user extended reality human-robot interface that we have performed successful experiments, and we have different types of control depending on the operator's preferences. But of course, we have to continue developing new features, new modes of control. We have to optimize the multi-user experience, adding more roles for more different users. And of course, we have to do better tests with more users and perform in experimental conditions. So thank you very much. And if you have questions,
For more questions, please find the poster of the authors. Thanks a lot. And we need to go to the next speaker. So, excuse me. The next speaker is Maiteri Gramopadhi. So sorry for the pronunciation of your name. Please come to the podium. And the topic of the presentation is assessing the impact of virtual reality interface in human-drone interaction. The stage is yours.
Yep, I'm going.
The sharing?
Yes.
Okay.
Hello, everyone. My name is Maitreyi Gramopadhi, and I'm a graduate student at the University of North Carolina at Chapel Hill. Today, I'll be presenting our work on assessing the impact of VR interfaces in human-drone interactions. Drone control is a non-trivial challenge for layman operators. Drone operators, for tasks such as search and rescue, drone photography, spend hours training how to precisely fly the drone. And due to some drones having more than 6 degrees of freedom, there is an abundance of users of information for a user to keep track of. However, some works have explored trying to design more intuitive drone interfaces that may be able to reduce these barriers of entry. Traditional drone interfaces employ joysticks or keyboard controllers coupled with 2D flat screens, whereas some newer methods have explored using technologies such as gesture-based controls and virtual reality or augmented reality interfaces for operating drones. And while it is important to create newer interfaces, it is equally important to test whether these interfaces are actually more useful than the 2D interfaces when we are flying the drone. And we have noticed that in the community, there is a lack of analysis between how well these VR interfaces perform compared to just traditional interfaces. And we aim to bridge this gap in our work. We present two contributions. Firstly, we develop a novel VR interface to control a 6 degree of freedom drone. The interfaces uses tools like joysticks and Oculus Quest 2 that users may already be familiar with. And secondly, we compare our interface with a 2D flat screen interface for drone teleoperation and present a comparative analysis of both the interfaces. For our robot platform and for our experiment, we use the Parrot NFE drone, which is a 6 degree of freedom small size drone with a mono RGB camera mounted on it. We specifically selected this drone because of its small size, which makes it easier to fly indoors. And we designed a virtual reality interface with a cyber physical control room design. We used the Quest 2 as the headset, and after wearing the Quest 2, users will find themselves in the control room that you see here on the slide. They will see a video projected from the drone's camera on the video screen that you see here. The screen is also by default programmed to follow the user's headset so that it always stays in view if the user does want to look around. It is also possible to toggle this function using the Quest controllers and have the screen fixed in just one place. And we also map the controller joysticks to the controller of the drone and operate the drone using the Quest itself. We also use the pass-through feature of the Quest to provide users with a direct line of sight to the drone when they're using the headset. So users get both an egocentric perspective with the drone's camera and an exocentric perspective by observing the drone directly. This video here shows me flying the drone around from inside the interface. So if a user is wearing the Quest 2, they'd see the drone flying around them, and they'll also see a video feed from the drone's camera here. For designing our experiment, we compared our interface with a 2D interface, and the Parrot NFE drone does come with the default 2D interface that is on a mobile phone. It's a mobile phone interface with on-screen joysticks to operate the drone, and the app also shows the video feed from the drone's camera. We performed a within participant study, and so far we have been able to recruit 6 participants by convenience sampling from the UNC Computer Science Department. We asked the users to teleoperate the drone and accomplish a series of tasks. We specifically selected the tasks to assess how precisely are the users able to just fly the drone without any training of any sort.
Here. No, the whole thing is off. Ah, the projector turned off. Okay.
Sorry, noise.
Yeah. Let's click this. Okay. So again.
Yeah, thank you. Yeah, so we asked the users to specifically fly the drone around and try to measure how precisely they can control the drone with minimal training. And through our experiments, we tried to analyze if the VR interface actually reduces the training time required for controlling the drone precisely. We asked each participant to complete 3 tasks with both the interfaces. In the first stage of drone navigation, we asked participants to achieve just the most basic task of following instructions like taking off, flying the drone forward, right, and landing, and without crashing. We just wanted to analyze if they can even accomplish like the basic drone flying task first. In the second stage, we asked participants to achieve an exploration task of taking off and flying the drone across the room to a wall, where they would find a piece of paper with a few digits on it, and we asked them to hover the drone in front of the digits and read the digits back to us. And in the third task of complex, we asked the participants to fly the drone across the room and complete the digit reading task for 4 different papers on 4 different walls. This slide here shows the room where we conducted the experiment, and we also show a top-down view of how the experiment looked like. We made sure that at all times participants were able to see the drone, but they were not able to directly read the digits. And we also selected the font size of the digits so that participants would actually need to have the drone within a meter of the paper to read them. And we expect that the fine-grained positioning and hovering required to complete these tasks would thoroughly evaluate how precisely the users can control the drone. We analyzed the time it took for participants to complete each task, and here are the preliminary results that we have so far. For the first task of drone navigation, so far we haven't noticed that statistically significant result. On average, participants perform slightly better with the 2D interface. However, since it is the first time for many participants interacting with VR, these results could be because they are just more familiar with the mobile phones. With the second task, we have noticed that participants performed much better with the VR interface than they did with the 2D interface. And this leads us to believe that participants do benefit more from the VR interface, and when completing the first task, some sort of training happens where the participants that used VR learn to fly the drone faster. However, for the third task, again, so far we haven't noticed that significant results where participants took roughly the same time with both the interfaces. And this leads us to believe that participants might learn to fly the drone, like simple drone navigation, faster with VR, but complex drone navigation still requires additional training. We also analyzed user demographics for the third task, since it is quite a complicated task. And we noticed that participants that had prior VR or robot experience were able to perform much better. Especially participants with the VR experience performed twice as better than the participants that had no VR experience. And since this big gap in performance still remains, with the results we have so far, it's hard to conclude that VR actually helps reduce the user training for drone operation. We have a couple of future work planned to build on this experiment. First of all, we noticed that from participant feedback that they experienced a lot of latency with the VR interface. And this is mostly because we are constrained by the network bandwidth and could be resolved by improving the interface. However, the users were put off because of this. Secondly, due to user or drone error, the drone did crash a couple of times, which caused its propellers to bend, and it became harder to fly over time. So we want to just incorporate some sort of safety mechanism to warn the users before it crashes. And finally, we just want to keep conducting the study with more participants sampled from a more diverse background so that we can reduce some of the learning effects and get more significant results. This slide details our contributions, and I'll be also around to chat more in the poster session. I'd love to welcome any questions. Thank you.
So much. We keep the question for the poster. I think with that, we are concluding this part of our workshop. So please attend the poster and keep your questions there. And we'll be back in 10 minutes.
Ricardo. They're across the hall. Maybe you guys, like, the three of you can, or you can call him from across the hall. He's just across the hall there.
Who was?
Carlos.
Oh yeah.
For the award. Name this. Videos.
Animations. Yeah, through the next slide as well. Sorry. Animation. Okay.
Yeah.
Thank you.
Thank you.
So you don't actually have how. So where are you now? CXT and work with the we have a schedule upstairs for a while. And then we have a paper together. Yeah. Remember, right?
This one?
Yeah, it's great to see. How's everything? How's the conference? I'm trying to go. We don't know. I know.
I'm just kidding.
So great. So what's the next step after poster? Yeah, I'm going to be on master's this year. Oh, you are a marker? Yeah. So what is your what will you do about this? Surgical or? I think like general body, it's fine. General. So
later.
And like check the application.
It's okay.
Yes.
This middle one is also video. Yeah.
Yeah. One is
okay.
You don't have three. One in biomedical. Biomedical is more like overhead data engineering, right? So it's not technical. Okay. So I think that would be good. We are going to have one air robotics, which is quite close to science. That's electrical. Mechanical, you can have general robotics. So, anyways, email me and we can chat about it.
Yeah, it's a little more than I would like. No vision too much. Yeah. Oh, finally.
So we have been discussing about the resistance and how we get the smaller data set. It's not just you hundreds of terabytes. Yeah. It's not something we can put anywhere. Last time to start.
I think we're good. Okay, good.
Please seat yourself.
Is it official now?
Not yet. No, the rounds at the end of the one.
No, official in terms of the session, the panel.
Yeah.
Okay, we are gonna start our panel. So, attention, please. So I would like to ask the panelists to come to the podium. Come into the.
It's no, that's you want to mute here, and also if possible, click on her, click then live, and put her here, and then when she's done, unmute and put us.
Gotcha. I'll do my best.
Like you can go like this and say send live.
And then click on that.
Same thing.
Is there going to be a button that changes once she is live to like end live, and then I go?
No, you can go like this.
Are you okay now, or should we?
Right, so she'll go there, and then you can click on.
Oh, and it'll accelerate.
Yeah. Takes a moment.
Okay.
So you are able to hear me? Yes.
Yeah, if you can, I'm going to manage this.
Okay, what we're gonna do? I'm gonna come. Yeah, go ahead.
Come up here.
I'm gonna come with the question, ask you, and then ask your opinion one by one. We go around, and then we go to the second question. Okay.
So let me. Do you want to introduce him?
No, you go for it.
Okay. So I'm going to introduce a panel. Just call out to everybody in that topic. So thank you very much again for joining us for this panel discussion. This is a golden opportunity for us as a workshop organizers to have representatives from industry and academia on the same panel. So we'd like to take big advantage of that. So on the panel today, we have in front of you, this Professor Jiwan Ryu from KAIST in South Korea, this Professor Manuel Cabrera from UMass Lowell, Mr. Carlos Vallejo Gonzalez from Meta Reality Labs Research, and Jeff Del Merico, who is a research scientist at Microsoft Mixed Reality and Robotics and AI Lab in Zurich. Online, we have Professor Cynthia Matushek, who is from University of Maryland, Baltimore County. She's also joining us on the panel. So I'll let my colleague Farooq to start off with the first question to the panel.
Okay. So I have a couple of questions. I'll start with this one. So imagine it's 50 years from now, and we make a time capsule right now, and we put it on the ground, right? And 50 years from now, we're going to open that, and we're going to see which one of you has a closer prediction of the future of extended robotic reality at that time, right? So think about it and tell us what you're going to see 50 years from now under this umbrella of extended robotic reality. Right? What is it that you can see, and what is it that you want to see? Who's going to go first?
That's what I was going to say.
Yeah. I can go for it. 50 years.
Thanks. That's a great question. So I think what I would like to see, and the direction that I think, it's my just to reconstruct the field, but I think not only Microsoft, but everybody else who is involved in the XR devices game would like to see XR technology that is more ubiquitous, that is possible to integrate in more day-to-day lives and not just be something that you put on occasionally for particular things, the workplace or so really going to more of an eyeglass form factor for XR devices that we'd then be able to use persistently throughout the day. And that would, I think, really, that from the XR side would really offer, open a lot of doors for the human-robot interaction that we can imagine, but also, be more prevalent in 50 years with, I imagine, a lot of more domestic robots and service robots that we would encounter. So whether it's the cleaning robots you see out on the floor now or things that we haven't even picked up yet, that if we have a lot of different, if we have both robots and people all equipped with XR devices, we have a lot more opportunities for understanding between humans and robot intentions, and also in collaboration between human and robot tasks, in not just in the industrial and commercial space, but also in the private space and in our homes and in the public. So I think that's my vision anyway, but I'm curious to see if there's a different perspective from academia or Meta.
That's great. That's great. You go for a second. From Microsoft to Meta.
Yeah, 50 years is a long time. Yeah, there are many things. I retrospect 50 years we started to colonize the solar system. Yeah. So maybe with robots would be the way to do it, right? Maybe it's dangerous to do it as humans. But more practically, I expect many things to change. We are seeing, when I think about robots first, I think about in general, any type of artificial intelligence. Doesn't need to be the physical world. So we are seeing technologies like large language models, how they interact with us, and I expect there's going to be, it hasn't happened yet, it's not there yet, but we're going to see a big revolution of how they assist and help us day to day. So we're going to need better interfaces. We will be discussing about haptics, etc. I think one of the big revolutions I think is coming is augmented reality. So this is going to be glasses, something that you can wear, or it could be like a, put more smarts on the watch or some other type of wearable device that will allow us to more naturally interact with all these systems, augment day to day how we do tasks. Like these systems will be with us all day. They know everything we do. They'll be able to give us basically more contextualize all the answers to our work, which is the part is missing. You look at all the robots, they part of the miss on the interaction we have with them is different context. They have a context, we have a context that's very different. Right? So now you have these robots sitting with you all day. Could be a pair of glasses, a watch, whatever, right? Or a combination. Now they can provide answers to or assist you in much better than anything else. I think this is definitely gonna see 50 years. I expect much sooner than this. And then maybe from my background, I would expect we'll have self-driving cars. Like I don't need to drive my car anymore. So I don't like driving very much. So, so I expect that's going to be also a reality. Anyway, a few predictions there.
That's great. That's great. Thank you.
Yeah, I'm going to base myself off of some of the things that I've seen now and that are kind of major blockages. For instance, I attended a RoboCop competition. And when you are an spectator and you have no idea what the terminal is outputting for the people that are programming the robot, you have no idea what's going on. Why is the robot not moving? So trying to convey some of this information that is happening when the robot is thinking, how can we convey it back to the public? And I think AR is going to play a big part of that once we reach a point that it's more ubiquitous. So, and I think that's going to take not only AR and not only robotics, but also this concept of Internet of Things to include it into and embed it into all of these solutions so that it's a more integrated approach. And I respectfully disagree with you in terms of the embodiment. I do think that some of these devices, some of the problems that robots have failing at home is that maybe they are constricted to a single body. But if we are able to, just like in the Internet of Things, that the refrigerator has one sensor and the other has one sensor, if we can have intelligence that can maybe use different robots or different bodies if it needs to do different tasks, we can maybe achieve some of these larger, broader tasks at home. So that's my opinion.
This is an unexpected question.
That's why I shouldn't be on panel.
In my lecture slide, I put two photos. If full virtual reality or virtual extended reality, and all the technology in real life, then we may not have about how. So great. Right. So,
okay.
I'm going to watch people. So
those are really great answers to have to try to add on to. So a couple of things that come to mind for me is I think we'll start to see extended reality in more of an environmental ubiquitous sense. So not just like glasses and watches and things that people wear that make it like human-centered on the augmentation, but also we'll see like projectors in the environment where if you want to know what's on the other side of a wall, it will show you without necessarily it being things that are attached to people rather than, say, rooms where you go to do certain tasks and things. The other thing is I think we'll start to see a real blurring of what we call sort of augmented reality. Like, we don't really talk about people with glasses and without glasses, like people who can see and people who don't. It's just sort of a default technology that's incorporated into day-to-day life. And I think everybody will just as the technology becomes really great answers to have to try to add on to something that we refer to as augmented reality. A couple of things that come to mind for me is I think we'll start to see extended reality in more of an environmental ubiquitous sense. So not just like glasses and watches and things that people wear that make it like human-centered on the augmentation, but also we'll see like projectors in the environment where if you want to know what's on the other side of a wall, it will show you without necessarily it being things that are attached to people rather than, say, rooms where you go to do certain tasks and things. The other thing is I think we'll start to see a real blurring of what we call sort of augmented reality. Like, we don't really talk about people with glasses and without glasses, like people who can see and people who don't. It's just sort of a default technology that's incorporated into day-to-day life. And I think everybody will just, as the technology becomes more pervasive, it'll also become less something that we refer to as augmented reality and become more just, the standard information pop-up boxes that everybody relies on.
Comments here. I need to make a quick advertisement and then I have a second question follow-up then. So I heard 3 times the word of ubiquitous. And so we have the UR Robotics happening in 2020. So we have the general chair of UR Robotics it's happening in New York and NYU and the program chair. So something to take her.
I think in the last 5 years, the biggest step we've made, maybe this is
so now,
a little bit of a cop-out, but I don't think it's technical. I think it's beginning to understand the concept of extended reality as this set of augmentation and virtual and different concepts that tie together into the whole idea
that our society
extended.
Or
computer science society or
thinking of
general
those
society has
as
taken
a
the last
field
5
of
years
endeavor
towards
that
that
we can
goal.
start having
And what is the
workshops and
most important
conferences about and
challenge
things
for us right
is
now in the
is a
following
major
5
step,
years
and it's
towards
not
that goal?
necessarily obvious
So
until then. You've
what
got
you've
people
done
who aren't
great
talking to each other
to get your
and
vision
aren't,
50 years in the last 5 years,
collaborating
and
and
what
getting
is the
the
challenge
pieces put
that we need
together
to focus,
to build these
like
really
be laser
impressive
focused on
systems
it
that we've
in the
seen
following
today.
5 years.
And for the
Take
next
one
5
step forward.
years, I think continuation of that is more critical than any single technical piece we could pursue. Building a community of people who are focusing on working together. You know, I think in the last 5 years, the biggest step we've made, maybe this is a little bit of a cop-out, but I don't think it's technical. I think it's beginning to understand the concept of extended reality as this set of augmentation and virtual and different concepts that tie together into the whole idea of extended. And I think thinking of those as a field of endeavor that we can start having workshops and conferences about and things is a major step, and it's not necessarily obvious until then. You've got people who aren't talking to each other and aren't, collaborating and getting the pieces put together to build these really impressive systems that we've seen today. And for the next 5 years, I think continuation of that is more critical than any single technical piece we could pursue. Building a community of people who are focusing on working together in this space.
Do you want to go with that over there? Do you want to do that next? Yeah. All the questions I mean difficult.
I love the easy ones.
I need to go. No.
Okay, so maybe I can answer the whole. There's 5 years. Take your 5 years. So I understand saying that this workshop. Extended reality and all the technology. What we've been trying to do is trying to find what kind of information we can transfer, additional information to transfer to increase the understanding of the situation and to better controllability of robot like this. But this is more like a case by case. More like a case by case. Someone's working on medical area, someone's health area, someone's working on education. So it's case by case. So it depends on application. We've been trying to find some of the what kind of additional information, what kind of things we need to transfer to students. But maybe in future 5 years, we need to put efforts together to find what are the important human factors to increase this levels of human understanding situation sensors. So there must be some common framework or things to overcome this pivot point. I believe that's something that we need to find together. Then maybe psychophysics or human factor study is essential.
Thank you so much. Yeah. Next panel.
Yeah, these questions are different, but I think I'm going to focus on things that we've done well in the past few years. I think I'm going to take a little different spin and say that I think, especially in the field of XR, AR, VR, there's been a big push for including more users. So there has been a lot of research of how can we expand VR, AR for people who are blind or are low vision. And all of these things I think is really important because, I don't know, I see in the future that if we want to make robots or AR systems as common as the phones that we all hold in our pockets, we need to think about these levels of inclusion of a broader audience. So addressing some of those issues are very important. So I think that part is really good. And then in terms of the future, because of we have the example of the phone that has become so pervasive, is I think we need to take advantage what can we use of what worked in the phone that became so prominent, and what can we take advantage of that and apply it into the way that we use robots or use these systems so that it can be ubiquitous.
Okay, so maybe three from two areas, right? I'm going to tackle this more from the as a first area from the hardware side. There is a lot of friction today with VR devices because you need to strap some like a cell phone on your face, right? And then you get sweaty and it's annoying, and also detracts from the real world, right? And I think this is only a step. I think AI is going a step with something all-nighter, etc. But the hardware, the technology we have today is not yet capable to produce displays and have the form factor that also has to look nice, so that you can have that experience in a way that you can wear it seamless, right? So there has to be big advancements on the hardware side, and that's a big risk. And we have like obviously companies working on it, but I think this is still would require an active area on pretty much any area of research, especially space, but also batteries, low power compute devices, a lot of technologies. Okay, that's one area. I think the other area, I think something we were discussing earlier with Nikhil, I've seen these presentations. There is a lot of focus on how we interact with robots at distance. And I think something that is going to be needed to put a lot of effort is how to make these robots more autonomous, more independent. Not only from the hardware side, but also from the decision-making side. So that we don't need to actually interact so much with them, especially in areas or in positions that is very difficult because sensing is too slow, or there is no bandwidth, or problems like this. So this is why we see today a lot of investment in models that use a lot of data. This is all the field-optimized AI and also foundational models use as much as possible, rather than having to rely on very expensive labeled data, rely on basically any data and being able to train self-supervised models with lots of data like that. We've seen when you do that, sort of magical things happening. Like for instance, the large language models is one example. So ideally, we'll be able to see these in more areas in such a way that we can actually move closer to some sort of like some level of generalization of AI, so we can make these robots more independent. My hope is 5 years we can see at least that solve to some degree with self-learning, which is one place where very clearly a robot that cannot make decisions on their own, that is in a safe way, and been pushing that tech for 10 years and still not that.
Okay. Regarding the past 5 years, I think going in a completely different direction and say, I think one of the most important things, at least in terms of mobile robotics and XR, is the availability now of a lot of commercial platforms that can really operate in more unconstrained environments. If I think about 5 years ago, you didn't have any of the quadrupeds on the market, really at that point, and most of the other ground platforms were really for logistics and things like that, as far as robots that were available in the commercial space. And we're, I think, moving into a phase where the robots that some company or customer can just buy and deploy in their environment, they have a lot more capabilities to operate in these unconstrained or dynamic environments. That's going to play a big role, I think, in the future in enabling XR-based human-robot interaction to really have, to create demand for that. As we have more humans and robots working together in these types of environments, where in the past, usually the robots worked over there, and then worked over here, and there wasn't a lot of coverage. So that's the one point. And the other thing to echo the point about the displays, I think that's one of the biggest challenges, to bring the head-mounted display technology to a place where people would actually want to use it throughout the day. Is the displays will have to improve tremendously. That's one of the biggest complaints that I hear about the HoloLens. Even though the team that works on that in Microsoft made huge advances in, like really increased the field of view and resolution and brightness and sharpness of the display. That is still the thing that when people try the HoloLens for the first time, it's still the thing they say to me. It's like, oh, the field of view is so small, and it's dim, and it's heavy, it does the better, it doesn't last all day. And I really think there are a lot of technical challenges that have nothing to do with robotics that will need to be overcome before we see the kind of social and market penetration of XR devices for everyday people that we're imagining for the 50-year plus.
That's great. It's amazing. So I was, when I asked this question, I was wondering if you're going to hear about pandemic. And that's great that we did, right? It means that we adapt. We can bypass the challenge, and we can always think about 50 years ahead. So, great. Amazing. So I'm going to ask a question and I'm going to ask my great panelists to try to answer. It's a very specific question. So we talked about extended robotic reality in this workshop, right? So it's a term that is kind of being more common these days. And it's my question, my personal question, how we can separate it, or, I mean, from my perspective, it's different from AR, it's different from VR, it's different from MR, it's different from robotics, right? It's a mixture, right? So how you can think about this mixture, not just thinking about AR as an amazing technology or robotics that can be autonomous and help autonomous farming. No, the question is that this combination, this mixture, this merger between extended reality or virtual reality or augmented reality and robotics, how that's going to work. I mean, what is the future that you can envision for this? Or like what type of challenges you can think this merger, this specific merger can have? Or what benefits or what possibilities it can open for us? So I try to speak a bit slower so to give them time to my panelists. I'm just talking now, so they have more time. I think now I can get back to my panelists and who wants to talk first? Yeah, go for it.
Go to the turn.
Thank you.
Yeah, that's another good question. So I'm coming from a fairly narrow perspective in terms of mobile robots, mapping and localization, but I can give you my perspective on your question from that standpoint. And really, I think the key thing, and I talked about this a little bit earlier in the morning, when within Microsoft, when we're working on our localization technology, we're really considering all of these different devices, whether it's phones or HoloLens or robots. That's just they're all essentially solving the same visual SLAM problem, and they're all able to localize in the same environment. The environment is actually the thing they all have in common, and so we really think of robots as just another class of extended reality device, and I think the XR is really going to be the technology that connects people to the digital world. And robots already exist in that digital world. It also brings robots into the human world as well, because whether it's spatial representations or shared information through human-robot collaboration that's facilitated by XR. We really, that's a technology that reduces the barriers between humans and robots, and that I think really the future I would like to see is where XR kind of brings all kinds of different devices to and people, so that everyone can participate in the same digital environment, access the same digital information, whether it's in space or not. But I think, yeah, fundamentally, I'm really thinking of XR devices and robots as essentially one of them just moves on its own. The other needs to go on.
Thank you so much. Yes.
So maybe there are two sides to this question, right? On XR, this is, I think we always think about how we have the robot, right? The robot, it's with the same robots to help, like self-driving. We want robots to drive us, right? And in the more clear or more common use case, the robot is not capable of doing the task. And then we are looking for some way for the robot to communicate to us, hey, here's the reason not working, please help me. Right? So if this is one area that requires a lot of study, how the self-driving car can communicate with a remote operator to say, this is the problem I'm having, this is the object, I'm not sure if it's an option or not, or this one I'm confused, can you help me, right? And here about teleoperation, maybe for self-driving that's too dangerous to do, maybe we need something like this, but then you can apply this to any robot. How the robot communicates to the human to say, hey, I need help, can you please help me, right? But then as the robot becomes more autonomous and capable, probably will be at some point the other way around. How we tell the robot where we need help, right? And the robot come and help us, right? And that interface is not so clear, right? That's I mean, for the experts, I'm not the expert in XR, so maybe you can help me here, but that's, we should think right in both ways, right? That's my contribution here, that how we think about the two sides of the interfaces later. If I don't become more and more capable, which I expect to see not so far from now, in 5 years. And then optimistic.
I'm not doing time estimates anymore. We already did that. But I do think that the magic of XR comes into play is exactly where it closes the gap between the two worlds. Because if robots are working alone, they don't need XR because they have their code and they have their statuses and they have their optimizations and they don't need XR. And if if humans are working alone, they don't need XR either. They're really working amongst themselves. They have their physical work to figure it out. But then it's that combination. So if we are really trying to have robots that can help humans in any task that you put them, or if you want humans to feel that they can go and ask for a robot for help, you need that bridge. And I think XR is going to be a very big part of filling that gap and making that.
My perspective, actually, XR, AR, VR, robot technology should be combined in other parts. In my area, actually, XR is one of the key components to make complete body system. So it should be one complete system. We cannot be separate. But one of the things that may be challenged if you combine XR, including visual feedback, haptic feedback, auditory feedback, or multiple things, and robot technology, then there are all the difficult questions arise. For example, it is very difficult, special example, if we move your head, then the HMD moves, and we track the HMD movement, and this movement transmitted to the robot head. Robot head moves, and you're supposed to see what robot sees. But there's something that's confused, and humans start to feel very confused.
Okay, so again, to sort of springboard some of the excellent answers that have already been given, I think I see XR and robotics as a way of closing a number of loops that as things stand are quite open. So I'm coming at it from a human-robot interaction perspective. And there are a lot of ways in which human-robot interaction, like we can command a robot, or we can receive information from a robot, but we don't really have bi-directional human-robot collaboration. We don't really have good bi-directional information exchange. And a lot of those things are extremely difficult to do in physical reality. You know, they're hard to tie in these very large data approaches. They're dangerous, right? Human-robot collaboration in an industrial setting is somewhat fraught. And I think working through a lot of those questions, and in some cases, extended reality is all.
Thank you, Juhan. So we have one panelist online,
you're
Cynthia.
Working with something in a social context or in an information flow. So context. Again, to sort of springboard off the physical robot excellent answers that have already been given. That would make I think I see XR and robotics as a way of closing a number of new kinds of reality that as things stand are kind of open. So I'm coming at it from a human-robot interaction perspective. That this gives, and there are a lot of ways in which human-robot interaction, like we can command a robot or we can receive information from a robot, but we don't really have bi-directional human-robot collaboration. We don't really have good bi-directional information exchange. And a lot of those things are extremely difficult to do in physical reality. You know, they're hard to tie in these very large data approaches. They're dangerous, right? Human-robot collaboration in an industrial setting is somewhat fraught. And I think working through a lot of those questions, and in some cases, extended reality is all you need. If you're working with something in a social context or in an information flow context, you know, maybe the physical robot doesn't need to have all the capabilities that would make that possible if it can be augmented with the new kinds of reality. So I think there's a number of ways that we've got problems that are close together that this gives us an infrastructure for closing.
I ask one of my other colleagues to continue from here, but before going there, I just want to add a couple of points here. In the US, there's two NSF programs that are connected to this topic. We have a Smart Connected Society and Smart Connected Health. So if those of you in the US interested, I would suggest, I mean, I'm also academia is applied for those mechanisms. I think they're really good connected to the topic. I want to also mention that at IEEE level, there's actually future direction initiatives. And one of the main initiatives is telepresence, which is actually led by NASA, and it's all about telepresence. And they actually are one of our endorsers. I mean, they endorse this workshop. So the telepresence and the future of connectivity with 5G, 6G, robotics, so on and so forth. So now I want to ask my colleague Nikhil to take it from here. So I'm not going to tell you what was my next question, but and then you can improvise. Yeah.
I'm going for the next 100 years. No, I think one of the panelists needs to leave quickly. Maru, I think we're getting close to your time. So I don't want to maybe try to stoke some differences that I see between academia and industry a little bit. Maybe Maru, you can answer this first one.
That was my question.
No. So standardization, I think one of the points that came across also from the last workshop and this workshop is people are, so I have the impression that we are working in this field like we were working with robotics before ROS. So everybody's sort of doing their own thing and then trying to experiment or trying to utilize the way they understand XR to their application. And I think also there's a differentiation between academia and industry in that perspective in how to utilize the XR technologies and which direction they should go. So maybe I would like to get your perspectives on this, and Kumar, you can go first.
Put me on the spot, why don't you? Thank you. It's funny because a couple of weeks ago, I was in a meeting at UPenn that was talking about a robotics roadmap. And we had a question similar to this, but it was different areas like agriculture, service robots at home with this time. So it was more application based more than the technology. But it came up, and this standardization is something that keeps coming up. So how can we find common metrics, common benchmarks that we can take advantage of in both domains? So, and how can we kind of keep the best of both worlds in a manner that makes us go forward at a similar rate? And I don't have a good answer for it. I just think that it's important to acknowledge that it's something that keeps coming up, and that we need to keep working on it. I just don't think right now we have I don't have an idea on where to begin, but I'm excited to work on it. It's difficult. So standardization is one of the things, and I think also in terms of interfaces. So how can we take advantage of, and this is closing the gap towards the users. So how can we take advantage of things that users are already familiar with while keeping the trade-off of innovation so that we don't, keep a keyboard and a mouse forever. But keyboards and mice are everywhere. So how can we take advantage of them to kind of put the same idea back into things that we are developing now? And with that, I am gone. Thank you so much for inviting me.
Thank you very much,
So, who's next? Want to comment on it?
Yeah, I can speak to this. So, standardization, I'm not sure if you refer about tooling or metrics or common framework of how we can share results. At least I can say from the academia perspective, fields that advance very rapidly, for instance, has been detection, right? Detection of objects or presentation images. And I think one of the reasons for that is, one is the open sourcing of very large data sets. And then number two is very clear metrics that the community has agreed upon. So on this field, these two areas are complicated, right? The applications are so diverse that then it's hard to share what data are you going to be sharing, right? It depends on the application. And also what's the metric we were discussing about? Okay, metric maybe is if it's collaborative effort with robots, it should be the time it takes or it reduces to accomplish a task. But there could be many other metrics you could take, and it also is very domain specific. So that makes it very hard. So I think it needs to be more compartment. There has to be more like breaking down into different compartments. And then everyone we should decide, okay, with some metric, with some data to share here, and then start from there. And then from there we can go to what tooling, what code, etc. could make sense to share. But yeah, that's a hard problem. And for industry, I think that we have standards for different things. That's at least in this area, from meta perspective, at least in VR, we're seeing like Apple starting to compete. They have, this in the Vision Pro, and we have our line of VR products. AI is another area, right? So that's going to be a little harder. I think maybe, I don't know what the wound that would be, but how many users you see, how happy they are. So it's really, but yeah, that gets tricky for industry because more competitive environment, maybe framework. Yeah, that's what I have to say about this area.
Thank you. Thank you so much.
It's only a few small additional comments. I think as far as standardization and tooling, I think there's already some progress in that direction with the OpenXR and the possibilities of Unity and Unreal Engine to develop cross-platform SR experiences, at least for human-based devices. But I agree that the applications at this stage are so diverse, it's hard to generalize many aspects of the events are outside of just app design or user interface. But I will say one possible way that we can have some unity across the whole XR space is my perspective as someone working on cloud technology, but I think, we're, especially if we want to aim for the sort of small form factor devices that we predict people will want to wear all day, we're not going to be able to do all of the computing on board that we want to do to enable the features that people will expect. And so I think having the functionality of devices supplemented by external cloud services is going to be really important to achieving those long-term goals. And that's one of the ways, even though we have Microsoft as a first-party device, we have in the past and continue to be interested in supporting a wide variety of XR devices to interface with our cloud services, because that's, there are not only multiple, multiple use cases that don't always call for HoloLens, but also I think that's a way that we can, help bring more users together. So that's hopefully a unifying force in the future as well.
Yes, thank you. Maybe G1?
I think I briefly mentioned my previous sensor. So while academic point of view, in academic area, while we are so far proposing application-specific scenarios and solutions so far, maybe what academy need to do in research data is try to find some of the common framework or general approach to considering a lot of the important human factor to enhance and increase the understanding. And people to this people to this point. That's something that we need to work with. And maybe one thing that I want to ask industry. So one of the things that is visual perspective.
I'm coming at it from very much from the academia side, and I think it's really worthwhile to remember that, academia and industry are different, right? We have different sort of deliverables and metrics for what qualifies as a successful research program, but they're very complementary. They're very much, they're not just different in a competing sense, they're different in a filling in each other's gaps sense. And I think figuring out sort of the toolkits and data sets and metrics that we can share revolves around figuring out how that complementation works. What each group has that is of value to the other, and treating the fact that we have, some somewhat different goals as a desirable characteristic, as a good thing, as a diversity in the community.
Thank you.
So I'm coming at it from very much from the academia side, and I think it's really worthwhile to remember that, academia and industry are different, right? We have different sort of deliverables and metrics for what qualifies as a successful research program, but they're very complementary. They're very much, they're not just different in a competing sense, they're different in a filling in each other's gaps sense. And I think figuring out sort of the toolkits and data sets and metrics that we can share revolves around figuring out how that complementation works, and what each group has that is of value to the other, and treating the fact that we have some somewhat different goals as a desirable characteristic, as a good thing, as a diversity in the community.
That, I think this concludes our panel. I would like to, on behalf of the organizers and everyone here, thank the panelists for being here and answering our questions. So thank you so much for being here and sharing your amazing thoughts. It's always great to hear from academia and also industry side by side. So that's one of the features of this workshop. So follow us. Next year, we're going to have it again and continue this discussion. Thank you so much. So now we can go to the next part of the.
We should go to the final session of the poster papers, and then also stay tuned for the award ceremony at the end.
Okay, we have the posters now, and then.
Yes, and come down for more. It's a little strange. Yeah, but this have this in the sample. I can do it.
Yeah, do you want to call this as? Sure, we have plenty of people there. One person. Yeah. But make sure. Yeah, I mean, you want to think that's it. Other directions. Okay, we continue.
Yes, I can make it.
Yeah. Wait for that.
This is right now. I need to be
Oh, yes. Okay, so welcome to the final session. We're going to have 3 poster presentations, and then we'll follow up with the awards presentation at the end. So first up, I'd like to invite, hang on. Ricardo Franceschini. Okay, good, thanks. Slides are already on here.
Yeah.
Presentation. Yeah, should be
on desktop.
On desktop, no?
Yeah.
Franceschini, please. You just go to. From the link. Okay. Let's start?
Yes.
Okay. Hello, everybody. I'm Riccardo Franceschini from EverCut, and today I will present the paper entitled Riding the Roller Coaster, Using UAV Piloting Experience with XR and Continuous Planning. The motivation behind this paper is that UAV have expanded their capabilities in a task that are ranging from rescue and search scenario to industrial inspection. However,
Most of the time, for safety reasons, teleoperation remains the prevalent mode in those scenarios, posing no trivial challenge for the operator, both from a piloting perspective and from a situational awareness point of view. For this reason, we believe that easing the piloting experience is of utmost importance by creating a piloting experience that is as easy as naturally, simplified as much as possible while maintaining the control on pilot hands. And on the other hand, we want the pilot to be aware of the surrounding space and the sensor data of the UAV and the decision that the UAV are taking. For this reason, what we are proposing is a processing layer named roller coaster, as the title of the paper, that blends the user input with an external plan that efficiently compute in real time to create a collaborative planning interaction. And at the same time, it proposes a user interface over the drone remote piloting device to show the path planning that is going on, the mapping information, and so on, such that the operator is fully aware of the processes that are going on. In particular, considering this basic schema of a drone, the retrieved path, we use JPS 3D, that, as I said before, is a very efficient on a commercial laptop, allows us to run at 100 Hz, more or less. And what we want to achieve from an operator point of view, we want to control the desired position, and we want to control the velocity that the UAV must reach at the next position, which is the highlighted position here at the bottom. And we want to control the velocity while leaving the actual planning and so decision making of avoiding obstacle and guaranteeing a safe path to the UAV. The interaction of the roller coaster is done by a PS5 controller that is exploited by its commercial availability and by its capability of having like adaptive trigger that are used to giving haptic feedback to the operator. And with the adaptive trigger, we control the velocity along the path, and with the thumbstick, we define the direction on which we want to plan. In particular, by simply controlling the thumbstick on the left and the right, we define the position in which we want to go, that is positioned at a fixed distance from the current UAV position, while with the left trigger, we control the velocity, linearly scaling according to a direction vector that connects the current position of the drone to the next actual position. And at the same time, the haptic feedback is used to give in real time the sensation to the operator of the velocity that gets stiffer the faster we go and gets lighter the lighter we go. And on the other hand, of the roller coaster framework is what we are going to visualize. We are visualizing on the remote camera interface the simple path that is retrieved and it's superimposed on the camera stream. And proposing also the visual feedback. And but the problem is that since the camera of the drone has a limited field of view, we also put in parallel a 3D representation showcasing the 3D environment and the sensor map, such that the operator is always fully aware of what is going on. A brief visualization on simulation here is proposed. We have on the right, which are sample of the piloting with the path superimposed, and with the path that is represented by the yellow line, while the gain, which is the velocity, give immediate feedback to the operator through this green line that changes dynamically with the velocity. And while the 3D representation is proposed here and is a basically 3D visualization of the environment with the desired position and the actual position that we are sending to the operators over the camera stream. A brief representation of how does it work is here proposed. The operator simply control its me that is doing and have zero piloting experience. Simply control the drone in this very cluttered environment. And whenever you press the left trigger, the roller coaster is initiated and the UAV starts to go and avoid the obstacle. At the same time, the operator can control the direction and move freely in the environment. As you can see, the operation is quite easy and doesn't require a lot of mental workload for the operator, because what he has to do is simply to control the velocity and control the direction. And the UFV takes in charge of passing through narrow spaces and so on. At the same time, when the operator wants to regain the full control, can simply release the trigger because maybe he wants to gain the control, and then take it back whenever it's needed to pass through narrow spaces and so on. Of course, this is a planner that plans in a 3D environment, and it works in any space, so it can also plan in avoid obstacle not only horizontally, but also vertically. Therefore, we proposed a semi-autonomous drone navigation through a collaborative planning pipeline and improve situational awareness through enhanced visual elements such as overlay trajectory and haptic feedback with the PS5 controller. Next step that are being carried on and almost done are focused on user validation, validating the effectiveness, has shown important results on the validity of the framework. And then also we would like to advance integration, including further device and immersive display. Thanks. If you want, there is a video on that.
We have some time if you'd like to ask any questions. Okay, I'll ask one real quick.
Yeah.
So have you tried any real-world experiments? Simulation?
Yeah. I mean, have a kind of video here that we tried the real-world experiments. The problem that we tried in a tunnel, and it was very bad situation. And it was running on a laptop, like was a Latte Panda computer that is very low power, and was running at around 30 Hz. The problem here that we were facing a lot of communication problem. The main because I was standing behind, and I was basically, okay, no, this is not safe to do it. And then between the submission and everything, I haven't tried yet.
Gotcha. I will look forward to the follow-up. Thank you. Okay. Thank you, speaker. Next, I'd like to invite Yifan Zhu to the stage. And okay, and just a second. There. Okay.
Press the space.
Yeah, you can use the arrow keys.
Yeah. Hi everyone. This is Yifan Zhou from Arizona State University. Today, let me introduce Immersi, an immersive mixed reality system for bidirectional human-robot interaction. In this system, we utilize mixed reality to create an engaging environment for human-robot interaction. We actually create this parallax 3D effect in the human brain. With that, we are able to collect high-quality human demonstrations for imitation learning. We utilize mixed reality because it provides a variety of different scenarios very quickly and with minimal cost. You just need to put different objects into the environment, and you are able to ask humans to collect diverse sets of demonstrations very easily. However, for that, we will also need an intuitive and engaging input system to collect and track the human motions. Currently, many people use this space mouse or joysticks to control the robot and provide human motions. However, as long as you've tried that even once, you realize these are not that intuitive to use. Therefore, we also need a better solution to track human motion. With all of these in mind, we propose this immersive system. It has 3 building blocks. The first one is the mixed reality projection, the visualization interface, composed of the projector and the camera. The second one is the human motion tracking system. we propose to use a smartwatch and a smartphone to track human motion. Finally, we also have this object generation pipeline. It's an automatic pipeline. It can convert text into the 3D object files that can be put into the environment and manipulate directly. Let's talk about them one by one. The first is the visualization interface that creates the 3D parallax effect. In order to do that, we firstly have to do the head tracking with the camera. By tracking the face location in the 3D space, we are able to just simply put a virtual camera in the simulator in the same location and collect the image and render the image and project them back into the real world onto the table. With this functionality, you can see in the figures here that when the human steps into different locations, the visualization on the table from the projection also changes accordingly. This creates the 3D parallax effect. Another thing is that in order to enhance the depth of perception of the human user, we also add a shadow to the gripper. This is shown on the right figure. Using this functionality, it provides a very intuitive way of how high the gripper is from the table surface. The second part is the input device. This smartwatch and the smartphone system actually works very well. We just need a smartphone to track the upper limb and the smartwatch to track the lower limb. And you can see from the GIF here that the avatar is following the human figure actually very precisely. Finally, we also have this data generation pipeline. We can basically generate infinite numbers of object files with very low cost. In order to do that, we leverage the power of foundation models. The first step would be generating some RGB images of objects by utilizing, let's say, DALL-E 2 models or stable diffusion models. With the RGB image, we can also do a depth estimation using some models like MIDAS and DPT. With the depth map, we then are able to create the mesh file. After do some smoothing of the mesh file, we can finally attach the RGB texture back to the mesh, where we finish this pipeline, generates the object. With these three building blocks together, we propose Immersi, which is a mixed reality system that creates the 3D parallax effect for human-robot interaction. And we collect human demonstrations with that. Now here is the question. Does this system yield better data? Let's find them out by experiments. If we want to say they have better data, then we need to prove the policies trained with the data have better performance. With that in mind, we ask human subjects to collect demonstrations of picking up an object. We train policies on those data, and you can see in the middle the evaluation results. The green one is our proposed method with the smartwatch interface. It outperforms all of the baselines. The baselines include kinesthetic teaching and base mouse. We also do some subjective analysis. We ask the human subjects to fill out the NASA-TILALEX indices as well as the system usability scale. Our proposed method is the first row in green. You can see that on the NASA-TILALEX side, our method has the best overall performance, and especially on the frustration and performance, these two columns is actually much better than the others. For the system usability scale, our proposed smartwatch also reaches the best performance together with kinesthetic teaching, outperform the other baselines and ablations. In conclusion, we propose this immersive system, which allows for intuitive data collection of robot behaviors using mixed reality. It provides better data quality, which allows for training a better policy. Human subject studies also show that users prefer our method better than others. If you're interested, please check out the code base. Thank you very much.
I think we have time for a question from the audience if someone has one.
You mentioned about the data generation, like this is synthetic data generation that you talked about.
Yeah.
And then you have the pipeline for generating point cloud from this synthetic data. Is it?
Yeah, exactly.
Okay. How do you take into account if there is any latency in displaying this point cloud or transferring this point cloud for the user? Is there any latency that you
so for that process, we simply just take the depth estimation of the object and basically create the mesh from that depth estimation.
Okay. Yep. But this is in the same computer?
Yeah, this can be in the same computer, or we can also communicate the information via ROS on other computer. All of them are okay.
Any other questions? If not, let's thank our speaker. And I'd like to invite Chris Suarez to come up for the final poster presentation of the day. So just to check, and then just need to make sure that it's. I just need to make sure it's good here. Okay. Sorry.
Hi everyone, I'm Chris Suarez from the University of Texas at Austin, here to present our augmented reality user interface for command and control of supervision of large teams. So the motivation for our augmented reality research pretty much focuses around all the same similar problems that we all face in this room. So specifically by this, like search and rescue or intelligence gathering missions like scout platoons, where you have one complicated task that you need to complete with multiple agents, specifically multiple autonomous agents, multiple human agents. That's what we're focused on. So previously, we presented AUGRE, our augmented robot environment framework. This was a couple years ago, and we basically showed that we can render holograms of autonomous agents and human agents in the same environment, and you can do this up to, it was scalable such that you can do it for about 50 plus robots. The problem in this video that we had is pretty much you can only interact with these in line of sight in the same environment. You can see those menus, you can't even read them. You can't, in that it's really hard. So we're going to just propose a couple new solutions to that. So what we contributed to that this time is we greatly increased the situational awareness of both users in the system and users outside the system. So I will talk more about that next few slides. So interaction capabilities in line of sight, non-line of sight operations, sensor feedback. Right now we're doing camera feedback, but I will show that as well. And more intuitive operations, giving autonomous agents commands. Okay, so as I said, we improved situational awareness on the left there. You can't, all of the robots and all the autonomous agents had a full menu above them all the time. It was very hard to interact with. We switched that now to we're using NATO symbology. So there's a very simple NATO symbol above every autonomous agent. When they get far enough away, they also group together, just like your iPhone displays how many messages you have. You might have 10 robots in a certain direction that you can all group together. And then if they're far enough away and you click on the NATO symbology, the menu actually pops up in your face and you can actually read it and interact with it. On the left there, we're showing our capability of localizing these agents relative to GPS reference world frames. So specifically, these autonomous agents, the HoloLens 2 does not have a GPS, and the autonomous agents that we have in the system also do not have GPS. But because we save multiple anchors and their metadata, and we reference them to, all we reference is at least one anchor to a GPS coordinate frame, and then all of a sudden every agent can extrapolate their GPS position and report it back. So that's what you see here on the left. And on the right, what you're seeing is one of our robots out in the field and providing feedback from multiple cameras to a remote user. That camera, it might be hard to tell, but it's actually running darknet, so it also is reporting bounding boxes of objects it sees in the environment. So let's say a robot is running darknet or some other object detection. It also has the capability of reporting back what it sees. So in this case, our Jackal robot found a barrel. It takes a second to send that image, that full image. And then when it's rendered, you can see our remote user there can see the entire image, has the bounding box around it. The user has the ability to dismiss that or delete it entirely. So you can imagine a case, we've seen this, where if you're looking for cars on campus or looking for people on campus, you get hundreds and hundreds of notifications. You might not want to delete them all, or you might want to save some. So you have all those capabilities. And something I didn't note there is actually there's a physical diamond that's rendered in the actual pose. So if that person were to walk over, if there was a line of sight user, they would see where that Jackal thought that barrel was. So yeah, in this case, this is all taken from our demo video. If you go online, you can see it. But Jackal found a barrel. The remote user wants to get a better look. So the remote user can actually take virtual teleoperation control of that Jackal. So on the right there, you can see the Jackal actually moving with the commands of the person on the left. When the Jackal gets a better look, it notifies the users again, hey, I got a better look at the barrel. And in a second here, the remote user is going to turn to the right and actually going to show me, because I'm the guy in the field, just managing the Jackal there, making sure it's not doing anything crazy. And yeah, we also have the capability of sending autonomous commands. So I'm the user here, actually going to give a waypoint navigation about 30 meters away to the Jackal. So we can step it out. I can just send it to 30 meters, hit send goal. It turns green. Some of it turns green, some of it's still red. The Jackal starts driving. And this is going to go double speed here, just so, and sorry, my head bouncing was a little annoying. But once it gets there, the whole waypoint will turn green, confirm that the robot has made it to the waypoint. And we also have the ability to send multiple waypoints. So here we send 2 waypoints to our Husky base. And you can see, actually, we can turn this on or off, but you can see the global plan that the robot is providing to the user here. So if, for example, the global plan looked ridiculous or something that didn't look right, the user could take control if it needed to. We also can display both the global plan and the trailing path plan. So like the previous poses, if you can't find it and you want to know where it's been, you can find it as well. And the most advanced command we have is autonomous user to human user following. So if you press a couple buttons on the menu and then you verbalize follow me, the autonomous agent will actually follow you back to wherever you want to go. So at the end of our demo, we do the barrel search task. We tell both agents to follow us, and both agents follow us back. Other work that we're doing, you might have seen this around the conference here, but so we're also, our labs focus a lot on radiation work. So this robot here is doing a radiation sweep of the environment, and humans can't see radiation, so you don't really want to be exposed to it. So what's nice about augmented reality is that this can help you visualize something dangerous like that in the environment. So you can see here the radiation sweep of the environment, and then you can see where this simulated radiation source was. And then Frank has also presented in this presentation our augmented reality work with interacting with objects with screw theory. So here he's pulling a drawer and he's opening a door and creating a screw axis so that an autonomous agent can come along later and perform those tasks. Here you can see he's turning a valve, and then later the vault bot comes along and turns the valve as well using just the screw axis. So in conclusion, we improved a lot of stuff. We're working on a lot of stuff. Please check out our video, and feel free to reach out to me. We actually do demos a lot. I can actually run this demo by myself. But yeah, okay, thanks.
If there are any questions from the audience, I think we have time. Nikhil?
Just curious, you showed the videos also one in double time. Was it a conscious choice that the robots were moving so?
Yeah. We have a lot of students that walk in that exact area all the time. Okay. And they don't adhere to robotic norms where we very often is the case where like we did a couple of videos where a student will just put their foot right in front of the robot. Right. And without thinking about it, they just feel super comfortable with it. And as operators, I just don't want any risk. So yeah, I was having it go nice and slow in those cases. Yeah.
But you're not doing any on-board real-time navigation or time because you map the area already.
No, I am running SLAM, kind of like Jeff said. So I run SLAM on each of the robots, and then I reference that SLAM with anchors. So I just add another frame for each anchor. Yeah. But we put a bunch of anchors down, and only one of them has the GPS reference, and then yeah.
But that's not the reason they're going slow. It's just you.
No. I tuned it down. Yeah, I just tuned the navigation down. Yeah.
Any other questions? I have a quick one. Mm-hmm. So among the other stuff that your team is working on for the future, have you started to explore kind of multi-user, multi-robot scenarios using that same framework? So it looked like, or at least I understood all those videos were one operator and a bunch of robots operating autonomously. Is that already multi-user, or are you looking into that?
In that demo, we do have 3 human users, okay. But in kind of what you get to there is each user is doing a specific task. So we have 3 humans and 2 robots. 2 of the humans are managing 2 of the robots, and one of them is a remote operator. Okay. Kind of managing the overall task. But yeah, so getting to 1 human to 4 robots, or 4 robots to 1 human, or 4 humans to 1 robot, that's, task management is still another thing to work on, but yeah.
Okay, cool. Thanks. All right, let's thank our speaker.
Let's move down. Okay, anyway. So we are at the end of the workshop today. Thank you very much for sticking around. I think we had very, very interesting talks today, and also the keynote speeches and the author paper presentations. This gives us a lot of sort of encouragement and motivation, because this is the second time that we are organizing this workshop at IROS, and the idea from the first year was to build this community, and as you saw from the panel discussion, I think there is a lot of interest in building this community for people to work together and take this forward towards 50 years hence, what Farooq was and the panel was referring to. So thank you very much for your contributions and being available. Hopefully we can build on this and take this forward, keep going with this sort of convergence of XR and robotics in the future. So with that said, I know people are waiting now. We have the award ceremony. We have the prizes. So the award, let's say, committee was based on two parts, as I had written on the website. So we all the authors submitted their papers. They were evaluated on open review, and all of the open review, the papers got their ratings, and the top rated papers were shortlisted to be then analyzed on the day today. So we had this award session in the morning, and the judges for that were the three organizing committee members, Farooq, Daniel, and Jeff, and also Carlos, who's the representative from Meta that we had today. So putting their great minds together, the four of them have come up with this top three winners. So I'm going to go one by one. One as the representative of the Haptics Technical Committee, which is sponsoring the third prize. And the winner of the third place for the XR Workshop 2023 is Shubham Sonani for Can you go down there? So again, thanking the Haptics Technical Committee for sponsoring the third prize for our workshop. We have the second prize, which is also recently sponsored by Meta. They're going to give a Meta Quest Pro as the second prize, and that goes to Frank Riegel. Thank you for coming back. Good use. All right. And the first prize for the XR Workshop 2023 actually goes to an online presenter who's a member of my group, so I'm very proud of that. Jonas Theodros Tefera, for his contribution on gaze-driven immersive teleoperations. Congratulations to Jonas. Thank you very much, everybody, again. We can have everybody in the front so we take a photograph together. Here we can have the three winners seated in the front with the certificates. What else? Yes. Or we can switch. Yeah.
Thanks for supporting the workshop.
We can be
Am I in that? Do you think in that?
Yeah. 1, 2, 3. Can you get also the? Yep, I have everything.
Thank you. That's all.
Thank you. Thank you, everyone. Good luck. And we'll see you hopefully next
month. Great talking to you. So we'll be in touch.
Yes.
See you in New York. And
How are you? Thanks for coming by.
Yeah. Jeff, thank you so much. It was great. Yeah, likewise. Love it. Yeah. So let's keep it going. Yeah. Thank you for